Welcome, welcome. We are getting started up. Today's event, March 6th. LaViolette will be presenting first at 12 p.m. Pacific Standard Time, which is 3 p.m. Eastern Standard Time. In about 10 minutes here, 12 minutes, T-minus 12 minutes. So we're just getting it started up here so everyone can get a chance to join the stream and be ready for when we go live. Paul will be presenting from 3 for an hour presentation, followed by an hour Q&A, like standard we do here. And then we'll be followed with Mike McCulloch and Quantized Inertia. Mike McCulloch and Quantized Inertia will be at 2 p.m. and Pacific Time, which is 5 p.m. Eastern Standard Time. And Mike McCulloch is, you can find his website at quantizedinertia.com. And Mike has published over 21 journal papers on a new cosmological model for inertia called Quantized Inertia, which predicts galaxy rotation without using dark matter. His work proposes that the phenomenon called inertia is caused by relativistic horizons, making the quantum vacuum non-uniform in space, and this offers a new way to engineer thrust for any type of vehicle or spacecraft. It's called horizon engineering. This prediction the prediction is that we can use electrical conductors or nano-engineered materials to make synthetic horizons, dampening the quantum vacuum in a similar way to the Casimir effect and engineering thrust without propellant. In his presentation, Mike will discuss the theory of quantized inertia, then present evidence from galaxy rotation, and finally discuss his attempts to bring the theory out of the lab as thrust, which led to his design for a propulsion device called the Horizon Drive. And we're going to talk about some of the people that he's working with on this Horizon Drive project, and lots of questions for these guys coming up, man. This is going to be quite a day. I am super excited, as you should be all. Paul LaViolette, our first guest. I've known about Paul for a lot longer than I've heard about Mike. I think Mike McCulloch of his started really coming up on my radar back in just a couple years ago. But Paul LaViolette, of course, published that book, Secrets of Antigravity Propulsion, in 2008, right here. And that book really opened up a lot of doors on a lot of things. Talked about the B-2 stealth bomber with the Biefeld-Brown effect that is in the wings of it that create the lift from the leading wing edge. Some of the interesting technologies that that Tesla was working on and other stuff. But one of the coolest things was this Project Skyvault, and it's still like stuck with me as like probably the most interesting thing that I found in that book. How about you guys? What do you guys think of that? Anyone else in the? You guys can hear me in this chat here, right? So I can't. I mean, we got some people here joining with us. I think Tim Ventura is going to be here. He's going to be introducing the conference soon, and getting everyone in here once we're ready to go live. So let's tune over to our live chat. I'm going to share my screen with you guys all in the conference, so you guys can see what's going on here. The live chat. Bring you guys over there. We have 40 people, 12 likes. You guys can hear us okay? Why don't someone from the Zoom conference say something so we can make sure everyone in the audience can hear the Zoom call fine and that all the volume levels are good on my audio.
Sorry, Jeremy, it's Tim. How does that sound? You sound okay? Hear that okay?
I can hear you fine. So
I'm changing my screen sharing settings. That's in Zoom preferences if anybody else wants to. What it does on my system is it jumps into full screen mode, but since I'm recording, trying to manage the chat and all that stuff, it can get a little wonky. So
Yeah, perfect. Thank you for that. Yeah, I still have to set up a Patreon. Renee in the chat said something about a Patreon for my YouTube channel. I had one set up, and I don't know. I got to either go back and figure that out at some point, because I just have been neglecting it. But yeah, I think Tim, where can they donate money to your project and to help you out with what you're doing? Because I'm sure this is taking a lot of time out of your schedule, and I know my wife and kids are missing their dad on a Saturday to do these conferences. So
Oh, that's a good question. I don't have anything set up for that. So,
we should try to
yeah.
get you something set up, just something public and stuff, so people can donate to you directly for help to help you manage and run the conference and the guests and stuff. I know I've been trying. We've all been trying to help you out in the network with people that we know to get more guests. Network with people that I know and other people in the group know to get additional guests for the conferences, which are great, man. This is epic what we're doing. I feel you're bringing all this knowledge out of these places where people really don't. I mean, there's not a light. We're shining a light down some really dark areas, and I'm hoping that this is going to embolden a lot more people to join us in bringing this out in disclosure and bringing this out to the public.
Yeah. I'm going to go use the room here real quick. I'll be right back.
Yep, man. That's no worries, man. We're doing this, man. How's everyone doing tonight? I mean, today, whatever time it is, wherever you are. Some people are. It is tonight, so. Let's see. What can we play? I'm gonna play something right now so we can get pumped up for Paul LaViolette being first. Why don't I play one of my old videos here? Paul LaViolette. That one. Where's the microwave phase conjugation? Skyfold. Lightweight, because microwave beam propulsion cannot generate sufficient force to lift a heavy craft. Nevertheless, it is still a viable option for anti-gravity propulsion, even if it's used as a backup system to provide additional maneuverability to a craft. It's also useful for moving satellites from low Earth orbit to geostationary orbit without having to carry all that extra rocket fuel. This was the reason a small UK company called Satellite Propulsion Research Ltd was able to get funding to build a prototype EM drive in the first place. I can't believe that M drive has been out since like 2006, 2007. When did that first come out? That whole M drive thing, and then here we are 10 years later, and I'm really curious to ask Mike McCulloch what is going on with this M drive and currently what he can tell us about. I mean, some of these projects, I guess, are DARPA, and they might not be able to talk about everything, but I'm so curious. Like, this was 10 years ago, way more than 10 years ago. Now it's almost 15 years ago. So where has this technology gone? Why isn't it getting more funding? Is it getting more funding that we don't know about somewhere, or is it just considered pseudoscience by the mainstream community? And they're just like, I don't know. I'm just really curious about what is going on with this. I can't wait to ask more people their thoughts, because a lot of people in the scientific community really don't like this idea, and I'm sure Mike's going to talk all about that because he's.
Okay, Jeremy. So let me ask Paul. Let me stop your screen share real quick.
Yep.
Thanks. Okay, there we go. And Paul, are you with us? Can you hear me? Okay. Let's see if we.
Can you hear me?
Wonderful. You sound wonderful, sir.
Oh, I got a high class microphone here.
yeah. Actually, I have the same one. And these things are heavy too.
Exact same one. Okay.
Yeah, 10-pound microphone.
I got it Best Buy. Yeah.
Well, thank you for joining us. You are literally a legend in this area. So I'm going to do my best, and I'm going to hope that I don't completely blow my intro here. I always have anxiety when I read this, but and then after we get through that, then everything seems to go pretty smooth. Yeah, we've got just about a minute left, and so I'll wait for just about a minute. But yeah, Paul, I literally cannot tell you like how excited I am to have you speak today. And I'm not sure where Mark was, but Mark Sokol he's been pinging me all week about this. So
I'd like to thank you for having me on.
Oh yeah, absolutely.
It's a great thing you're doing to do these conferences.
Well, this just kind of happened. Actually, these conferences just kind of happened. Mark Sokol had approached me, I don't know, a couple of months ago. Jeremy Reese and him had done a couple of things online. And they said, well, why don't we start doing this on Zoom? And we were all burned out from COVID, right? We're all tired of being stuck inside. And so it just kind of started from there. Okay.
Do you want me to test my screen share?
Well, actually, let me do this. Not quite yet. Let me. I'm sorry. I do the controls also, so I've got tons of folks coming in, and then I've got recording in high def on the PC. So Paul, let me mute you out for just a moment. It's 12 noon, and I will do the intro, and then I will take it back over to you. And hopefully I won't goof this up. It keeps moving my mouse because I keep getting these people join the conference. Okay. So I will mute you and okay. So everyone is muted. Okay. Sorry, folks keep coming in. Okay, so I will start the intro in 3, 2, 1. Welcome to APEC. It's March 6th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us again on this call, along with everyone watching us on YouTube. We have a big session for you today. Dr. Paul LaViolette will be discussing the theory of subquantum kinetics and the Pais Navy gravity patents. And Dr. Mike McCulloch will discuss quantized inertia and the horizon drive. After that, Jeremiah Popp will be presenting on the hunt for field propulsion, and we'll be wrapping up the event with open discussion and ad hoc presentations. Just a couple of quick reminders. You can view conference replays, details, and speaker information on our website at altpropulsion.com. Please save your questions for the Q&A session after each presentation. Go ahead and type all of those questions into chat, and we will be going through those after each presenter finishes. And basically, I'll just be calling on folks, hopefully in the order that they go into chat. So let me start out by introducing our first guest. Dr. Paul LaViolette is a true legend in electrogravitics and frontier science, and the author of several formative books in the field, including Secrets of Antigravity Propulsion and Subquantum Kinetics, along with several other books and many physics papers. He has a BA in physics from Johns Hopkins, an MBA from the University of Chicago, and a PhD from Portland State University. He's also done consulting work in innovation for the Greek government and Fortune 500 companies, along with many other science and technology achievements. It is a true honor to have Paul join us today. So without any further ado, let's welcome him to today's call. And Paul, I'm going to unmute you now. There we go. Welcome, sir.
Thank you, Tim, for having me here.
Absolutely. And yeah, if you'd like to do the screen share, go right ahead. And
just to test out. Okay, let's see.
Screen,
screen.
You can get started at any time.
Share. Okay. Now I want to see this.
Oh, perfect.
I want to see the. Antigravity lecture. There it is. Go to the top. Okay.
And are you able to? Yeah, I was going to say, there we go. Let me mute myself out, sir, and go ahead whenever you're ready.
Okay. Hope everyone can see that fine. So this is on my websites, etheric.com and starburstfound.org. So we'll be talking about these sort of things pictured here. I'd like to start off with a quote from something that was said by William Tompkins in an interview. He wrote this book, Selected by Extraterrestrials, which is really revealing about what was going on in the classified world in aerospace. And he was working with Douglas Aircraft, designing ships of Star Trek size, actually. And he was saying we were building these in Utah and boosting them up into space. And in interview, one of his interviews in August 2017, he was talking about a quote from Navy Admiral, Secretary of the Navy, Admiral Forrestal. Let's see. Can everyone see that, or is it partly cut off by the pictures? I don't know if there's a way to get rid of the picture part. So every book in the libraries and the colleges, university, every book on the planet is misinformation. All over this planet, books are not telling the truth, whether it's medical, solar system, astronomy, or science. Every person on the planet has been given misinformation. So here are some things that I feel, some trash that needs to be emptied in modern physics. As you see, it's quite a collection. And also I put in there, added in Alcubierre drive, which I don't know how many are attached to that. It seems to be a favorite of physicists who have not yet left the space-time theory and sort of still sticking on to the old system of viewing things. Big Bang Theory, expanding universe, space-time, special relativity, all these should be thrown out. And in subquantum kinetics, I have replacements for all this stuff. General relativity, black holes, they don't exist. Wormholes wouldn't exist if black holes didn't exist. String theory really doesn't make any predictions. Quarks, the ether replaces that whole idea. Gluons, quantum mechanics, subquantum kinetics has a complete replacement for that. Quantum electrodynamics, wave particle dualism, You don't have a dualism any longer in subquantum kinetics. The idea of the collapse of the wave function, Copenhagen interpretation, dark matter, dark energy, second law of thermodynamics, energy conservation law, and Newton's third law. So we're actually living in an over unity universe, as you'll see shortly. And this is my theory. Subquantum kinetics was published in 1985 in International Journal of General Systems, and it was initially 3 papers, and they decided to make a special issue out of it, so it's just devoted to subquantum kinetics. And then in 1994, I published it as a book, Subquantum Kinetics. The first issue doesn't look like that. It looks like this. It was a lot thinner. It keeps going through editions. That's the 3rd edition, and the 4th edition is now in ebook form. You can purchase my books through etheric.com site. Subquantum Kinetics is only sold there, except through getting used books through Amazon. But I understand the paperback is going for over $100. So the ebook is a lot cheaper alternative for $30. And you get a lot more in it. So here's some of the salient points. I'll cover subquantum kinetics just briefly because it's sort of the framework which I've operated, which made possible my reverse engineering all these anti-gravity and gravity control technologies. So it's been in existence for over 36 years, has a sound conceptual basis. It was developed by applying systems concepts to physics, to microphysics. 14 of his predictions were subsequently verified. 11 papers about it have been published in refereed physics and astronomy journals. It is a unified field theory that acknowledges the reality of an ether. It is entirely consistent with Tesla's thinking, unifies physics with the life sciences and with esoteric thought. It appears to have very ancient roots. Even ties in with ancient Chinese concepts of yin-yang metaphysics. So if you look at conventional physics, it's kind of in its own box. Subquantum kinetics goes way out the box, so it greatly expands the range of phenomena which you can interpret and understand, anti-gravity being one of them. And you must admit, general relativity has trouble with that. So nature of the universe, everything changes and nothing remains still. So that was a sort of clip from Heraclitus. They have short clips of his philosophy that have been preserved. He was what you'd call a process philosopher, and the mainstream physics is based on the idea of structure, not process. You know, the idea of subatomic particles, and then you go a step lower, you've got quarks held together with gluons, sort of tinker toy models. With subquantum kinetics, it starts out with the idea of process, like what Heraclitus was talking about, flux. So this would be a postulating an ether, which is in a state of transmutation and transformation reaction, you could call it. And the ethers in the dotted circle, G, X, and Y, would be what are creating our universe, our physical universe. But they are being formed like G comes from A, which comes from A prime, and that's upstream. And then you have downstream, like X decays to Z, goes to Z prime. So you have this continual flux, and it's unidirectional. And this is where our feeling of time comes from, because we're at rest, sort of in this flux. We are caught here at the GXY nexus. And this flux goes through us and animates our universe. So time actually has a higher dimensional meaning, you know, that it's this ether flux, actually, if you want to come down to its origin. By the way, this is an open system view of the physical universe. So if the universe is GXY, you see there's an outside to the universe. And so current physics views that the universe is a closed system, and it doesn't, it's not based on the idea of this open universe. And when you go to the open universe concept, all sorts of things start making sense, and it allows for free energy and a lot of things. In fact, our whole galaxy is an over unity region of space. So these things are possible. You also can have under unity, where there's energy actually decays over time. Fortunately, that's way out in space, away from galaxies. That's why you have the redshift, cosmological redshift. So these are the reactions that go on. If you look here at the middle, G, X, and Y, and expand what's going on there, here you have, it's like a crossing of two ether reaction processes. They interact here, and it produces this XY loop. And then these products continue on out. So you got inputs, A and B inputs, and Z and omega output. In the process, you get this looping. And this is the simplest reaction system that can produce physically realistic particles, something that would resemble subatomic particles. It's based on the brusellator. The brusellator would be, if you just took out G, it went A directly to X, so it would have just two variables. But the brusellator does not produce solitons, sort of nucleated particle-like structures. Its space structures are unbounded, sort of. They go through a whole reaction volume. Here's an example of proton and electron. So here we're plotting the Y potential, phi Y, and this would be a positive charge. This electric field. And there's also a X complement to this, where X mirrors Y. And that's because Y and X are interlinked. So if Y goes up, X goes down. It's like yin yang idea. It's very good for visualizing what this happens. The X component of the electric field, which is not shown here, is linked to the G component. So you have a G well formed when you have a positive charged particle. For the electron, be just the opposite. Y would be low, and X would be high, and X would be causing G to be positive instead of negative. This would be antigravitic, whereas this is gravitic. The electron would actually be 2,000, have a wavelength 2,000 times greater than the proton. So the proton would be like a little needle lost in the haystack of the electron, if you wanted to look at it proportion-wise. Here is showing the bias would be the electric charge, that the whole pattern is biased upwards, whereas for electrons biased downwards, and that's what produces the particle's electric charge. But the, let me go back again. You see the characteristics are that it's a rounded center and it's got a wave-like going out, radially out, so wave pattern, which is Compton wavelength. So this is what I was theorizing initially in the early years, and then it's now been validated with computer simulation. So here's the model G, I call it. It's this model I've shown on earlier slides, we call it model G. And you could suggest other models if this, you find doesn't work as well as you'd like, but we're in the process of exploring it. We haven't even begun to scratch the surface. It's a nonlinear, non-equilibrium reaction diffusion system. And with such systems, you can have extreme complexity. Nonlinear systems by nature have high complexity. So it's just 5 reaction steps, and you've got 3 variables, G, X, and Y. So if you take the G, X, and Y, and you plot them, you write them out as partial differentials. So you're representing the 3 variables as partial differential equations. This is the reaction part. This is the diffusion part in each of the cases. And you can solve these as a system of equations on a laptop computer, actually. I was approached by somebody who was very interested in subquantum kinetics back in 2009. And he had background in computer simulation. And he went ahead and he actually simulated this on his laptop. And this is from his simulation in 1 dimension. And this is showing a nucleation of a neutron, because this is not in the bias state, it's just a Did the music come across? The music from the slide, did it come across at all?
No, I didn't hear any music.
Oh, okay. Well, it was Thus Spake Zarathustra. Because this is probably the most important phenomenon in the universe, was the emergence of matter. That's why we're here. And so if you can explain the emergence of a single particle, you explain everything ultimately, because it turns out that these have the tendency to multiply. Here you see the gravity field is has a wave pattern, and it's sort of mirroring the X field. This is the X. This is 1/10 plotted at 1/10 of its magnitude, because otherwise it wouldn't fit on the graph. So this shows how close it is to what's actually seen. This is the neutron, and this is this charge density of the neutron as seen by particle scattering experiments done around the year 2000, 2002, around that time, published. And you see that rounded core doesn't go to a spike like previously they had speculated. And it has this wave pattern, about Compton wavelength wave pattern that goes out. And here you can see the fringe wave pattern amplified better, because this plots as surface charge density instead of charge density. So the parts radially further out will be magnified as a result, and you can see the nature of the wave pattern going out. So this was a confirmation of our prediction, and no other theory has been able to predict this. Quark theory doesn't predict the nature of what they saw, but it was a confirmation, actually, because subquantum kinetics had predicted it well before they found it out. It's one of the 14 prediction confirmations. Here's how particles can multiply. Okay, the reason this second one comes into being is because there's a supercritical region. You see, there's a supercritical region around the first particle that allows it to stay stable. And then there's a it has to do with G. G is determines the criticality of the system. And I use concepts similarly applied to a nuclear reactor, critical, supercritical, subcritical. So where the particle is supercritical, so it allows it to be stable. But then as you go out, the wave reverses, it goes subcritical, and then further out goes supercritical. So this second particle emerges in a supercritical region near the first particle. So because the particle is there to begin with, it is able to greatly modify the probabilities of a new particle emerging. So, I mean, these come into being, they can come into being from 0 point fluctuations. It just takes a very long time to wait for each one to nucleate. But once one is formed, it can start producing daughter particles. So it's mother-daughter relation. And we now started, we have a group that's working on simulating this, and we've gone to two dimensions now, and this is in 2 dimensions. And if you plot, instead of color change, plot this along the z-axis as magnitude, this would be y magnitude. You see it sort of overshot there and came back down to its stable state. And you see the ring pattern around the core. And we're doing a lot of interesting stuff now with the simulations. This is 2 dissipative solitons. That's what we call these, dissipative solitons. In other words, neutrons, because they're neutral charge. Accelerating down opposing gravity potential gradients, so to make them collide. And this is what you find. So sort of like elastic billiard balls. And we've measured, this program is written by Brendan Derer, and with the Model G vertical motion group, we had a lot of input from people and doing all these simulations. We measured, he measured the, where the particle would be at different times as it comes, and it actually accelerates. And we found it actually accelerates down the gradient. So it in effect satisfies Newton's laws of motion as far as gravity goes. And it's a viable substitution for space-time and general relativity concepts. But it's much more in that it predicts, subquantum kinetics predicts the electrogravitic connection between X and G, between electricity and gravitation. So I don't know, I assume a lot of people, or most out there, have taken the red pill and gotten away from space-time. And so here we're talking about electrogravitics, which Einstein would have to throw up his hands. He found no way to unify electricity with gravitation. And this is from the work of Townsend Brown in the, as far back as the beginning of the 20th century. He was experimenting with electricity and finding an effect, gravitational effect. When you charge a dielectric that's a massive dielectric, so it has a lot of mass between the plates, that he gets a force on the dielectric towards the positive. And the graph here below would explain it in terms of subquantum kinetics, that negative particles are antigravitic and positive charged particles are gravitic. And between the two, you get a gradient which affects your mass and accelerates it. So ideally, this could accelerate forever. You know, you go up to light speed, eventually beyond. Now, with neutral matter, it turns out the electron is predicted to have a slightly smaller gravitational well, gravitational hill, I should say, than the proton's gravity well. And so as a result, there's a residual, and that's why we have that matter attracts matter. Matter produces a gravity well. This difference so minor that we're talking about maybe that when you actually separate the proton from its electron, you get the masking of the electron away from it, it may have a gravity well 1,000,000 times greater than when it was combined with the electron as neutral matter. So I want to talk briefly about the Earth, so have an idea of what gravity is. So here we're plotting gravity potential. And it's basically a G ether concentration well is formed. And why is that? It's because neutral matter is consuming geons continually. Because when you have a low G, it's because geons are being consumed more, like a proton. And it's you're dealing with open system, you get G coming in, but it's also going out. And the result is that the balance is that it's low value for neutral matter, and that's what creates the gravity well. Here it shows the reaction from G to X, but there's also a reverse reaction from X to G. And it's really this reverse reaction that determines the electrogravitic coupling. So if you have a positive particle, X will be negative, will be low, and that will force G to go low and create a supercritical region that stabilizes a particle and creates a gravitationally attractive region. The opposite would happen if X was high. If it was a negatively charged particle, G would go high too. And so you have a gravity hill. So here's terrestrial gravity. You have ether flux, G ether flux. It's continually flowing into the Earth because geons are being consumed. And this is what forms the G potential gradient. It's the interaction between the gradient and the flux. It produces a 1/r potential gradient. If you study, this is all in subquantum kinetics. But notice because the Earth is producing a gravity well, and let's see, yeah, here we are. That supposes the Earth, you have a G well in the Earth, that will produce a actual positive charge, but virtual positive charge, because now we're dealing here with neutral matter, but etherically, because there's a gravity well, you will have Y being high and X low. It's as if there's a positive charge in the core of the Earth as a result. So interestingly, this explains very nicely why the Earth is negatively charged on its surface. These are real negative charges that sort of agglomerate onto the surface of the Earth. They're attracted because they see a positive charge coming from the Earth. And of course, you have the positive charge ionosphere above the surface. So Earth's like a capacitor as a result. So this it gives a very interesting explanation of the Earth's charge at the same time. It's basically electrogravitics. Now, so here would be an example of the mech, the Searle disk, and then attempts were made to duplicate it. In my Secrets book, I suggest how it functions to reduce the gravitational attraction, that it's in effect spinning electrogravitically, causing a geon flux outward. And this sort of steers the downward flow of geons outward. So they never really pass through your spinning disk. And there's also a lot of UFOs, they say that they use something like Mercury to spin, create a vortical motion, and it would be sort of the same idea. So in 1985, I began writing a series of draft chapters for a book that was about gravity control. And this was the predecessor of my book, Secrets of Antigravity Propulsion, that was finally published in 2008. It became my bestseller. It's now gone through over 10 printings and over 30,000 copies sold. One chapter in this 1985 draft that I had set down gave ideas for the design and principle of operation of an anti-gravity craft that is almost identical to what the Navy scientist Paius patented. And this is over 30 years before he patented. And for my own reasons, I didn't put this material into my book, I guess because it was my own concepts. It wasn't something that was proven yet. And I somehow felt it was sacred. It was beautiful, and I wasn't ready to put it out yet. And we'll talk a little about this idea first, and because it will help us understand better the Paius patents, which are written in using parts establishment physics concepts, but it ends up being a mumbo jumbo in places. So this will help hopefully understand what Paius was talking about. And it may, I believe that actually Paius patent, even though he patented it 2017, 18, the actual technology was developed probably in the late 50s. It goes back to Brown and Bonson's work. I wasn't aware of any of it, what was going on in the secret program, but I was just reasoning based on subquantum kinetics, and I had just gotten a copy of Electrogravitic systems. I requested a copy from Wright Patterson, and they sent me the study, and we made many photocopies, and I was giving them out to people, and then Tom Malone suggested, why don't we publish this, a self-published book, and it was eventually published along with paper on the B-2 bomber I'd written. It's called Electrogravitic Systems. So all that is now absorbed in my book, Secrets of Antigravity Propulsion. So this is chapter 5 of this draft, the manipulation of gravity, I called it. It was written in 1985 on my IBM and dot matrix printer. You can see, if you expand that, you'll see it's dot matrix printer back then in 85. So 1985 is the same year that I published my theory, general systems, and electrogravitic systems studies I obtained that same year, 1985. And the printing of the publication of the general systems articles were still, they hadn't gone to ink yet, and I was able to get in mention about electrogravitic systems. I just gotten it, and that here was proof of what subquantum kinetics was talking about. Plus, before that, I had Brown's work. I guess I discovered about Brown's research at the beginning of 85. I'd already submitted the paper. It was being reviewed, the papers. And I was a little uneasy, the fact that I was predicting that electrons are antigravitic and protons are gravitic. So you have polarity to gravity. Nobody else had predicted that. And I was wondering, could I be wrong? And when I discovered Brown's work, I was very relieved that here is evidence, experimental evidence that it's right. So, so this is what I had at that time when I wrote that paper. And here's some work by Brown. Show you, he had these thrusters that would levitate. And This one is from his 1965 patent. It's a dielectric, and he's got a little disc here, which is, he calls it a half wave or quarter wave disc. He's energizing this with microwave frequencies. So he doesn't explain the whole thing, but you can kind of figure out. In the same here with this device that was lifting, he was not only putting in a DC charge, but he was putting AC across this. And so you have, on the one hand, the unbalanced forces would cause this to lift because the negative electrode is smaller than the positive electrode. So your forces are more concentrated here than they are here. But more importantly, by pulsing this with AC so that it's non-reversing AC, if you can picture that, it's DC pulses in effect. Because the dielectric is polarized, let's say it's polarized charge towards the negative, and then so when the AC wave goes positive, it will instead add to the previous negative polarization to go to 0. But when it goes negative, it will in effect double that and go to twice the polarization voltage. So this was a technique, I believe he discovered, that he could get greater lift. And he talks, well, Bonson talked more about it. But here, by doing this, you could use a tank circuit to energize the capacitor, your capacitor to, this is one way of doing it. Or, you know, you're at, be at resonance here. Or you use a microwave oscillator on your negative electrode. Now here, this is out of my book, Secrets of Antigravity Propulsion. And I just want to point out that Bonson was talking about this AC pulsing with DC, and it would establish a resonant stationary field between electrodes. He hypothesized this electrostatic stationary wave would somehow store energy of the applied, and it's, I can't see it because it's blocked out, to produce an ether-like energy reservoir residing in the space immediately around the test device. He felt that this resonant condition magnified, I guess, the latent energy in the stationary field to be used with a minimum of power consumption. So here he uses the idea of ether-like energy reservoir around the craft. So basically he's pumping the ether, creating a soliton effect around the craft. Soliton meaning a field phenomenon, like particle in the ether, the field pattern of the particle, you call it soliton, but you could also refer to a soliton, the potential, the gravity potential you'd be creating around your craft. And here he talks a little about it, about how he is adding AC to the DC. This is patent 1964. He was actually, he died right after his patent came out in an airplane crash, which sounds very strange to me. Doesn't seem like an accident to me, but after he died, his patent was given to it was assigned to a company which I couldn't find out the name of the company. His family members were very tight-lipped about anything connected with that. But I think that these concepts were used as the input to the UFO design that Paius eventually patented. But the actual work was begun way back then. So he says also that alternating potential has some effect upon the degree and efficiency of ionization of the gaseous medium which the apparatus operates. And he believes that this is beneficial to have this ionization, and he's able to establish a resonance with the air molecules around the craft. And notice here that the force increases by the 2.6 power voltage. So he took it up to 150 kilovolts. He was getting 100 grams thrust. You go to 1.5 megavolts, you get up to 40 kilograms thrust. So you're talking about enormous thrust, and military would have been very interested in this. Now this is from my paper, and you see the applying basically Bonson's and Brown's ideas. At that time, I wasn't really aware of Bonson's work or all of Brown's work. All I had to go on was Burbage's article and the Electrogravitic systems paper and a few other papers, Kisselman. But with electrogravitics, with the subquantum kinetics, I was able to come up with this idea of pulsing, that you'd be able to create potentials far exceeding what you pulse with in the immediate vicinity of the craft. So you'd be creating a gravity hill below with the negative charge side of the craft and a gravity well above the craft, and that would tend to lift the craft. So here I talk a little about it. So how it is that pulsing is able to affect the magnitude of the induced gravity potential. I was using psi g back then, and I changed to phi g because psi g, you could confuse it with notation from quantum mechanics. So, but it really means potential here. How is it able to affect the magnitude of the induced gravity potential field may be understood as follows. By conducting a thought experiment visualizing the ether diffusion processes, may be seen that there is a certain memory effect involved where the phi x, phi y, and phi g profiles established by any one given pulse linger long enough that they may be added to by the profiles established by the succeeding pulse. In this way, it should be possible to build up field gradients that are much steeper than the field gradient developed by a steady voltage potential. These artificially produced field gradients would not necessarily obey an inverse square law. Rather, they would vary with distance much more rapidly, their steepness increasing with increasing pulsation frequency. Or if you don't want to talk about gradients, talk about potentials. So the G on a hill and G on well that you're establishing, the magnitude of those potentials outside the craft would increase according to how fast you pulsed. So the faster you pulse, the greater the potentials. So I was suggesting try pulsing at several thousand cycles per second, and maybe you could overcome the pull of gravity. But I was very low-balling, as you see what is suggested in the Paius patent. They're going to megahertz. Okay, if not more. So here I give more details. On the other hand, when the gravity gradient is being dissolved, the profile will relax away from the steady state shape, establishing an increasingly shallow gradient. For any diffusion phenomenon, the diffusion flow is always directly proportional to the magnitude of the potential gradient. Thus, in view of the above, the G diffusion rate will always be greater during the period of charge application and less during the period of charge neutralization. So by means of such repetitive pulsation, large ether potentials may be built up in the immediate vicinity of the craft's hull, potentials that deviate significantly from the environmental values. Moreover, this may be accomplished using relatively small initial charge investment. So I mean, let's say you're using megavolt charge pulses. You might be doing, you know, thousands of megavolts or more in terms of the ether potentials that you're generating outside the craft. It says, note that these built-up fields are not sustained by any material counterpart. That is, there's no charged particles acting as sinks and sources for these induced ether flows. In effect, the ether itself becomes charged. You'll see in the Paius patent how they talk about charging space-time or polarizing space-time. That's what they're talking about. But with the ether theory, it's more understandable. The macroscopic inhomogeneous steady state that is established might be likened to a giant dissipative space structure. Okay, that's concepts from Prigogine. He refers to these ether patterns, or he would speak in terms of chemical potentials, chemical concentration patterns. So we're using the idea of fields are concentration patterns in the ether. And so you could refer to them as solitons, actually. And this effect that I'm talking about, the lingo that's used in the black world is soliton phenomenon. It slips my mind, but they use the idea of an induced soliton phenomenon. That's a very important concept in their work. And this is what the Paius patent is doing. Then let's say you have high voltage discharges, here voltage, and these are negative pulses, and they're generating gravity pulses, which create a gravity flux and force in this direction. These are gradient-driven scalar longitudinal electrogravitic waves, basically. So up here you plot electric, and down here gravitational potential. So you not only have an X-ethron flux, but a G-ethron flux. And virtual anti-mass induction. Tesla was doing this in his work with the non-reversing pulses work that he did. This is not the AC work. This is, these are DC pulses. And he was getting actual forces from his DC pulses with very sharp rise time in the forefront of the pulse. If you did this with solid state devices, they call these oscillators or impact diodes. Examples, they're solid state devices that can operate from frequencies 300 to 400 gigahertz, power outputs of up to 3 kilowatts. Now people like us are not able to get a hold of these. These are restricted, restricted to normal research, only for military use. So most you can get is something like around what you get from a microwave oven, which is very small, 100 watts or something. And these waves are superluminal, and I did experiments with Guy Belansky in 2005 and 2006, and it's written up in my book about that. This Guy Belansky just passed away a few years ago. Brilliant guy. And we were radiating pulses, electric charge pulses, called it Coulomb waves, from his electrode, and we measured the delay time to go from the electrode to different points across his laboratory. We had an oscilloscope up here. And we found that they started off superluminally at 6.5 C, and as it dropped away from as it left the electrode, it would drop down with an inverse function, eventually approach, but not quite, the sea speed, still was superluminal after 350 centimeters. So it actually fit this model perfectly as being due to this, that the dome was generating an ether wind, and the scalar longitudinal Coulomb wave was riding, sort of surfing this wind. And that's why it was superluminal. And the reason why the velocity distance away from the electrode is because the ether wind would fan out from in all directions, and you get a 1/r decline. So it fit the model fit perfectly the data. So this was evidence of breaking special relativity. Now I want to talk about my next development back in '85, which is what I call the Aquarian monopolar elevator. So I realized that it would be better if you could have the outside of the craft the same charge. So the ideal one would be the one on the left, be all negative charge, both above and below. And you design it like a capacitor. So you have two hulls. Now, if you notice, this is getting very much like the Navy patent. You get your lift by pulsing the lower half of your craft faster than the upper half. So you're creating a greater G hill below the craft than you do above the craft, and therefore it lifts the craft. You could also do it this way, have positive charges, but the thing is that positive charge craft is going to be attracted to the Earth. It's going to be viewed as a mass there. Whereas this one's going to be viewed as a feather, sort of. It's gravitationally repulsive to the Earth's field. So not only you get from the fact there's a difference that's more gravity repulsive on the bottom than the top, but the whole craft itself will be generally gravitationally repulsive. So lacking a workable theory to explain electrovitics, Brown did not take his theory the next step to produce a monopolar charged UFO-like craft capable of extreme acceleration without inertial consequence for its passengers. The subquantum kinetics ether theory was developed and began in 1985, pointed a way to how this may be done. So here is the picture, and I'll read passages here. Consider the first case where the plates are minus, plus, minus. I did it this way to have it like a capacitor, sort of, you know. But if you don't really need this second negative plate, you can just go plus, minus. So the inside of the craft would be plus and the outside minus. And it'd be like in a Faraday cage. Whereas in the first version, as I showed earlier, you'd have a big electric field gradient across you, and it would not be safe unless you were inside a Faraday cage. So this is safe because it's automatically going to be a Faraday cage. So reading this, in the case considered here, the polarity outside the craft would be negative. Thus, by pulsing the plates with high voltage DC, the gravity potential in the vicinity of the outer two negative electrodes would be made to rise to a positive value. Since gravity potential is correlated with pulsation frequency, by pulsing the craft's lower hull more rapidly than its upper hull, the gravity potential would be made more positive below the craft. In this way, 5G gradient would be established, which would tend to lift the entire vehicle. Thus, even though the upper and lower hulls both generate G potential hills, the gradients so produced would simulate that produced by a 5G attractive gravity mass that was centered directly above the craft. The beauty of the monopolar design is that in order to establish a vertical gradient across the craft, the upper and lower hulls need not be charged to different voltages, as is done with the bipolar design, which was the first one I showed. Rather, the hulls need only be pulsed at different frequencies. Thus, by supplying the same voltage to both upper and lower hull capacitors, a net zero potential difference would be maintained between the craft's upper and lower surfaces. Of course, if they were not pulsing at the same frequencies, phasing in and out, there would be some potential differences. But the main thing is that the soliton outside the craft, the potentials outside the craft, would be far greater. So, and those would not be able to short out. So also reading down here, this monopolar design has the advantage that the degree of lift may be controlled simply by differentially changing the excitation frequency as applied to the two hulls. So if you want a rapid descent, the craft may be pulsing, you would pulse the upper hull more rapidly than the lower hull. And this would create a virtually attractive mass immediately below the craft, or the opposite for lift. And then if you're hovering, your pulsing frequencies would sort of converge to about the same. So what you're hearing when you listen to a UFO is the beat frequency between the upper and lower hull, pulsing of the hulls. They may be pulsing at megahertz frequencies, but what you're hearing is the difference, the tonal difference. So when it's hovering, they're almost the same with a very low vibration sound. And then when they takes off, you'd be raising the pitch of the lower hull progressively, and it would shoot out in space. And you could get extreme speeds by, you could eliminate entirely the pulsing on one side in, let's say, the upper surface, and you'd suddenly shoot out at many Gs. I guess I'm running over a little. That's the first hour has passed. So I'll have to cut into a little of the question period. So why you don't have inertial characteristics is because you're inside a bubble of gravity potential. So you have no knowledge of the outside world. For you, your world is that you're being attracted to your floor. Let's say it's the positive hull of the inside of the craft, positively charged. So that's your reference. And your craft could go lickety split in all sorts of different directions, and you wouldn't know it. Because the Earth's gravity field doesn't pass through your craft, it goes around. Gravity in this model is geon flux. And it's being actually, the geons are deflected, that flow is deflected around the craft by the G hills. So it doesn't really penetrate. They actually repel the geons. So here we have sort of just what I was saying for the different modes: acceleration, deceleration, and hovering. Beat frequency progressively increases in pitch when you accelerate, progressively decreases in pitch when you decelerate, and produces very low pitch when you're hovering. So this shows, in the case where you had plus on the inside and minus on the outside, how would be your gravity potentials? To be very high G potential on the upper and even higher on the lower surface, creating an upward force. And these would be kind of waves you'd be applying. That these waves actually pump G etherons. So they act as G etheron pumps. You can think of it in hydrodynamic terms. You're actually pumping geons to where you want them. So this is that the negative potential outside is preferable because the craft becomes mass repelling. Interesting, the flow of time would speed up inside your craft because, as you know, in physics, when you go into a gravity well, it's called a gravitational time dilation. Time would slow down. Well, the opposite would happen when you're manipulating G and making it very high positive potential instead of negative. The other thing is occupants could become invisible to outside observers, a mild Philadelphia experiment effect. That could possibly cause partial dematerialization of particles of people and whatever inside the craft, so that light could pass through it. And the other thing is light might be bent, well, would be bent around the craft gravitationally if it was a very strong field. So this could explain craft invisibility. So when you do see craft sighting, the actual craft could be much larger than the actual visible spot. It's just that you don't see the rest of it because it's invisible. This could also affect the consciousness of the people piloting this craft. This I just want to show, we did a simulation where apply a gravity hill to a particle and you see what happens. There's the particle, it nucleates, bam, dematerializes. So this would be a Philadelphia experiment type of thing, you know, in the extreme. Now, in the Paius patents, this is the high frequency gravity wave generator. This came after this next patent here. This was the preceding patent. See, this is a double hull, and he's got he's injecting microwaves here with microwave transmitters in a resonant aspect, and he is affecting, he calls it polarizing space-time outside his craft. In other words, he's generating a field-induced soliton effect, which is the lingo they use. So here it says, this is from the patent. Microwave emitters create high-frequency electromagnetic waves throughout the entire resonant cavity shroud, causing outer resonant cavity wall or a portion of the resonant cavity wall to vibrate and create a polarized vacuum outside the outer resonant cavity. Yeah, he calls vacuum, I guess he's afraid of using the word ether. They all use the word ether in the black world. But this is US Patent Office, so that's the way they use it. And that's part of the problem of the patent. It uses standard physics terms, which make nonsense out of the whole thing. So a lot of people have trouble understanding. I was told by somebody who was interviewing different physicists on would they be able to explain a Paius patent. Not a single one of them was able to explain whether it was real or not. It just didn't make sense to them. But it all makes sense with subquantum kinetics. This other thing we see here, an operation is preferred embodiment of the craft may be powered to move in different directions by causing different sections of the resonant cavity shroud to vibrate. See, exactly what I was saying in '85. This is 30 years before this ever came out, okay? So they're talking about a monopolar elevator here. For instance, to move upwards, the top portion, top edge of the portion and top trailing edge portion of the resonant cavity shroud is vibrated, then causing the polarized vacuum field 60 to move the craft upward. Okay. Here, they say electromagnetic field generator responsible for the, it's sort of blocked out here, I can't see, mass diminution effect would generate a repulsive energy field while in the Earth's atmosphere. thereby repelling air molecules in its field path of ascent. I totally agree with what they're saying. Consequently, in orbital space, by local vacuum polarization, quantum fluctuations, modification, coherence, and that I call quantum physics mumbo jumbo. Doesn't make sense. But basically, it's what I was talking about in terms of the ether. You're creating a soliton, a field soliton around the craft. A repulsive effect would be created. Recall the negative pressure of the polarized vacuum would permit swift movement of the craft. This is his way of trying to explain it. Now, no wonder the people in the patent office didn't believe that this was possible, and they only approved the patent after some high-level guy with the Navy got on the phone with them and said, well, we've got these things operating. I don't know if they made the guys patent office sign non-disclosure agreements and showed him some videos or what, but they finally agreed, okay, well, if you sign your name to it, that it works and you have these things operating, then we're obligated to issue the patent, because their authority is patent doesn't have to obey the laws of physics to be issued. It has to be something new and have application. So that's exactly this apparently fits that. And I just say here, the term used in black projects is field-induced soliton phenomenon for this effect. And this is the referencing to building up this high gravitational potential, or what they call charging the vacuum. So inertial mass is reduced. Here it's talking about reducing inertial mass. Here they use non-equilibrium thermodynamics mumbo jumbo. Far from thermodynamic equilibrium, analogous with symmetry breaking. What they're talking about is the field-induced soliton phenomenon. This is, I work with this stuff in subquantum kinetics. They have their own explanation for the inertial mass reduction. The truth is that they're isolated from the outside world inertially. That's why they don't feel any inertial effects. So I believe this is the true explanation. And here's from the claims of the patent, what they claim, if you want to read through. Maybe a lot of you have downloaded the patent, so you can take a look at these. And here's from the other patent. Here they have sonic resonators to produce the waves. These are gravity wave generators using sonics. So here they're talking about generating two frequencies, one with these microwave emitters, and then they have these other piezoelectric transducers here generating gravity waves, and they're spinning. This whole thing is greatly out of proportion. These might be very small devices that they're spinning inside the craft. They talk about using pebble bed reactor, but that's very old technology, U-238. They're probably burning water. So we talk about the Navy's gravity field generator, and the Paklanov gravity impulse beam essentially accomplishes the same as what the Navy is patenting, but in a different way. If you're familiar with Paklanov's beam, he discharges a few million volts through a superconducting electrode, cathode, and the pulse electric discharge goes to the anode and stops. And there's a very strong magnetic field. He's got superconducting coil here, generating a very strong magnetic field to confine the discharge, and he has another one here around. And as a result, even though the electron discharge stops, the gravity wave that's associated with those electrons, which is repulsive, because their electrons have a gravity repulsive wave associated with them, continues, and it keeps going. And he was able to cause pendulum to kick. And with a very high version that was working at 10 million volts, they were able to put 4-inch holes through concrete blocks and dent 1-inch thick steel plate. So that's now in a secure facility in Moscow. So here's the Navy's version. PZT crystals embedded in aluminum matrix composite shell. So this would be PZT crystals embedded in aluminum matrix. And then they rotate, the motor rotates this whole thing. So, and they charge this whole thing to millions of volts. So why would they do that? Why would they rotate it? Because what happens if you got a charged sphere rotating, generate a magnetic field, right? So the magnetic field is going to be collimating what's coming off of here. And what it does is that instead of the gravity, these are they're pulsating this piezoelectric frequency. Piezoelectric crystals are being pulsated with frequency, and they're generating electrogravitic waves. It's negative charge here, so they're repulsive, and they're radiating out waves. If they didn't rotate it, they go out in all directions, but by rotating it, they collimate it, and it goes out along the axis, so they can send this thousands of miles out like a tractor beam that way. Down here, they mention about cobalt 57 or iron 57 being used in the shell to create ionization. I know there seems a lot of mumbo jumbo here, but I think what they're trying to do is ionize the air around the shell. So not just the high potential, but they boost the ionization with isotopes. They talk about this epoxy ceramic that they would fabricate with the PZT powder, aluminum powder, and epoxy with some layering approach. And they're claiming immense permittivities, 10 to the 18th. I mean, good God. I mean, unbelievable high capacity, K factors. That's the K factor there. It says here, lead zirconate titanate, PZT, which has been polarized in order to exhibit very strong piezoelectric properties. So here they're talking about polarizing this so that this creates your unidirectional pulsations. It's not AC, it's DC pulses. So figure 2 pi square meter piezoelectric shell, fits 1 meter radius, charged with 300,000 coulombs, spinning at 30,000 RPM and vibrating radially at that frequency. So plugging this stuff in, this would be a Peltier belt, sort of like a Van de Graaff generator. They have their pebble bed reactor here, and they're basically charging this to very high voltage. This needle is there to help ionize the air. And they're pumping the ether out to create these waves. And by the way, I looked up an article about PZT epoxy composites. You can make this in your garage if you get the right components. However, they were able to fabricate only with K factors of a little over 400. So the Navy is apparently light years ahead of the rest of us out here in the real world as far as what they can do with capacitance. And here's from the claim section of that. And since we're short of time, I won't read it. And my feeling is they're using something like Randall Mills sun cell for generating power for those things. This burns water. or hydrogen, whatever you want to say. The hydrogen is induced to go down into the hydrino state with catalysts, potassium and whatever other catalysts, and generates enormous power. He claims a megawatt or so power. So that would be, I feel, a lot safer to burn water than to have U-238 up in the air. So I think that finishes, and here's my websites. We went over quite a bit, huh? 20 minutes over.
Paul, let me thank you so much for that presentation. That was absolutely amazing. So let me do this. Let me mute you really quick. And I've got everybody muted out. I am going to go into, let me see, let me stop your, oops, let me stop your sharing. Yep, I'm going to gallery mode. Everyone, let's give an enormous hand for Paul LaViolette. Absolutely deserves it. That was a remarkable presentation. Thank you so much, sir. Thank you so much. Okay, and
smash it.
Okay, I'm going to unmute you now. And who wants to go first in terms of questions? We are in the question and answer session now. And I will put it back on speaker mode. Okay, and Paul, we can hear you again. Let me see.
Yeah, if they need me to show anything from the slides.
Yeah, well, let me see. Erica said Jeremy wanted to ask some questions. Jeremy?
Yes, can you hear me?
Oops, yeah, there you go. Sorry, Jeremy, hit unmute again.
Hey, so, oh, there we go. All right there. Yeah, we have a live audience, 143 people watching, so out there. So this is cool. This is one of our best ones yet, man. Thank you so much for an excellent presentation, Paul. I have your book right here. Let me get my video on here too, so I can see. I have your book right here. I'm particularly liked chapters. The chapters on the microwave phase conjugation and what was it? Chapters
Project Skyvault.
Yeah, Project 5, 6, and 7 and 8. Oh, 8 and 8. Sorry. Yeah, and the microwave phase conjugation and Project Skyvault. And it's unfortunate you even went over, but you didn't even have time to get to too much of that in detail on too much of that stuff. Because I've been researching a lot of stuff on phase conjugate mirrors. And barium titanate crystals and how phase conjugation works and barium titanate crystals and four-wave mixing and some of these other schemes that you had mentioned or talked about in that book. And I was curious where you had come across that awesome information.
For this Skyvault?
Yeah.
I was at Bob Brown's UFO conference and presenting about actually a different topic about Earth changes. And a fellow approached me after the conference and said he'd like to be in touch and gave me his email address and phone number and so on. So after the conference, after I went home, I contacted him, and apparently his boss once worked on that project and sort of spilled some of the beans to him. And that's how he knew about it. And he passed all of what he had on to me. He also got his boss to put him in touch with a fellow who was still working on the project at that time. And he got had few letter exchanges with that fellow. And taking all their information that he passed on to me, I was able to sort of reverse engineer the whole project and use his phase conjugation at microwave levels. There's a lot of articles on phase conjugation used for optics, you know, but even Scientific American talks about that. But there was like a blackout, news blackout on microwave use of phase conjugation. All that was done by the military. You found one patent on it by Hughes Aircraft. Hughes was one of the main developers of all that stuff. And they were, of course, working in antigravity. So that's how I got tipped off about it.
Interesting. I had another question about the models. You had mentioned that you had an assistant or someone you were another scientist you were working with named Brendan. I didn't catch his last name. The one that had built those models for you.
We have a group. It's called the Model G Vortical Motion Group. Brendan might be attending. He may be one of the attendees here.
Oh, and do you have any information that you could share on how other people could learn about that, Paul?
Yeah, we're looking for other people who have experience in computer modeling. We have a Facebook page, and you could send an email to me, and I could put you in touch with Brendan. So we meet every Sunday for an hour using Zoom, and doing a lot of interesting things. We're trying to simulate the vortical motion of the particle to hopefully have a model of spin. So that would be a great step forward if we could show that.
And if I could jump in really quick, I'm sorry. Your email is ethericgate@gmail.com. I'm going to paste that in chat too. But so for anybody on YouTube, it's ethericgate, ETHERIC, ethericgate@gmail.com. My apologies. Okay, Jeremy, I'm sorry. Go ahead, sir.
Yeah, so I'm super interested in your modeling group. I want to learn. I have a couple people who are computer scientists and work with computer modeling and stuff. And we were working with some of that Wolframs, the hypergraphs and stuff recently. And I think that some of those people would be interested in your model because you showed briefly it was a graph model and it was an iterating function or a recursive function, and very similar to what Wolfram posits for what he would expect to be the generating source code of the universe. So I would certainly like to try that image and that graphic that you came up with and I'm struggling to wrap my head around what the primes mean, and the G and the Y and the X and all that. So I'd like to learn more about that and see in computer modeling.
Yeah, Wolfram he put out some papers where he was saying that the future of physics would be modeling, and that it's possible to model a universe basically using computer modeling to hopefully model physical phenomena like particles, so on. I don't know if he actually mentioned particles, but he's basically, what he was saying is the approach that we've been using. I started doing this back in the 70s. He published his paper around 2000 or so. And we actually used his program Mathematica as the platform to do our initial simulations in 2010. Now we're using other programs.
It's powerful software.
Yeah, maybe if people with Wolfram, with his company are interested, they're welcome too. This is amazing effort to move forward. It's very exciting.
Okay. Now let me go next to Marco. Marco, this was actually a few minutes ago now. Marco, are you still there? Yeah.
Yes.
Okay. Go ahead, sir.
Yes, sorry for my pronunciation. You said that the thrust that produces the Biffid-Brown effect is of gravitational origin, but both NASA and other scientists have tried to reproduce this effect in a vacuum, but without any results. So if this thrust is a gravitational pulse, why does an asymmetric capacitor not produce any force in the vacuum? Thanks.
Well, we have Brown's work. He did his experiments in a vacuum, and he was getting thrust, pinwheel sort of thing going around. Brown's experiments have been duplicated by Cornell and published in referee journals, so it pretty well establishes that it's real. They violate Newton's third law, He mentions that in the article. So doesn't mean just because people fail in the experiment that it doesn't work the way Brown was talking about.
Let me go next to Michael Boyd, who has some questions. And thank you. I should apologize for jumping around. We've got a lot of folks on the call today. So, but Michael, sir.
Hello. Paul, I'm Michael Boyd, and my curiosity is about space-time metric engineering, and it sounds like you're using the word ether and vacuum energy interchangeably. Is that true?
Yeah, well, instead of a space-time concept, which I feel has been disproven, it's better to talk in terms of ether. Take the red pill instead of the blue pill.
So you're saying ether and vacuum energy are not the same phenomena?
Well, they're differently construed. First you have to define what you mean by vacuum energy, and you mean
let me give a shot at vacuum energy.
0-point fluctuations, is that what you're talking about?
0-point fluctuation, the virtual pairs.
Actually, in subquantum kinetics, the energy of what you call it, you have to use a different word from energy because you're dealing at subquantum level, where energy is a quantum phenomenon. You have the subquantum flux, and you have tremendous action, if you want to call it, going on, transmuting the ether, and that's what sustains our physical universe. The actual pulsations that emerge that we would call 0-point energy, they're little fluctuations of the ether. They're also predicted to be there, but not in the same way that physics says. Whereas physics has entire quantum size fluctuations of like equal in mass to a particle, going both particle and antiparticle, and then suddenly disappearing. In subquantum kinetics, that is a single fluctuation. That's not with a negative aspect. It's real. It's like a virtual, like electric. Think of electric noise in the ether, and most of them are below the level that would nucleate a particle. They're so small. But if you wait long enough, you get a very large one. And if the ether is fertile in that region, in other words, there's a G well or low G potential there, it will nucleate a particle.
Okay, would you consider yourself knowledgeable about semiconductor physics?
Not that much.
Do you understand?
I'm not in electrical engineering that much,
Okay, would you understand the concept of what's called an energy band gap in the semiconductor?
Okay, somewhat, yeah.
Would you consider the ether to have a band gap like a semiconductor?
Okay, I guess I don't know well enough the concept to be able to answer the question. Band gap, so energy doesn't, that it needs past a certain threshold in order to have an effect? Is that what you're talking about?
Yeah, well, it's sort of like in electrons, you would think of like the valence band versus the conduction band electron. So in the valence band, the electron doesn't, it's not free. But when you go to the conduction band, for example, like in a material like a metal, it's called a free electron. So you can like see the little shininess on the surface of the metal because the electrons are free. They're not connected. They're not bound to an atom. So, and the change in the energy between the valence band and the conduction band, that's called the band gap. And every material has a band gap. For example, silicon has a 1.1 EV band gap, and carbon has a 5.5 EV band gap.
We haven't developed subquantum kinetics to the point of applying to material science like that. That's something hopefully people will go into the framework of the ether physics of subquantum kinetics and then start applying to these other areas. we need people to get involved in it, really.
Yeah. So let me go next to Pablo. And Pablo, are you there, sir?
Yes. Yes.
Yeah. And can you start your video, Pablo, if possible?
Do you hear me?
Do we have any questions relating to the patents, the Paius patents at all, or these are all on other topics?
Yes. Do you think that the Pais patents work if they are compatible with the subquantum kinetics model?
Yeah, that's what I was trying to show you with the paper I wrote in 1985. I actually anticipated what they're doing 30 years before they published their patent. And it's all based on Brown and Bonson's work. I certainly believe that they do what they say. And that's probably what we're seeing. A lot of these UFOs, like what was it called? From the gun camera pictures the Navy released, those could be ours, you know.
Okay, I'm sorry. I'm meeting Pablo's getting some background noise also. So, and Pablo had also wanted to know more about your website. And again, I can put etheric Stargate, I believe that's, yeah, etheric.com. Sorry, and I will paste that into chat. But again, anybody listening, it's etheric.com. And Jonathan Lane had a question about the patents also. Sir?
Yeah, so I've got a sort of a two-part question. The first part is related to the patents. So when it comes to the way that the craft are supposed to produce lift, how is this supposed to work outside of a planetary gravity field, or would it be limited to repelling the sun's gravitational field, which at 1 AU is only about 6 milliGs?
No, it would work everywhere. Earth's atmosphere, outside the Earth's atmosphere, out in outer space away from the sun, because you're generating your own gravity field around your craft.
All right. And my other question was about the mechanism for the way the inertial isolation works. I know we've got Mike McCulloch on the call with us, and I've been following his work on quantized inertia, and the way you're describing the inertial isolation from the outside world sounds a lot like a Rindler horizon from his work. So do you think those are the same concept, or is there something else going on?
Yeah, well, it'd be good to interface with him and find out if there's a connection. Yeah, I don't know that framework that you're talking about, but basically gravity, you're not affected by the gravity outside your craft, like the Earth's gravity field, the sun's gravity field, because those are all geon fluxes are involved, and you're repelling those geons. They don't flow through the craft, they flow around it. So they don't affect the craft at all. All that you have as your basis is the positive gravitationally attractive floor and ceiling of your craft. That's your reference point.
Okay. That covers it. Thank you.
Thank you, Jonathan. Okay, so I had one more from Pablo, and he had asked me to ask this for him because again, he's having some background noise. He's wondering if there's a simple experiment that's kind of, I guess, a recommended experiment to kind of prove the subquantum kinetics model for generating artificial gravitational effects. And so I think what he's kind of shooting for is maybe something that people could try and construct on their own. Wouldn't necessarily fly or lift, right? But enough to kind of demonstrate an effect and help prove the model, so to speak.
Well, like Brown's work, I consider as the experimental evidence that supports that. And I cited his work, Brown's work, in my first publication of subquantum kinetics. That here is what subquantum kinetics was saying for gravity polarity being associated with electric charge polarity, electron versus proton, and that supports this. So here's experimental evidence.
Oh, wonderful. Thank you. Let me go back to Jeremy Reese. And again, Paul, I hope I'm not jumping around too fast. Are you doing okay so far?
Who, me?
Yeah. I know I'm throwing a lot of different folks at you. So
Yeah, no, that's okay.
Oh, okay. Okay. Let me go back to Jeremy Reese then, sir.
Hey, Paul. I wanted to ask another question about the Pais patents and some of the physics that's going on there, according to your model, and then some of the, again, physics language that I've run into in my research into how this stuff kind of potentially works. Have you ever heard of a polariton or polariton condensate? You'd mentioned the soliton models and some of these things, but I was wondering if you ever heard of polaritons, surface plasmon polaritons, and what are called Zenix Summerfield waves or surface plasmon polaritons.
No.
Well, it's very interesting. I think it might be. I found a lot of stuff in the academic literature related to this, and I think it might be related to what you have going on there. And you have this model where it's vibrating. You have a mechanical vibration plus a coupling of electromagnetic fields and light, essentially. And there's a lot of interesting papers on light matter coupling and with light matter Higgs coupling as well.
Well, the mechanical vibration you're converting to electric pulsation. It's the main thing. It's electric waves you're putting out.
And those are far field rather than near field, because I know there's we talk a lot about the waves that are being put out and what their function is.
The longitudinal waves, no magnetic component necessarily. The beam generator that the Navy has, they're spinning it that's the only way they use the magnetic field, is to confine the beam. But the waves themselves are electrogravitic, repulsive. And so the vibration they only use, because with piezoelectric crystals, vibration is converted to electric, and you charge the whole thing up to extremely high potentials, and you're creating oscillations of electric potential on the surface. So when they say about the vibrations not affecting the inside of the craft in their patent to insulate it somehow, they don't want people to be affected, I guess, was from the actual physical vibrations that might be going on there.
And why do you think that the Navy let those patents out? Why do you think that they allowed that to leak and get out to the public?
They're not leaking. They're doing it purposely as part of disclosure. And I met with people at the U.S. Space Command. Actually, the same year the first of those came out, but it was right before. And they were telling me about this new interest for disclosure, that they feel we can't go on continually having everything in the black world. The public needs to know what they've been funding, and that's why they create the Space Force. Eventually, the Space Force was created, and ideally in the future, those projects, which are black projects, would be run through the Space Force. And we haven't begun to see that it's just an entirely new world that's going to be out there for us when they start disclosing. The government will be disclosing free energy machines and med beds and anti-gravity craft. All this stuff is being disclosed. And so this is one example of their disclosure, was these crafts. But it's very old technology for them. They're not losing anything. It's at least 50 years old.
Paul, let me go next to Bill Alec. Bill? Let me see if Bill's, yeah, there he is. Let me ask you to unmute. Bill, you had a question, sir?
Okay, can you hear me now?
Perfect,
Yes.
sir.
Yeah, hi, Paul. I've been doing a lot of work with Tom Bearden's analysis of scalar wave theory. And I'm working with these converging fields and transformers in a resonant mode connected up to a capacitor. And I'm seeing this strange wave that comes up during resonance. When you adjust the frequency on these transformers to its resonant mode here, I'm seeing this, this strange wave that pops up. Now, Tom calls it a scalar wave, but he also calls it a local gravitational wave as well. And you have to use, you can't use normal heaviside Maxwell electromagnetics.
No, those aren't magnetic wave, electromagnetic. They're scalar waves. Yeah,
it's basically empty. You know, there's no solution for that.
Well, these appear in space, right? Is that what you mean? There's no charges or anything associated with them?
As an electric current. Okay. So I supply a steady state AC voltage to this transformer, but the electric current, I see this strange wave occurring at the at resonance. And it turns out that if I use Tom Bearden's solution of quaternion math, that the scalar component comes up. Okay. And there's a solution to it as a sine squared plus the zero vector is what Tom Bearden calls it, the scalar wave.
I would say you're producing something like virtual charge or virtual gravity. In other words, fields that aren't associated with matter in any way, but you're generating them as if you can generate very high potentials, plus and minus, right in the air. I've done it myself with a pulsating effect with a phase conjugation apparatus. And you get huge long sparks jumping in the air. And Tesla was experiencing those phenomena. So those are, I believe, virtual charges, a plus and minus that you create. Maybe
Wonderful.
That's something that can explain what you're doing.
Thank you, Paul. Let me go next to Vlad. Let me ask this on his behalf. He wanted me to ask if you could comment on John Searle's work and the claims of the anti-gravity effects in the SEG. I think you already talked a little bit about that.
Only that a lot of people have tried to duplicate his work. There was a Russian group and they weren't successful from what I understand. There was a group in Eastern US that I guess they were working with Searle and they were getting close to something. I haven't heard if they were successful. But I think in principle it's possible, and I have a chapter on that in my book.
You know, and also if I could ask on behalf of Morgan Lynch had asked, or actually Morgan, would you like to ask? I think he was asking, let me ask him to unmute there. I think he was asking if Beefield-Brown was, or sorry, if Pai's work was based on Beefield-Brown.
Oh, definitely. Yeah. And Bonson's work.
Okay.
Bonson actually even stated in his laboratory notebook, he felt he was charging the ether around the craft and it involved a resonance phenomenon.
Can I ask a short follow-up question?
Yeah, go for it.
Can you turn up your volume?
I can speak louder. I don't know if my volume is working.
That's perfect.
Okay, I'll speak louder. Okay, so one of the reasons why I wanted to ask this question, also, by the way, thank you for an excellent talk. So in terms of the relationship between Bifield-Bound and what Pais is doing, it's the couplings in these things, because Bifield-Bound is purely an electromagnetic effect, and so far as I understand, what Pais is doing.
Electrogravitic.
Electrogravitic effect, and then what Pais is doing is this conversion of electromagnetic radiation to gravitational radiation, which reduces the mass via the Gertzenstein mechanism. So he uses
he's trying to vibrate the piezoelectric, so you can use probably EM microwaves to excite the piezoelectric. But the piezoelectric it's a resonant cavity, so the piezoelectric would be going radially. And that would be producing actual scalar waves. It would involve magnetism of what's actually leaving the craft.
And so it's not, because the reason why I had my point of confusion is because in terms of the actual power output and thrust would be, you would have some crazy 40 orders of magnitude difference between the electromagnetic coupling and the gravitational coupling between these things. And is this something that's understood, or is this something that
You lost me there. The 40 orders of magnitude.
Yeah, the conversion, the production of thrust, so far as I understand from the patents from Pais's patents, is it comes from the conversion of electromagnetic waves into gravitational waves via the Gertzenstein mechanism. And this is a small, I mean, very, very, very small effect, to the point that Pais needs his high energy electromagnetic field generator operating at the Schwinger limit, at a at an absolutely very high power level, to convert it into gravitational waves to produce the effect. And I mean,
maybe he's constrained by what physicists will understand, and I don't think it's really. You really have to go to an ether model to think about this stuff, and maybe take some of these concepts like Schwinger limits and so on, and put them in the context of the ether to really understand.
I see, actually. No, and I was actually interested about this because I was unaware that they had measured bifield Brown in vacuum, and that's where I was like, oh, like this is really cool that all of a sudden it's in vacuum, because I would hear about it that it's like a wind effect, from atmosphere and things.
Oh,
like
no,
this,
it's not the ion effect at all. He's done vacuum chamber experiments and shown it's still there. In fact, it works better in vacuum.
Oh, nice. Okay, all right, yeah, thank you so much. Excellent talk, though. I appreciate it.
Oh.
Thank you.
Got a few more questions, Tim? I don't hear you.
Oh, I'm sorry. I'm sorry about that. Yeah. Actually, I was just asking who else has questions.
I'd seen a few comments there. Something about they didn't understand something about the piezoelectric.
Marco had he just put one through. He wondered about the Nasikas thruster. I'm not familiar with that.
Yeah, in fact, I think Dr. Nasikas is one of the attendants. Actually, he should do a presentation at your conference.
Yeah,
talk about his thrusters. Yeah, we're working together on that. His first version showed a very small thrust with a permanent magnet. But to get the big thrust, you need electromagnets, superconducting electromagnets. And we have a new version he's designed, which hopefully we could, the computer model suggests enormous thrusts. In terms of newtons, over 1,000 newtons, 100 kilograms,
I think Marco had written here force to mass ratio of at least 13. So, yeah. And
that was for the first version. For these versions, we're talking about thousands. You get one thruster, you can become Superman, go into space. If it works, we got to test it, That's a project we're working on, getting requests for quotes and stuff for that.
Well, thank you. I've never heard of that one before, so I feel a little ignorant on that. But let me go to Jeremy next, sir.
I just have so many questions. Sorry, my mic was off. I had muted it for the live stream. I just want to remind all our live viewers that smash that like button and stay tuned, because it's going on. It's not the end of it. Paul, I wanted to ask a question about you had mentioned in that first slide a couple things. I wanted you to talk more about black holes, what your idea was on some of your ideas on cosmology, and also what you said you can replace space-time with something else, and I was wondering, like, what do you replace quaternions with, and Minkowski space time metrics and that sort of stuff? Like, what was your replacement?
I replace them with model G. That's that partial differential equation set. That's the whole ball of wax. Very simple, just 3 partial differential equations. And it's a simulation approach. So, I mean, you can still retain all the physics observations. There's a lot of work to be done to intermingle what we developed over the centuries in physics with subquantum kinetics. So far, it's been me, and now we have a group doing the modeling. So there's no reason that anyone can just jump in and learn subquantum kinetics and start doing this work. One fellow has compared subquantum kinetics with standard physics and had all sorts of advantages of subquantum kinetics over standard physics in all sorts of areas. It's the simplicity is one. It's really quite elegant that you can get so much out of this one model, this approach. Whereas physics is more built like a patchwork quilt. My view I always talk about is that physics was developed by doing experiments, developing a theory about the experiment, and then you try to sew it together with other experiments into a unified field theory. And so the problem is you'll end up with a patchwork quilt. Whereas with subquantum kinetics, we begin with the genetic code and we tweak the equations, pick the right constants and parameters in those equations that we simulate till we get things that match reality. As for black holes, they don't form in subquantum kinetics. For one thing, to form black holes, you have to have the gravity field within the particle go to infinity. It has to be a singularity. And that doesn't happen. And we see that in the actual particle scattering experiments, that the electric field doesn't go to a peak, it rounds off. And knowing that there's an electrogravitic connection, that would mean the same happens for the gravity field. So as two particles get closer together, the force goes to zero because their fields are plateauing. So the other thing is that when you have a collapse in subquantum kinetics, you would produce what's called genic energy, because in the supercritical region of a mass, energy is over unity. Photon increases its energy over time. Like on Earth, it's happening right now. And that's where the heat, the core of the Earth is coming from mainly. About 15% of the sun's energy is genic energy, spontaneously produced, the rest fusion. But as an object collapses, that genic energy depends both on the gravity potential, which would, the gravity well would go very deep as the object collapsed, plus the temperature would go sky high. And those two things together would cause genic energy to go through the roof. And that's why you get supernova explosions. It wouldn't be possible to form a black hole because the energy would be so powerful coming out, it would bring the collapse to a halt. You have what you call, I call them mother stars. They're supermassive cores of the centers of galaxies, and, like 4 million masses, solar masses packed in there. Forming a star, immense mass star with an incredible energy generating capability. It's generating that energy over unity. It's photons increasing their energy over time. And it's an immense amount of energy that's radiated from those. And not only energy, but matter is created there. They're increasing their mass over time because matter created in the supercritical region gets blown out during the explosions. 95%, 99% of the matter in our galaxy once originated from the core. So this is inside to out type of cosmology. Jeans had this idea, Sir Jeans.
How do you spell that?
James Jeans. As for cosmology, one of the first predictions of subquantum kinetics was that photons would lose energy as they traveled through intergalactic space, because intergalactic space should be subcritical. So just the opposite of what it is in the galaxy. And so you should get an exponential decrease. And so I started studying cosmology at that point, and I learned about the tired light model, and people were actually suggesting that just based on observation as an alternative for the expanding universe concept, that photons lose energy as they travel, and it's not really that the galaxies are receding. So I wrote a paper in Astrophysical Journal back in 1986, which showed that the compared the Big Bang theory, expanding universe theory, to the static universe tired light model. And the tired light model fit the data better on 4 different tests. And if you try to adjust the Big Bang theory to fit your data like they usually do, on one test, then it would go further away from the data on the other test. So it's sort of like a Chinese handcuff. And so that pretty much put a nail in the coffin of the Big Bang theory. I've done an update of that paper, and I'm trying to get it published. And it's very hard to get published because everyone is so, in the physics community, it's sort of like it become a religion. And anything, you can have the best paper and it won't get published. So you're going knocking door to door right now, hoping somebody will open. But you can see that paper, it's updated, and I now have 8 cosmology tests instead of 4. And so it's much, much better than what I published in '86 with updated data. And you can find it going to either starburstfound.org, to the archive, paper archive, or to the etheric.com archive. Also, there's a very good paper on gravity, which will be a chapter in a book on gravity coming out this year. And the paper is the pre-edited version, which is available for everyone. And it gives a very nice overview of subquantum kinetics, all the gravitational aspects of it.
Wonderful. Well, Paul, we're just about out of time for the Q&A session. We're actually going to go to Mike McCulloch next. But again, let me thank you so much for spending the time to share all this with us and answer all the questions. So again, let me mute you back out, and I will put it on gallery view. And everyone, let's have, again, an enormous hand for Paul LaViolette. Sir, I cannot thank you enough. It was wonderful having you with us today. Thank you again. Okay, so let me go now, and let me see. I'll do the intro for Mike McCulloch. So next, everyone, I'd like to introduce you to Dr. Mike McCulloch, who just came in. He'll be discussing quantized inertia and the horizon drive. Mike has a bachelor's in physics from the University of York, a PhD in physical oceanography from the University of Liverpool, and currently lectures in geomatics at the University of Plymouth. He's a member of the British Interplanetary Society, the Lifeboat Foundation, and a fellow of the Higher Education Academy. And he's published dozens of papers on physics and geophysics in numerous journals. We've had a lot of requests to have Mike present at APEC on quantized inertia and the horizon drive. So I'm really pleased that he's able to join us and speak about it today. So Mike, I believe you are with us, sir. Ah, there we go. Let me ask you to unmute.
Yeah, hello. Thank you for inviting me.
Welcome to APEC, sir.
Thanks. Shall I share my screen?
Yes, please. Wonderful. It looks like we're all set.
This should be my first slide should be showing now.
Wonderful. I'll mute myself out. Again, just go whenever you're ready, and thank you very much.
Okay, thanks. Okay, so today I'm going to be talking about quantized inertia. So I'll first go into a bit of the background. What is inertia? What do we think it is? Then I'm going to propose a new theory for it called quantized inertia, discuss the astronomical evidence that I've managed to collect so far, talk about the DARPA funding I received to test it in the lab for thrust, talk about horizon drives and their applications at the end. Okay. So I guess I don't really need to go into this because Tim already went through this. So this is my background. You can say I was also a scientist at the Met Office in ocean forecasting. So I have a background in the ocean, and some of my thinking in physics comes from my previous experience studying ocean waves. Okay, so the basic problem I started off with was the well-known galaxy rotation problem. So, as you know, this is a galaxy. This is the Andromeda galaxy, and it's spinning around, all the stars and it's spinning around. And they've managed to calculate the amount of mass in a galaxy by looking at the number of dots in it, and assuming each one has the mass of the sun, you can work out the mass. And then you can look at the velocity of the stars using Doppler shift and work out their speed and the centrifugal force that they are experiencing outwards. And it turns out that the gravitational attraction is far too small to hold the stars in. So all the galaxies we see should be flying apart, but they aren't, obviously. So this was first noticed by Fritz Zwicky, who's shown on the bottom left in 1933, and more recently with galaxies themselves, Fritz Zwicky was looking at galaxy clusters by Vera Rubin in the 1980s. So of course, normally what's done.
Mike, I'm sorry if I could jump in really quick. There's some background noise. And I should apologize for interrupting. Is it too close to a computer fan, perhaps, or?
No, it seems fine. I can't hear anything, so I'll just try and speak up. Shall I?
Okay, thank you, sir. My apologies.
Yeah, sorry about that. Okay, so what's normally done in astronomy is to add dark matter to the galaxies to increase the gravitational force inwards to hold the stars in. But dark matter has to be adjusted to fit every galaxy, so I don't regard this as being good science. Other reasons for doubting dark matter, there's a list here. So, for example, there's something called Renzo's rule, where speed follows the light. Every time there's a change in the speed of stars and galaxies, there's also a change in the light curve, or the amount of light in the area. So it seems that speed follows the light, and there's nothing dark affecting it. I'll talk about Milgrom's break, what I call Milgrom's break, a bit later. But also other smaller systems like globular clusters and wide binaries within galaxies, they can't contain dark matter, which must remain smooth on those scales. But they show the same anomalies as well, which argues against dark matter. And also a philosophical point, dark matter is not falsifiable. You can look forever for more exotic dark matter particles and get funded to do so. And you can go on forever like that. Okay. So I started thinking about inertial mass. So inertia has never been understood. It's just assumed that things keep going in straight lines until you stop them with force. For example, this ladder keeps going in a straight line when the van stops. Inertial mass is not due to the Higgs field, which only explains the mass of the quarks, which is about 0.1% of the mass. So what I'm going to do is propose a new model for inertia, which combines some aspects of relativity and quantum mechanics. Okay, so first of all, quantum mechanics. So the Heisenberg uncertainty principle. So this is quite famous and is shown at the top here. It says that the uncertainty in momentum of a quantum particle times the uncertainty in its position has to be more than a very small number. So what this means effectively is that if you shrink the spatial scale that you're looking at, so you shrink the uncertainty in position, then you increase the uncertainty in momentum. So this means that on the smaller scale, space is teeming with virtual particles, which they can be thought of as particles appearing in pairs, as shown by these blue arrows here, or they can be thought of as waves, shown by the red wave here. So space on the smaller scales is a bit like an ocean. So is this true? Well, Hendrik Casimir proposed a test for this. He said that if this is true, and you put two plates very close side by side, then some of these quantum waves would fit well between the plates, for example, this one at the top, and some wouldn't. So you see the one in the center here, there's an antinode at the plate, so the electrons in the plate will move around to damp the wave. And so some of these waves will be cancelled between the plates. And this means that there'll be more quantum vacuum pushing the plates together than will be pushing them apart, so they will tend to move together. And this is called the Casimir effect, and it has been well observed now. It was observed first in 1996. Okay, so it seems that on a smaller scale, space is a bit like the ocean. So I'm going to try and present you a simple analogy now. This isn't meant to be exact, it's just an analogy. If you imagine a ship parked next to a dock, then out to sea there'll be lots of waves hitting the ship, giving it momentum and pushing it towards the dock. But the idea is that between the ship and the dock there will be fewer waves, because first of all there'll be sheltering, but I'm not so concerned about that. There will be a kind of resonance in that only certain waves can exist. For example, one shown can exist because it's got a node, a place, part of the wave where the water doesn't move at the ship and the dock, so there's no friction, so this wave can continue to exist, but other ones are damped. So there'll be more waves out to sea, so the ship will tend to move towards the dock, and in fact there's something called a maritime Casimir effect. In the ocean, two ships side by side will tend to move together because of this effect. So in this case, the ship will move towards the dock, and if the people aren't aware of the waves, then they will assume something mysterious. And I think this is how we regard inertia at the moment. Okay, so in order to go a bit further, I have to replace the dock damping waves with something a little bit more abstract, and that's a horizon. So imagine you have a rocket which is accelerating to the right here, shown by this black shape, and it's accelerating so fast that even if an explosion happens behind it, the sound from the explosion will never catch up to the rocket. Then from the point of view of the rocket, the explosion does not exist. So you could say that the explosion is behind an acoustic horizon for that object. So this is the idea of a horizon. It's sort of a boundary to the cosmos that we can know about, and it doesn't just work for the speed of sound. It also works for light, in that if the rocket accelerates fast enough, then even the light from the explosion will not catch up with it. So a horizon is not a physical thing, but in what follows, I'm going to treat it as if it was. Okay, so these horizons have been looked at before. So for example, Stephen Hawking wondered what would happen if one of these virtual particle pairs was emitted on a black hole event horizon. So if you have a lot of mass in a particular region of space, light cannot escape from this so-called black hole. And if you have a virtual particle pair emitted right on the boundary, the one that goes into the black hole will disappear, which will leave its twin free to be released as what's now called Hawking radiation. Just a couple of years after this, Bill Unruh from Canada, who's shown in the top right here, said that a similar thing happens to an accelerating spaceship or any accelerating object, in that a certain point behind it, in the area on the left, information will never be able to catch up to that spaceship traveling at the speed of light, limited to the speed of light as it is in special relativity. So again, if you have a particle pair emitted right on this horizon here, the one that goes behind the horizon will disappear, and the other one will then be free to be released as what's now called Unruh radiation. So this is a very interesting kind of radiation, because it would be seen by the accelerating spaceship that somebody standing still or going at constant speed in the same space would not see the radiation at all. Okay, so has this been seen? Well, it may have been. The problem with seeing Unruh radiation is that the wavelength is very long for the accelerations we experience. So for terrestrial acceleration of about 9.8 meters per second, the wavelength is about 7 light years, which is unseeable. But if you were able to boost the acceleration a huge amount, so increase A here, then the wavelength would reduce. And in one experiment, this may have happened. This was an experiment done by Bevis Lewis and reported on by Igor Smolyaninov, who's shown here. They shone a laser onto a gold nanotip, which is shown in the top picture, the plasmons from the laser went around the bend of the tip very fast, a huge acceleration of about 10 to the 19. And they saw light coming off the tip, which was unexpected. And Smolininov managed to show that this looked just like Unruh radiation. So it may have been seen already. So I'm going to use this Unruh radiation, just as I used the ocean waves before, to try and explain the concept of inertia. One of my inspirations for this was a paper by Hai, Schroeder, and Puthoff back in 1994, where they published a very interesting paper attributing inertia to the 0-point field. But they needed an arbitrary cutoff for the 0-point field. And the model I'm going to suggest doesn't need an arbitrary cutoff because it works on a difference in the 0-point field on both sides of an object. So the absolute value of the 0-point field drops out. So that's kind of nice. Anyway, imagine you've got an object shown by the black circle here, accelerating to the right. It sees Unruh waves, which I've shown with the red waves on its right-hand side. Now, between the object and the horizon, the new bit is I'm going to assume that this horizon is able to interact with these Unruh waves and damp them, just like the dock did to the ocean waves, so that only certain Unruh waves can exist between the object and the horizon, like this one, for example, the one shown. If you do this, then there'll be more waves, more radiation in front of the object, pushing it back, than there is behind it, pushing it forward. So there will be a force tending to oppose whatever acceleration you give it. And I managed to show in a paper in 2013 that this looks like inertial mass. And after Jaume Gine corrected a factor of 2, and we published a paper in 2016, it predicts inertia really well. So this predicts standard inertial mass, this mechanism. But that's not the whole idea. There's also another horizon, the cosmic edge. So very far away from us, 10 to the 26 meters, stars are moving away from us, or one of the models is that stars are moving away from us so fast that they're moving at the speed of light and we can't see them. So there's a cosmic horizon. So if an object is accelerating so slowly that its Unruh waves become so long and the horizon it sees recedes so far, as far as the cosmic horizon, then on both sides of the object, the radiation will be equivalent. It'll be equivalently damped. So this mechanism for inertia will tend to collapse at very low accelerations. And I showed this in a paper back in 2007 here. So this is exactly what's needed, it turns out. So what happens is that in the center of galaxies, the acceleration of stars is large, so the Unruh waves are short. But at the edge, the acceleration is very slow. So the theory predicts that the inertial mass reduces, and in fact, it reduces to exactly the degree that the centrifugal force becomes exactly equivalent to the gravitational force. So we have a very nice balance. So I showed that first in a paper in 2012, and then this is a later paper from 2017, where I looked at data from 153 galaxies, and the plot shows the expected acceleration of the stars along the x-axis and the observed acceleration along the y-axis. And the data is shown by the gray squares. And the theory is the dashed line. This is quantized inertia, the prediction, and it agrees with the data. And I should note that there's another theory called MOND, which is shown by the solid line, which also predicts the data, but with MOND you have to input an arbitrary parameter called A0. So they're able to tune that theory to fit the data, whereas I have no such luxury. The theory has only one chance to be right, and it gets it exactly right. Okay, so that's a paper from 2017. Okay, but the clinching piece of data, and this really means there can be no doubt about this mechanism, is that in the center of galaxies, the acceleration is relatively large, so the Unruh radiation is short. As you move out to larger radii, the Unruh waves lengthen because the acceleration is less. And crucially, at exactly the radius that the acceleration is so low that the unruh waves get to the cosmic scale, it's at exactly that point that the galaxies start to misbehave. So this is a compelling piece of evidence that the galaxy rotation problem must be due to unruh radiation and quantized inertia. Okay. Oh, and this point here I call Milgrom's break, by the way, because the physics sort of breaks and changes to a different regime. Okay, so since then, so that was all about inertia, but it turns out you can derive gravity, Newtonian gravity, in the same way, well, a very similar way. So you start from the uncertainty principle like this, and if you apply it on a macroscopic scale, so on the right I've shown the sun here and the Earth orbiting it. So if you now treat matter as a horizon, so you imagine that the sun is a horizon for the Earth because it blocks the space beyond it, then you'll see that dx is very small between the Earth and the sun, but between the Earth and the rest of the cosmos, the uncertainty in position is going to be very large because it's a large space. So you can put these values into Heisenberg's uncertainty principle, and whenever dx is small, dp is going to be large. The uncertainty momentum is going to be large. So this means that the Earth has a large uncertainty of momentum towards the sun and a small one away from it. So this means that the Earth is going to move towards the sun, a bit like gravity. Well, it turns out that if you do the maths, you come up with Newtonian gravity. It's exactly the same. And I can report as well that in the past week, I've now derived in the same way a variable speed of light version of general relativity as well by this method. Okay, so this is reported in a paper here. I wrote a paper in 2014 on it, and that's the journal link, and there's an animation of it as well on YouTube. Okay, so now I start to get a bit more practical. So if we understand inertia, then maybe we can control it. So the way to do this would be to have an object that you impart a very high acceleration to. So this could be a spinning disk. This could be microwaves in a cavity, something like that. If you accelerate it fast enough, then the unruh waves will become short enough that they might be damped by, say, a metal plate, something as simple as a metal plate. So I proposed this in 2013 in another paper in 2018. If you can damp these unruh waves, then it means that, for example, in this case, you've got unruh waves coming up from below and fewer of them coming from above. So the object will tend to move up. And this is great because it's a fuelless way of producing propulsion. Normally, to get something to move up, we have to blast hot gases out the bottom very fast, which is dangerous, noisy, expensive, and you have to carry heavy fuel. But this would require no fuel. So this would be a horizon drive because the metal plate is acting like a horizon. Okay, so there might be several ways to do this, and I think a lot of effects like this have been seen over the years. So, for example, there was the Pokletnov disk from 1994. So what he had was an asymmetric disk with a very high acceleration, spin acceleration. And the interesting thing for me was that he had a disk with a very small, very fine crystal structure on top and a coarser crystal structure on the bottom. What this will tend to do is to damp these unruh waves that the material is seeing more above than below. So you will get a gradient in the unruh field that I've tried to show here with this yellow color. So it's more intense below and less intense above. So this will tend to move things. Things will tend to flow down move down the gradient. So things will tend to move up in the vicinity of this disk, as was observed. Okay, so Then there was Scheuer's M drive. So British engineer Roger Scheuer in 2001, he found that when he resonated microwaves within an asymmetric copper cavity, that looked like this, obviously, called the M drive, it tended to move towards its narrow end. And in a similar way, this will tend to cause a gradient in the unruh field as well, because the narrow end will damp the unruh waves more than the wide end. So again, you'll get a sort of a gradient that things will tend to fall down towards the narrow end and produce a force in that direction. Then there was Woodward, Jim Woodward from California in the 1990s, and also more recently, he's been looking at asymmetric capacitors. So here's a picture of one of those, vibrating piezoelectric crystals between the capacitors to produce a high acceleration. And in this case, the thick capacitor plate on the left here will tend to damp unruh radiation more than the thin plate. So again, you'll get this sort of gradient that the object will move down. And indeed, these things tend to move towards the thicker plate. And then there was Thomas Townsend Brown from the 1950s and earlier with his capacitors, and they tended to move towards their anode. And I'll show you a very direct case where this also means that there's a gradient in the unruh field that pushes it in that direction. But I'll get back to that in more detail later. But I have published papers showing that I can predict the Pogletnov effect, or at least some aspects of it. Scheuer's M drive, although of course that's still controversial, and Woodward's Mach effect thrusters as well. So this is some data for the M drive. This is a plot showing the thrust predicted by quantized inertia on the x-axis and the observed thrust up the y-axis. And you can see it, the theory does quite well predicting the thrusts. But with the M drive, it seems that some groups can detect it and some groups can't. For example, Roger Scheuer obviously detected it. NASA, Harold White at NASA detected a signal and a thrust. Even Martin Timer in Germany did at one point, but now he cannot. And I think NASA had a second try and they couldn't detect any thrust the second time. So it's still very controversial. Okay, so it was about this time that DARPA, I was contacted by DARPA. They emailed me showing interest and I applied for funding and was awarded $1.3 million to look into this. So DARPA is a Defense Advanced Research Projects Agency, and they've had a hand in things like GPS, the initial versions of the internet, the ARPANET, and stealth fighters. So my project's aims are to make quantized inertia more predictive. So they wanted a computer model predicting the thrust from any given structure, and also to show whether or not it can counter gravity. So they're obviously interested in thrust and launching things with it. So this doesn't mean that I had to launch things, just to produce a thrust in the lab that was obviously due to quantized inertia and that could be scalable to produce a launch later on. So I commissioned some labs, and well, there's a lot I'd like to say about the experiments, but I'm unable to for fear of lawyers at the moment. So there was a test in Dresden where an infrared laser was used and fired into a copper cavity, an asymmetric copper cavity, and it was on a torsion balance, so any thrust on the cavity should have rotated the system. And the system used was a very sensitive one, capable of detecting a few nanonewtons. So the simplest way to say it is that no thrust was detected for this pathway. So we've abandoned it. There's a lot of detail behind that, but I won't say any more. There was also a lab in Madrid, Professor Perez Diaz, shown here, and his team. So what they did was they had a laser, they put the signal into a fiber optic loop with 300 loops, and then placed a metal plate in the vicinity And the idea here is that unruh radiation will hit the structure from all directions except from the one where the metal plate is, and it should gain weight. And indeed, it did seem to gain weight by the expected amount in the results from last year. They then put a plate on the other side to make it symmetric, and the thrust disappeared. So these results are encouraging, and the observed force was 0.1 newtons per kilowatt. So you get 0.1 newtons for every kilowatt you put in, which is good. This is better than ion drives, and you don't need fuel. But we're not quite sure about the results yet, so we have to do some more tests on this. There are also tests going on in California at the University of Southern California. So I've been collaborating with Professor David Barnhart at USC and Dr. Ryan Reed with positron dynamics and a few others. And we won some funding from CATIA, which is a Californian aerospace funding body, for them to do some QI cavity tests. But because of COVID, these haven't been done yet. There's been quite a delay, but this would be quite a nice test because they're hoping to use a levitated cavity and then use an interferometer to look for very fine movements. There are also tests being done in Poland by Z Kamala, which are very interesting, but I don't have time to talk about today. And then in 2017, I was contacted by an electrical engineer called Frank Becker. So he'd read my papers on quantized inertia and realized that some earlier experiments he did trying to reproduce the Brown effect, the Bielefeld-Brown effect, could be evidence for quantized inertia. So we talked about experiments using capacitors. Then he received funding and experimental help from Anker Bat, who's actually an actor, but he has an MSc in electrical engineering. And they reported their results on the archive and VIXRA. So they're using capacitors. I mean, I was listening with great interest to Paul's talk just now, and it seems there's a tremendous history behind this that I was only vaguely aware of. What I was aware of was that many groups since the 30s have been looking at capacitors and have reported anomalous thrusts. So T.T. Brown in Paris measured thrust in a vacuum. Canning at NASA in 2003 measured thrust from asymmetric capacitors in a vacuum. Also, T. Musher from Japan measured thrust, but not in a vacuum. And there's a good summary in this paper here, Martins and Peniero from 2011. So the Becker and Bat experiment went as follows. They had a DC power supply, 5,000 volts, and they fed it into a capacitor, which was inside a vacuum sealed container. And the capacitor plates were very close together, a few micron, about 2.5 centimeters in diameter. And they placed the whole thing on a digital scale and they put various voltages in and measured the change of weight. And they measured results like this. So this is taken from their paper. So on the x-axis is the separation between the capacitor plates. So you can see it goes from about 1 millimeter here down to about 1 micron on the left. And up the y-axis, it shows the normalized force. So you can see that the force they got, which is shown by the red dots here, increased as the separation reduced. And because the y-axis is logarithmic, this is actually an exponential increase of the force with the closest of the plates. The interesting thing is that the best result they got for a separation sort of 10 micron is 100 newtons per kilowatt. And this is quite explosive, because if this can be confirmed, then this means we can launch things electrically without rockets. So I'll come back to this in a bit. But the best my DARPA-funded test had achieved so far was 0.1 newtons per kilowatt in Spain. So this is apparently 1,000 times better. So I was very excited by this. Since then, in fact, just this last week, I've been contacted by another team who read a blog that I wrote about this and did a test and got a very similar result. That's the result shown by the black cross here, which tallies with Becker and Batt's data. But the good thing about this new test is that they didn't use a digital balance. I was slightly concerned that electrical effects would be affecting the balance. They used a pendulum and measured the angle of a pendulum, which is a non-digital, non-electrical way of measuring it. So that's very nice. So DARPA have now agreed to allow us to do tests at Plymouth to try and confirm this. So to try and explain what's going on in terms of quantized inertia, the schematic tries to do that. So normally in quantized inertia, an accelerated electron, which is shown by the black dot in the upper picture, would see more unruh waves in front of it. So I've shown that with sort of warm orange color than behind it, because the unruh waves would be damped behind it by this horizon shown by the black vertical line. So it would tend to be pushed back by the orange in front against its acceleration, and it would feel inertial mass. But what I think is happening with the Becker and Batt's capacitor is that the electron is coming off the cathode in this direction. But now, instead of seeing a lot of unruh waves in front of it, it sees virtually none because the capacitor plates are damping them in front. Instead, now it just sees the unruh radiation behind, so it's actually pushed forward. So what's actually happening is that the process of inertia has been reversed by the capacitor plates, and the electron has got more momentum than you expect, and then it bangs into the anode and pushes the whole structure forward. So I've done a calculation over the past 2 weeks predicting what quantized inertia would predict for this, and this is the result. So the force you should get should be n, the number of electrons you put in, reduced Planck's constant times the speed of light divided by 2 times the separation of the plates squared. So the x-axis shows here the separation of the plates. The y-axis shows the predicted and observed force. Predicted force is the red squares, and the observed one is the black diamonds with the error bars. So you can see that the prediction agrees with the observed thrust really well. So this is really interesting because this is a huge force which is launchable. Becker and Batt also did some other things with their experiment. They, for example, they thickened the cathode. You can see I've shown it in the schematic on the left. And this will tend to damp the unruh waves on the left even more, so it should reduce the force. And indeed, it did. So this graph here shows the force. These bars show the direction of the force, whether it's forward or back. So initially, they have this big blue bar, and with the thicker cathode, they reduce the force. But the most interesting result probably is the fact that when they put the this metal bar behind the Rindler horizon, as soon as it went behind the Rindler horizon, it had no effect on the experiment. And I should say that this Rindler horizon is not a physical thing. It's a calculated position where this information boundary is. So there's actually nothing there from a physical point of view, just an informational one. And as soon as they put this plate behind it, then the behavior changed and they got the original force back again. So this is a nice crucial experiment for quantized inertia, and it could be the first direct observation of a horizon. Okay, so I can show you where Becker and Batt. These results are published on the archive here and on VIXA as well. Okay. So this will be extremely useful for satellites. So this shows a schematic showing a satellite. You have a solar panel here, which has a mass of 20 kilograms and an output of 0.25 kilowatts, taking typical values. And say you put a horizon drive on it of mass 10 kilograms, total weight will look like that. If the horizon drive produces 100 newtons per kilowatt, and we've got a quarter of that, we'll get a force of 25 newtons, which is about 8% of his weight. This is much better than present satellite ion drives, which give only about 0.02 or 0.1 newtons per kilowatt. and they need fuel. Quantized inertia apparently, well, it should, if this experiment is confirmed, give 100 newtons per kilowatt and without fuel. So obviously much better. It also means we can launch things. So if you had a horizon drive with a mass of 10 kilograms and a lithium air battery with a mass of 1 kilogram, that would produce 1.8 kilowatts per kilogram. And if you work everything out, you get a force of 180 newtons upwards, which is more than the weight. So this would enable launch. Okay. So the horizon drive will also give you a very smooth ride, and I've been quite intrigued. I'm not sure whether it's true or not, of course, but the Nimitz UFOs seem to dart around very fast, very high accelerations, and if there was anything in them, surely it would be flattened against a wall. But if, for example, they had a propulsion system like this, then that wouldn't happen. So normally, if you have say a tic-tac shaped spaceship with a flower in it, and you suddenly accelerate it hugely by firing your rocket, then the flower will be smashed against one side of the tic-tac. But with quantized inertia, what you're actually doing is manipulating the process of inertia itself. So the flower would not be affected because the gradient in the unruh field will affect everything inside the ship equally. So the flower would not be smashed. Okay, so there are other ways to do this. For example, I've recently shown mathematically that if you have a horizon drive small enough on the nano scale, well, that 0.1 micron, then you might be able to produce thrust without power, because just by using the 0-point field itself. So you might be able to design a material, a nanomaterial that self-propels. And I wrote a paper about that called Can Nanomaterials Push Off the Vacuum? And that's in progress in physics. Okay, so you might be able to produce something like this, something that floats without even power. Okay, so applications. The obvious first one is satellite station keeping, far more effective than ion drives. You'd also have to launch lighter satellites. They won't have to carry fuel. Orbital maneuvering would be silent. I've also shown that you might be able to generate power from the vacuum as well using these nanocavities, but I haven't mentioned that in this talk. Obviously, flying cars, new kind of aircraft, structures that hover. So if you can build these nano cavities, you'd be able to build materials that hover by themselves. Obviously, launch interplanetary trips will become easier and cheaper, and it also makes interstellar travel possible in a human lifetime for the first time. Because in order to get to, say, the nearest star, Proxima Centauri, you have to get near the speed of light, and to do that, you have to carry so much fuel that you need to carry a minor planet with you. So this makes it very difficult. But this kind of propulsion would be propellantless, and so you will be able to do that. You'd be able to get close to the speed of light. Okay, so a summary. So quantized inertia explains inertia, obviously. It unifies, in a sense, relativity and quantum mechanics. It uses both of them. It gets rid of dark matter because it models galaxies without dark matter. It has extremely good astronomical evidence. I talked about what I call Milgrom's break, that proves it's unruh radiation that's causing galactic rotation, the effects on galactic rotation. It predicts a very useful horizon drive or electric rocket. DARPA funded experiments, and we're homing in, hopefully, on a successful pathway using capacitors. That's the most successful pathway so far. And DARPA is going to fund an experiment here at Plymouth University to confirm that and try and enhance the effect. So if we can verify this, we'll have fuel satellites, electric launch, and interstellar travel will become possible. The sort of scientific takeaway from this is that quantized inertia says that all movement is caused by horizons damping the quantum vacuum. So let's design technology that taps into this. Okay, so just a sort of contact slide. Thank you for listening. And I can take questions. This is my book. You can contact me by email. My blog is Physics from the Edge as well as my book. I'm on Twitter, and there's a TEDx talk here to watch. Thanks for listening.
Well, Mike, thank you very, very much. Let me mute you out for just a second. I want to go to gallery view. And actually, you know what? I need to, here, I'm going to stop your screen sharing. Let me go to gallery view. And I want everyone to give Mike an enormous applause. Thank you, sir. That was a wonderful presentation. Absolutely wonderful. And actually, that's I think that's a really brilliant model. I'm really excited by that. Okay, so let me go back to speaker view and let's go to questions. Okay, so I will unmute you and let me see. I have questions about, so who would like to go first? I have a ton of questions in chat, but I also have a ton of comments there as well. I guess, so David Mathis was asking about inertia control of the Rindler horizon. David, do you want to ask that directly, sir?
I don't even remember where it's at. First off, Mike presented a lot of information.
I know, he went through a
short amount of time. And just trying to take notes on his lecture was a little bit interesting. So, Mike, are you suggesting that you can provide eventually inertia control of the Rindler horizon or some other event horizon?
Yes, I can control, I think we can control inertia using synthetic Rindler horizons.
And how do you expect to construct such a thing? Is it going to be, does it require a metamaterial to do so? Or is it an electromagnetic phenomena only?
It's an electromagnetic phenomenon only. So I'm assuming that Unruh waves are composed, as is known, of all the fields. But at the moment, I can only see that we can affect the electromagnetic component of it using metal plates, metamaterials, that sort of thing.
Okay. Thank you.
Okay, thank you, David. You know what? Let me go to Jeremy Reese and see if we have any YouTube comments. Jeremy, do you have anything from YouTube?
Let me just unmute real quick. Sorry about that. We had first off, Mike, I'd like to thank you so much for joining us today. That was fantastic. I've read a lot of your work. I've dived into a lot of these concepts, so it was a little easier for me than, say, someone who's taking notes and all new to this stuff. For me, it was like a roadmap of all these little bits and pieces of a lot of stuff that I had read or knew about, but you did a brilliant job of connecting it just now in this presentation. This was fantastic.
Thanks.
I wanted to ask a little bit more about how schemes for where we're, of course, an engineering conference, and I want to ask a little bit more about the M drives, which I think that dates back to, like, what, 2007?
Maybe 2001.
2001. Wow, that far back. So the M drive, and also what you know about engineering projects and groups that are working on this, and anyone else that you might know of, that, because I'm always interested in getting new speakers to present. So anyone that you could recommend, name drop away.
Yeah, there's Martin Timar in Germany, who I mentioned in my talk, who's been looking at M drives, and I think has a null result, a zero thrust at the moment. There's somebody I think he's at the Naval Research Lab, called Mike McDonald, who's looked at them as well. And I think he also got a zero result.
Yeah, and I believe Roger Scheuer will actually be joining us on April 3rd, if I remember correctly. He'll be presenting on the M drive. And so we could ask him more about that and how that interacts with the quantized inertia model when he joins us too.
And also, my second part question was: have you ever heard of Todd Desiato? You mentioned Hal Puthoff in some of the VSL stuff. I know Todd has published extensively on VSL GR, and I was wondering if you'd ever read some of his work.
No, I haven't. I haven't read any of his papers. I'm afraid. I have heard of him. I know the name. I'll make a note of it.
Yeah, definitely.
Okay, well, Jeremy, thank you. Thank you. So let me mute you back out. Let me go to, let me see. Hector Serrano was asking about espresso. That doesn't count, Hector. And let me see. Jonathan had a question, and I should apologize. I'm trying to scroll through chats. There's a lot of them in here. Jonathan was asking about spacecraft design. Jonathan?
Yeah, so thank you for the talk, Mike. I've got a question about how the energy generation and propulsion applications of quantized inertia would fit together in a single spacecraft. Now, as you've mentioned on social media before, you could do an M-drive style free energy device by spinning a pair of thrusters around an axis to generate current. And then eventually that hits over unity if you do it in the right way. So would the horizon, would the artificial horizon set up for doing that with, say, the axis of rotation along the axis of a spacecraft interfere with a horizon that you're trying to set up for a thruster on the aft end?
The horizons would be independent.
Okay.
So that would be okay. That wouldn't be the most efficient way to do it. The most efficient way to do it would be move the cavities to a nanoscale. So then you wouldn't need any input power at all.
Sure, I'm just thinking because like nanoscale materials are not exactly easy to make. And so something that you could build out of things that, like regular electronic components and steel and things like that would probably be a little more attainable. Like we've seen down in Boca Chica, cheaper construction makes up for a lot.
Yeah, okay, sure. Yeah, a lot of people become concerned about that because it looks like I'm getting energy from nothing. But my answer to that is that I published a paper recently showing that there's something called Landauer's principle, which states that if you erase a computer memory, what happens is that you reduce entropy in the system. So you have to produce energy, heat energy, to force entropy to go up again. And this is well known in the computer industry. It's Landauer's principle. So in quantized inertia, what happens is that a horizon forms and it cuts off part of space. So you lose information about space from your point of view. And I've managed to calculate that the energy released looks just like the energy you need for quantized inertia. So the energy is coming from information. So it's not energy from nothing. It's
okay, and thank you, Jonathan.
thanks.
Yeah, let me go to. I'm sorry, I'm jumping around again. We've got a lot. Michael Boyd, sir, can I ask you to go next?
Hello?
Wonderful, sir. Go ahead.
Okay. Hi, Mike. I'm curious to try and understand what relationship is between quantized inertia and vacuum energy. Is it directly or indirectly related?
So the way I think about the Honor effect is it's an excited vacuum. So it's an enhancement of the normal 0-point field. An accelerating object sees a more intense 0-point field than the one that we normally do.
Okay. So would you be knowledgeable about semiconductor physics?
No. No, I did a physics degree, but
do you know like in the photoelectric effect where you have
oh yes, yeah.
So basically you have a valence band and electron and what's called a conduction band electron, And the energy delta between the two is called the band gap.
Yeah.
And, okay, so my question is along those lines, do you think that that the vacuum energy has a band gap, like semiconductor, for example?
No, I'd say it doesn't. I wouldn't say it with 100% certainty, but I don't see any reason for the vacuum to have a band gap.
I've asked Hal Puthoff this same question, and he said no, doesn't think it has a band gap.
I think it'd be quantized, but no band gap.
So, well, for example, matter, any kind of matter, has a band gap. So, like a silicon crystal has a 1.1 EV band gap, and then like a piece of carbon, like a diamond, has a 5.5 EV band gap. So in a gas, like hydrogen gas has a band gap too. And so that's why that kind of gives you the context of why I'm asking about. So there's basically nothing there in the vacuum to create the energy. Would you agree with that?
Well, yeah, there's no band gap. It's a very simple system as far as I've assumed so far. I don't think I can prove it to you, except that the theory assumes that there is no band gap, and it seems to predict a lot of things. So
yeah. Well, Michael, thank you. Let me move along again to Morgan Lynch, and I should apologize. They're starting to pile up on me, so I want to move through them. Morgan, are you there, sir?
Yeah, I'm here. Can you guys hear me?
Yeah, wonderful, sir.
Yeah, hi. Hi, Mike. Hey, this is my first time actually seeing you speak. I've been following your work. Actually, I think it's really interesting. I would say that I had a very nice discussion with Ulf Linhart at the Royal Society about a year and a half ago, and he had been proposing that there's this cosmological constant which comes from like basically a Hubble scale Casimir effect. And so I really like this idea that you're doing with this Unruh effect. I think it's actually really interesting. What I wanted to ask or maybe recommend, so you are proposing that you can produce a thruster based off of this essentially asymmetric Casimir effect based off of a Hubble scale and a Ringler horizon. And what I wanted to propose to you actually, which might be a fun idea, is to look for an analog gravity model of what you're describing. You know, what we all want to look at is advanced propulsion, right? And you might be able to actually find an analog system where you can realize what you're proposing. You know, I don't know if it's Bose-Einstein condensate or water or some sort of nanophotonic system, but there may actually be. Do you understand? You know, these guys in Nottingham and all of this stuff. I think you know you might be able to find a system to realize these things. I think it's a really cool idea.
Yeah, Ulf Leonhardt. I love his work. So he was at St Andrews, I think, before, but now he's
nice. Okay, cool. Yeah. So I think this is really cool. I think but like in terms of like a proof of principle, I think you actually might be able to really kind of like hit one home with these things. So it's I'm looking forward to see what you guys are doing in the future. But I support what you're doing.
Okay,
it's really cool idea.
Yeah, analogs.
Well, wonderful. Well, thank you, Morgan. Thank you. Let me go to Hector Serrano, who is brewing espresso, but actually has a question. So go for it, sir.
Okay. Hi, Mike. I just got a very simple question. Who's the project manager at DARPA?
Oh, it was Mike Fiddy.
Who's his replacement?
Rohit Chandrasekhar.
Oh, wow. Okay. Now I know. Okay. That's all I asked.
Okay.
Thank you.
Oh, okay. Thank you, Hector. Let me see. Oh, Jeremy, would you like to go again, sir?
I would. Thank you. So I have a question, and it was about isn't the Schwinger limit the band gap of the vacuum in a sense?
I'm afraid you'll have to explain the Schwinger limit.
So the Schwinger limit's like we were talking about that band gap, and the band gap being the Schwinger limit would be that's like the limit where, say, if you have a high energy gamma, that it would the limit where the energies would produce particle and antiparticle production. It's that limit where you actually you can have coupling of matter and energy in the vacuum.
Oh, I see. So that's really huge, isn't it?
It is, I believe. This kind of relates to what I believe our last speaker was talking about with the solitons and the production of what he was referring to as solitons. And I had mentioned about we had talked to you share some of these links on Twitter about the polaritons and stuff. University of Rochester is doing some interesting work with producing negative mass and negative energies and stuff in the laboratory with polariton and polariton condensates and stuff like that. I'm wondering if this might be like what's going on inside, these skin coatings and stuff. I don't know. This is what I've been researching lately in any case, but I don't know. Do you have any comment on that?
No, not at the moment.
No, not at the moment. Some stuff to look up though.
Okay.
Yeah, I'll look it up.
Okay, Jeremy, let me mute you back out. Sorry, I'm jumping around a little bit. Oscar, and I'm not sure what your question is, but would you like to go, sir?
Yeah, well, I wrote it in the chat. Hi, Mike. How are you?
Yeah.
Long time no see, but yeah, I'm really pleased to see that the project is advancing and the California connection is working well. I have a question. I mean, I fully agree with you. I really love your QI theory about galaxies rotation and the radiation. We spoke about this probably 1 year, a year and a half ago, but I still don't see how a metal plate can dump the inertia. And as you said, the plant won't be smashed on one side of the vehicle if the vehicle is a metal shape that blocks all the radiation from outside, because that contradicts a little bit the experience that we all have, that even in a submarine or even in a space capsule, you are subject to inertia.
Yes, but I'm saying that inertia is due to a gradient in the quantum vacuum. In acceleration's case, an energized quantum vacuum. So a gradient will apply to every object within the spaceship and the spaceship equally. So it applies to every single atom in the volume equally. So there'll be no difference between the motion of all the objects. So the plant will not be smashed.
Yeah, but why we are not seeing that in our experience? Is because it's macroscopic, or because the thickness of the walls are not thick enough?
Oh, because well, normally what happens is that if you accelerate in one direction, a horizon appears in the opposite direction, which pulls you back. And if you accelerate at a very fast rate, the horizon is pretty close. Sorry, my camera's frozen up. It always does this after 1 hour. Maybe I should answer this question, then log back in. But yes, if you accelerate rapidly, your horizon is close and there's a huge acceleration on you from the horizon, pulling you back. But if you're able to control the horizons yourself, you can stop that from happening. You can put horizons wherever you want.
So that means that at low acceleration, we could see that effect, but at normal accelerations, we are not seeing it.
You should see it at all accelerations equally, but I'm saying that you can add synthetic horizons to offset it.
Yeah. Now, Mike, would you like to log back out and log back in?
Yes. Yeah. Okay. Sorry about that. Happens in my camera every hour.
No worries at all. Go for it, sir.
I'll see you soon.
Okay, and everyone, I hope I'm doing okay with the questions. Let me see. So let me see. So I guess we have Eric next, and then Michael Himes. Do you have a question, sir? I notice you keep unmuting yourself.
Yes, it's about the M drive.
Ah, okay. If you can give him just a second till he's back on.
I kept losing my train of thought. I meant to ask him another question, and then I forgot what it was by the end of it, and I'm like, I'm rambling now. All right. No, but I remember what it is now. I wanted to ask him about his new paper on VIA. So,
Okay. Well, yeah. So let me get, we have Eric, and then we have Michael Himes. I want to get those two gentlemen, if that's okay, Jeremy.
No, I'll wait in line. I'm not rushing to the front or anything. Just popping in to fill the time while we're all sitting here, on downtime, dead air.
Oh yeah, no worries at all. No worries at all. I'm really excited. I think we have some really exciting guests and some big ideas too this week,
Yeah, I believe that Mike, well, it's a kind of topic because this is about propulsion, but QI has also implication for low energy nuclear reaction. In a paper, I think that there is a paper that Mike wrote about that, the hydrogen's atoms get enough force to smash together in small cavities, and that could explain why some crystal lattices can create nuclear fusion of hydrogen inside the
lattice fusion.
Yeah, low energy. Yes, low energy is cold fusion.
Yeah. No, it's interesting. Yeah, you mentioned that, and that's been picking up over the last year. I've been hearing more about. I think they're calling it lattice fusion these days, right? They change the name every year. They gotta stay one step ahead of the debunkers. So.
Yeah, it's because cold fusion had some implications that everyone wants to avoid. So that's why they're trying to find alternative names for that.
Yeah. Okay, and we're still waiting for Michael.
I think that Mike should get a new computer, new mic, microphone.
Yeah, I think. Yeah, well, and again, I should apologize to everyone for interrupting earlier. I thought the hum might be that it was too close to his fan, but maybe something else was going on. So. Yeah, and we can give him a few more minutes, and if he isn't able to log back in, that's also fine. I know, I'm just glad that he was able to give us. Well, he gave us a lot of his time, and we also did a good Q&A session for him as well. We do have a few more, and then we have Jeremiah also. And let me see. So we do have Jeremiah. I have a question from Ziggy. I have a question from Eric. Question from Michael Himes. We'll probably do Michael first, and then Eric, and then Ziggy. So.
As you know, the M drive went to China.
No, I didn't know that.
Yes, and the Chinese built a whole UFO system based upon the M drive physics. Now, Mike was right about band gap. Copper, as a metamaterial, has a band gap, and the valence electrons, when accelerated in a scalar field, shed photons. It dumps mass. And all of this surrounds that. Most people don't consider things like crop circles, where you have the alpha wave ring current coming from the resonant cavity of the Earth. It's an Aether effect, but it's stirred by the scalar resonance spin in the of the transmitter. So you got this little vehicle hovering over the crops, and it's transmitting down to the ground. It penetrates the ground, and it stirs the alpha wave ring currents, which returns, and it's huge. It's like a huge dump of current.
Okay. Well, Michael, let me apologize. Mike just came back in. I have to find him. There we go. So, Michael, would you like to ask your question to Mike McCulloch now?
I don't know whether he is aware of the link, the LC circuit of a transmitter in a scalar resonance with the ground, or the mirror image that the scalar resonance produces. So I would like to know if he can link those two things together.
Okay. And Mike?
I'm not sure I understand the question. The LC circuit?
Oh, yeah. He was asking about, Michael, you were asking about the M drive, right?
Right. It creates an LC circuit with the ground. It's a resonant circuit.
Oh, you're suggesting another reason for the thrust?
Yes. Are you familiar with the alpha wave ring current discharge? Look at a crop circle and see what happens under the little vehicle that makes those suckers. That's an alpha wave response.
Okay,
It's
I've heard of
right up from.
Okay, and is that something, Michael, could you spell that alpha wave? It's
ALFVEN wave ring current.
Thank you, sir.
Totally overlooked by physics. Everybody's focusing on a vehicle. It's not just the vehicle. It's what happens around it.
Alpha wave ring current. Okay.
Right.
Yeah, that's something I think we'll all have to end up doing some research on to understand where you're coming from.
It's so intense. The radiation is ionizing. There is a Z pinch in the return. It is huge.
Oh, actually, it looks like Jonathan Lane knows about it too. Alphenic wave ring current. Okay, well, so let me go to Eric Hermanson next. So Michael, thank you. Let me go to Eric.
Hi, Michael. How you doing?
Hi, yes.
Hi. Could you put up the slide with the Becker bot experiment?
Yes.
With the 100 Newton response?
Yeah, hang on.
You know, and I should mention for the Q&A session, especially because we ended a little early, just let us know. You know, we don't have to go a full hour, or we can go. We're flexible on time, Mike. So whatever your schedule looks like.
Okay, I'm okay at the moment. It's getting on towards midnight here, though.
Oh, are you're in the UK?
Yes, I'm in the UK.
Oh, you're in Plymouth in the UK. I thought you were in Plymouth, Massachusetts.
It's 11:10 now. Yeah, so is that the one you wanted to see?
Yes. So so obviously this one experiment was the results were much different. They were about 1,000 times better than a lot of the other experiments.
Yeah.
First of all, and the setup here was sounds like it was basically a capacitor setup. Was there a dielectric in the middle?
Yes, there was a dielectric of polyethylene, I think.
Polyethylene.
Yeah.
Okay. Was there a reason that you chose that, or?
Becker and Batt chose it to encourage field emission of the capacitor. So they point out in their paper, this is quite it's quite important that you get a field emission. So they took sandpaper and they roughened the capacitor plates, for example, to encourage field emission.
Interesting. Okay, and did it work with an air gap, or did the dielectric in there need to be in there?
No, the dielectric. Well, I'm not an expert on capacitor, I should say, but I think if you have an air gap, you get ionic discharge, which is not what you want. You want field emission instead.
Okay. And can you go to the next slide where you had the plate behind the device? I think it was one more slide further where you had.
Oh yeah, this one.
Yeah, that one where. So I'm trying to understand what's going on there. So without this plate, so they were like holding a plate behind the device, and something would happen, and they took the plate away, and something else happened.
Yes, they saw two different effects. What happened was that when they thickened the cathode, like I've shown here, the force reduced. When they put a plate disconnected from the cathode into the space, the force reduced much more and reversed.
Okay, so the plate was connected to the cathode. It was in the circuit.
Yes, it was electrically part of the cathode.
So the plate that you showed behind this box in one of the versions of this slide, that plate is actually in the circuit touching the cathode?
No, that's not touching the cathode.
Okay. So so there's a metal plate behind here right now. And so is this causing anything bad or good to happen in this configuration?
You mean in the schematic?
In this schematic, when the plate is there, what is happening with the experiment? Is the experiment running at full?
The experiment is now behaving as if that plate was not there at all, because it's behind the Rindler horizon that the electrons see. So from their point of view, that plate does not exist.
Okay, now you're saying that if you take a wire and you connect that plate to the cathode and leave that plate in the same spot, something else would happen then?
I don't know what would happen. So it should also have a null effect. So it shouldn't have an effect at all on the electrons, even if it was connected to the cathode, because it's behind the Rindler horizon. So you have to assume it doesn't exist from the point of view of the electron.
And how far back is that horizon? Is it like an inch or is it like 10 feet?
It was about 2 centimeters. Calculated 2 centimeters.
Okay. Yeah, I'm going to need to read this paper, because I don't know a lot about how these horizons work. But do you have any ideas why this one experiment was so much more powerful than the other ones? Was it?
Yes.
Is there any ideas so far?
Yeah, it follows from the theory, because the thrust is expected to increase as you increase the acceleration of the core, if you like, the material you're accelerating, and also it increases as you reduce the size of the cavity that it's confined in. And I mean, I'm not an electrical engineer, so I would not have guessed a capacitor would be the best way to do it. But Becker and Batt were engineers, electrical engineers, and this occurred to them, obviously. So the gap here is about 10 micron, and the acceleration of electrons is about 10 to the 19 meters per second per second. which is absolutely huge and far higher than the accelerations I was able to get in my light-based experiments.
Okay. And you know, this is probably easy to build. Has this device been tested any other time than this one time?
This has been done several times actually over the past few decades. A similar test was done by, I think his name is Takahashi Musha, a Japanese person who did basically the same thing in 2008, maybe. I think it was 2008. And it's been done by NASA, Canning, 2003, and other times as well.
Because this will lift off the ground clearly. I mean, this can lift at least 10 kilograms off the ground, right?
Yes. Well, if we can confirm it, it means we can launch with this. So it's a very important thing to look into.
But I'm just wondering, did they flip it upward and turn it on and see if it jumped off the table? That's what I would have done. But I guess they didn't do that. But no, all right, well, I'll look at the paper. Thank you very much.
Yeah.
Thanks, Eric. Oops. Okay. And let me see. And actually, I think that probably answers several questions. I had several people asking about, Wayne was asking if the yellow block is a metal electrode, but I think a couple other folks were also asking about an experiment they could build. It sounds like this, Mike, it sounds like this block, this experiment that you have right here is maybe one that folks might want to attempt, or?
Yes. I guess you have to be careful with safety because it's 5,000 volts, isn't it? But
well, that would be the question then, because you've mentioned, and I should apologize for talking so much, but you've mentioned that B-field Brown and several other effects over the last few decades. But if people were going to build one specifically to test this, the experimentum crucis, then adding the event horizon to what appears to almost be like an asymmetrical capacitor, that sounds like that would be.
It's actually a symmetrical capacitor, this one. Well, the initial experiment was. When they changed the cathode, it wasn't. But
okay, yeah, well, thank you. And the reason I ask is Jeremiah and Mark Sokol and several others in our group are actually building things. So we might have some folks who could do some experimental validation. And
yeah, that'd be fantastic.
Oh yeah, absolutely. Okay, well, oh, and Jeremiah had it. Okay, Jeremiah, would you like to go next, sir?
Yeah, can we shoot back to that other slide with the high-density polyethylene sandwich between the plates?
Well, I don't think I show it actually in detail.
Yeah, that one. Yeah, go. Your experimental test. You had the thing about. I just wanted to also understand exactly how this system was exactly configured. It looks like on the scale you had two plates that were directly in contact with that polyethylene, and I'm just trying to figure out like what exactly is different between your experiment and just simply a parallel plate capacitor. I unfortunately I missed a little bit of your presentation earlier, and I apologize for that. So I really want to grasp what you're showing here, though.
Right. Well, I'm not an electronics expert, but the dielectric, it has to be quite subtly done. So that you put the dielectric between the two capacitor plates so that you get field emission and not discharge. Field emission of electrons.
Is what we're looking here on the bottom in that diagram, is that effectively what was on top of that scale?
Yes, that's right.
And then what's the gap between those two, what looks like metal plates, the gray bars? There's a dielectric between those?
That's the dielectric, which is polyethylene.
Okay, and what's the yellow part then? That's just
this is just my attempt to represent the energy in the Unruh wave field.
Oh, okay. Thank you so much. That really helps. And what's the black line there? Just the end of the field?
That's the Windler horizon. So from this accelerating electron's point of view, that is the end of the cosmos.
Thank you. Yeah, that really helps. For some reason, I didn't quite catch that. So I'm sorry if you already explained it.
My
Thanks for covering it again. And did you test with various voltages and see how that responded? You know, what kind of results you got? How does voltage affect it?
Yeah, they did. And also Takaaki Musha, the Japanese experiment, they found that using, this is interesting because Paul LaViolette mentioned it in his talk, using pulsed DC multiplied the force by a factor of about 4.
And I'm guessing like that would make perfect sense within even the theories that we're familiar with, where in the asymmetrical emission, anytime you have a transient wave that has an asymmetry, you're going to end up with a radiated power that's not symmetrical between the positive side, the electron acceleration and the electron deceleration. So that's unsymmetrical radiation and should equal the force.
Okay. Yeah.
Wonderful.
Thank you. I appreciate it.
Thank you, Jeremiah. Okay, let me go to Max next, sir.
Hi, can you hear me?
Yes, absolutely. And could I get you to start your video, Max? That's okay.
I guess so. Sure, why not?
And what was your question, sir? Absolutely.
Few questions. I might have missed if Professor McCulloch had an expression for the distance to the Rindler horizon. And the second question, there was, I think it was a guy named Reda had a paper recently come out with some critiques of UI. I wondered if you'd answered that. Over.
Yes. Yeah, the distance to the Rindler horizon in the experiment was about 2 centimeters. So that's just calculated from the acceleration.
Okay. Did you have an expression for that? Yeah. Okay, so it's just, was it in the charts? I didn't see it.
Yeah, it's there actually. I've shown it on the schematic.
Right, the expression for it, I mean.
Oh, yeah, sorry. That is c squared over a. So it's the speed of light squared over the acceleration of the electrons, which is of the order of 10 to the 19 meters per second. And your other question, yes, yeah, I liked Render's paper a lot. I thought it was very useful. The factor I use in quantized inertia to model the changes in UNRU radiation has always been an approximation, and Render tried to calculate the full expression, and he found it was rather difficult to do.
Wonderful. Okay, well, thank you very much. Let me see. Does anyone else have any questions? Michael, Michael Himes, did you have a question, sir?
Yes. With regard to the dielectric and the capacitor, you say it was polyethylene. Is that a chiral molecule? What I'm hinting at here is, how does chiral spin, figure in the field dynamics of your setup there?
Well, it shouldn't have much of an effect. We're only measuring the force in one direction, so.
Yeah, but the chiral spin can be engineered one way or the other, whether it's right-hand spin or left-hand spin, or a balance of the spins up and down.
Okay, well, I can make a note of it.
Okay.
What I'm building is an asymmetric resonator that is dependent upon the chiral dielectric material between a series of plates.
Are you going to try and measure thrust from that?
I know it has thrust. The US government is building it, and so is China. I had reference to the EM drive. China got a bunch of their physics clues from Schreier.
Okay.
Right.
Yeah. Well, and when Michael, when we go into open discussion, if you're still with us, I would love for you to talk more about that in open discussion in a bit. Let me mute you back out for right now, and we'll
Sure.
see where we're at with questions. I think that Michael Boyd had one more question, and then.
Hello, Mike. Could you go to the prior slide, to this one? No, one more. I passed. It was the one where you had outside the horizon slide. Not this one. I don't know. You showed it earlier. It was
this one.
This one. There you go. Okay, so now I'm trying to understand this. So the orange region, that's 2 centimeters, correct?
Yeah. Yeah.
And that dark black line is the Rindler horizon.
Yeah, that's right.
Which is about 2 centimeters away, and then the 2 parallel plates are have a 5 kV DC pulse. I mean DC applied to it, right?
Yes, that's right. Yeah.
And then that the gap is filled with what did you say, the dielectric?
Polyethylene.
Polyethylene. And do you know, did the dielectric have a certain polarity? Do you know?
No, I don't know.
Michael, if I could jump in really quick, one of the things that Mike McCulloch had mentioned, I believe, was that there's a field effect emission of electrons that needs to happen across the dielectric.
Right. So what I'm trying to figure out is, do you know approximately what the velocity of the electrons was relative to the speed of light in that experiment? Because I could use that to calculate how much inertia the electrons had, for example. So
we calculated quite easily from the acceleration. I can't remember the exact value of the acceleration. It's about 10 to the 19 meters per second, and the distance across the gap varied from.
So that's
10 micron.
It's relativistic, is my point. It's
Yes.
So
Okay.
that those electrons are going towards the right. They're accelerating to the right.
Yeah, that's right. Yeah.
And then that gray region on the left, that's basically a baffle. What is it? A piece of metal?
Yes, piece of metal.
A piece of metal is put on that side, and it doesn't affect the experiment because it's outside that Rindler horizon, correct?
Yes. If it's on the right side of the Rindler horizon, it does affect the experiment. If it goes to the left side, it doesn't affect it.
Oh, okay. So now, you know how Puthoff's hypothesis, I hope, about space-time metrics. He has this thing he calls expanded space-time, and basically, I'm curious if you think that region, the gray part on the right, I mean on the left, excuse me, is in a region where space-time is expanded, so it wouldn't be visible to the observer outside that region.
I'm afraid I haven't read that paper of Puthoff. I read the High Schroeder Puthoff paper, and a few others of Puthoff.
Okay, I'll try to put a link on the chat so you can check that paper out. And thank you for your time.
Thank you again, Michael. Okay, let me see. Let's do Thomas Anderson, and then again, Mike, how are you doing on time, sir?
I'm fine to go. I'm good to go at the moment. So.
Okay, well, why don't we do Thomas Anderson, and then maybe he'll be, if it's okay, unless you'd like to stay and do more questions. Well, I have a couple more, but let's do Thomas Anderson then. And sir.
I was just going to say on the capacitive plate, I'd like to make a suggestion rather than a question for those who might be attempting to replicate this.
Yeah,
or future attempts at rebuilding this too. Have you looked into triboelectric effect?
Triboelectric.
Right, because polyethylene has an extremely strong negative triboelectric effect, right, where it readily builds up a negative charge on its surface. But if you were to layer that with like another dielectric sandwich together, like say polyurethane, which has a propensity to build up a positive charge, so that you can kind of like cut down on the amount of power necessary to generate your positive and negative charge on your plates, and see if that might have any effect, because it also might help retain the effect, since you're saying that you're wanting to try to avoid a discharge effect where the energy is being, I'm assuming you mean by discharge, you mean like a coronal effect?
Yes, I think they try to avoid that.
Right.
So that use different dielectrics to cancel each other out in terms of charge.
Right. That might, I'm just thinking that might help, and it might help kind of shortcut the need for the nanomaterials to at least get a good start on like establishing the technology, so that the nanomaterials would then, follow afterwards, because it'd be like, well, if we can improve this to make this even better, why not invest the energy and the time, just like we invested so much energy and time in electric motors that we've gone from a little spinning wire on a mercury pool to driving electric cars now. So.
Yeah, okay, thanks. That's a good suggestion. I'll make a note of that as well.
Thanks for hearing. So.
Thanks.
Okay, let's go to Jeremy Reese next, and thank you, Thomas.
Hey, Mike, I had a question from our live chat from, what was his name? Oh, sorry. He wants to know, when I find his name, he wants to know if you can talk more about general relativity and how your theory fits in with Einstein. Because our last speaker threw Einstein in the trash, and we want to know, do you keep GR, right? And your theory is in accordance with GR, right?
Yes, it is in the solar system. So what it looks like is, okay, so Einstein in 1911, he came up with an early version of general relativity called the variable speed of light version of general relativity, but he made a factor of 2 error. So he got rid of this theory and went on to a geometrical one using a space-time metric. Much later, Robert Dicker in 1957 rediscovered this theory and corrected the factor of 2 mistake, and found that this theory actually predicts everything that general relativity does in the solar system. So the bending of light by the sun, the delay of light in reflection from Venus, and tests like that. So this is called variable speed of light general relativity. And this past week, I've shown that I can derive this from quantized inertia. And it's exact in the solar system. But the great thing is that, unlike general relativity, which cannot predict galaxy rotation, this new version of general relativity can also predict the galaxy rotation, as well as as things like the bending of light by the sun. So anyway, I've just written a paper about this and I'm about to submit it.
Oh, actually, I find that intriguing. I had no idea that he published another paper. So is it okay to ask you, could you describe that in a little bit more detail? You said Einstein, a variable speed of light theory of relativity?
Yes, that's right. So he considered the speed of light, so c is f times lambda. And if you assume that time slows down in a gravitational field, that reduces f, but also because distances shrink in a gravitational field, that reduces lambda. So the speed of light close to masses decreases. And this accounts for the fact that it bends around masses like the sun. And it predicts it exactly as well.
Oh, okay. Well, thank you.
Yeah.
I'd never even heard of that before. So
I liked it right from the beginning because it fits more with my theory of quantized inertia, which uses a flat space. And I don't like bent space because you can't directly test it.
That question was from Greg Chase, and he says, "Thank you. Let's hope it gets published."
Does anyone else have any more questions?
That question was from Greg Chase, and he says, "Thank you, Michael. He let's hope it gets published."
Jeremy, do you have any more YouTube questions?
One more question from YouTube I have one from Gardy Pierce. He wants to know: is there an implosive technology physics division degree? I'm not sure what that means. And
is he referring to Schauberger, who had an implosive device?
Yeah, I think that's what he means. And then I think he had another question about what are correlations with cavity structural effects, quaternion spinners, and Hopf fibrations?
Oh, I don't know. I don't know about that last one.
I know about Hopf algebras. I'm going to have to look that other Hopf fibrations. I've never heard of that before. I'm going to have to look those up. And I've heard of direct spinners, but
chaos theory or something.
Because I was like, you know about Roger Penrose's twister theory, right? That he published in 60. He started that in 67, but then I guess they're saying that that's just direct spinners reinterpreted or something. I don't know. But interesting stuff.
That doesn't seem to be testable to me.
You get lost in a lot of math, yeah. But we're building stuff, and we're going to test it, and this is awesome, and I hope you get that published. One question from Peter Middleton: is the gray metal plate charged on the far left, and plus or minus? And if so, with what voltage? So the gray metal plate on the left. So that one that's beyond the Rindler horizon, that plate, is that charged, or what are you doing with that plate? Is that grounded? Is it just, what do you do with that plate? And then
I'm afraid I don't know. It's all in the paper. I think it's probably grounded, but I'm not sure. I better not speak if I'm not sure about it.
Excellent. All right.
Wonderful.
Well, trade secrets.
What, Jeremy, was that everything from YouTube,
or is it just neutral? Yeah, that's what he was asking. But yeah, I'm not sure. You could probably do a lot of different things with it, and it might be different for different sides of the craft, depending on what side of the craft that's on. Because I assume that if you make the whole craft out of that material, then it's going to be different on different sides to get an asymmetric effect across the craft in order to.
Well, I know there's been a lot of excitement about Mike's theory. There has been a lot of excitement. I've gotten several, probably 5 or 6 emails that immediately come to mind from people who were like, wow, we're really excited that he's coming on to speak. So I would love for some of the folks who are excited to test this, to build tests and hopefully support his model, and and then hopefully find things that maybe could elaborate on, right, to refine the theory or come up with next steps for it.
That would be a real help. Yeah. I mean, people like Frank Becker coming in with an experiment was a great help.
Yeah, well, and hopefully Mark and Jeremiah, in fact, Jeremiah is on next, so hopefully Jeremiah will promise to do an experimental test on this. And they do really good work, and they do good measurements, so.
Thank you, Mike.
Thanks. So let me see, and it's 3:41 now. Are we all set, guys, for questions? I think Jonathan Lane had one more. Why don't we finish up with Jonathan Lane? We'll be at a few minutes ahead of schedule for. Go ahead, sir.
Okay, so one question about the comparisons with general relativity. You'd mentioned in I believe it was on Twitter that wormholes would not exist because space would be flat, but that it would be possible to create a horizon effect that would allow you to jump over space. How would that work?
Yeah, so I'm a very strong follower of Mach, and his kind of idea was that if you can't in principle measure something, then it doesn't exist.
Mm-hmm.
And this is why I like horizons very much. It's like the slide we're looking at now. That plate on the left does not exist from the point of view of the electrons that are accelerating so rapidly. The Rindler horizon has effectively chopped off part of space for them. So, I mean, I don't know exactly how to do it, but if you could arrange horizons to chop off part of space, then you could simply step over it.
Okay.
That's the idea.
Okay. So thank you, Jonathan. So I think with that, or actually, you know what? Let me, if it's okay, Mark had a question, and Wayne actually had a question as well. Mark, would you like to go, sir?
Oh yeah, thank you very much, Mike, for putting this presentation together. I missed a little part of it, but the part about the parallel plate capacitor, or the asymmetric parallel plate capacitor, is that just a asymmetric parallel plate capacitor charged up, or is there anything else that we'd have to add? Because this is something that I've already tried in many variations.
Yeah.
I believe it's symmetrical, Mark, and that's my apologies. I said asymmetric, but he said symmetrical.
It's symmetrical, and you need a dielectric between the plates to encourage field emission, and you don't want to have discharges, ionic discharges. You want field emission of electrons instead.
So a high K dielectric like CCTO or barium titanate?
I don't know. They use polyethylene, so something like that.
That's a high strength dielectric polyethylene that would withstand, but it doesn't have a high K factor. It doesn't like accept a lot of charge.
Mark, do you think that you guys could build something like this as a test?
Yeah, I can actually chime in here too. As far as why to use polyethylene, take for example some of the test data done on polyethylene and Teflon. Teflon would in fact be possibly even better, because those dielectrics, although they don't have a very high K, they have an incredibly fast RF response, which is why they're oftentimes used in the jackets of RF cables. Because they can basically take those kinds of transients. So it would really be ideal if you're trying to create a wave front from one side to the other that's effectively fast and has a very sharp transient, then those materials are not going to eat that transient up.
Oh, so this is a pulsed parallel plate capacitor, right?
Yeah, that is a good question. Would you mind, Mike, answering how these capacitors are driven? What kind of waveforms are input into these devices?
Oh, it's just at the moment it's constant, but the experiment I described by T. Musher, he used pulsed DC, which he found increased the effect by four times.
Do you have any idea as far as what kind of frequency he was pulsing at, or what kind of rise times he had?
Do I have the paper here?
Oh, you do? Well, that's convenient.
Yeah.
Yeah, we're wondering about the symmetry of the waveform, whether it was a sinusoidal or an impulse type waveform.
Yeah, let me just stop screen sharing for a minute.
I did see something in the slide deck that made it look like it was kind of a pulsed sawtooth wave, which reminds me of the flyback stuff that we are all very familiar with.
Yeah, sorry, I can't find my copy of it. So, but if you could email me, I'll try and send a scanned copy to you.
Thanks, we appreciate it. That sounds good. No problem.
Yeah. Sorry about that.
Thanks again, Mike. Well, let's do this. Why don't we? I think that we're all pretty much set for questions.
You're here about the motor?
Oh, sorry about that. Okay. I think that we're all pretty much set for questions. So why don't we?
Eric Hermanson, question.
Oh, okay, Eric. Why don't you go real quick, and then we'll call it a day with that for the questions.
Okay, Mike. So I don't understand horizons well, and so this might not be a valid question. We can talk about it next week. But you know, I'm thinking about this, and as a particle moves and things vanish behind it, correct? The
yes,
the information behind it. And so, you know that I'm not a fan of the quantum vacuum, because there are celestial photon studies, transit studies, that show that there's no fluctuations happening that cause the photons to arrive with dispersion or anything like that. But let's assume that there are fluctuations. These fluctuations must be keeping particles stable, particles that can decay. If the vacuum's at play, then they're probably contributing to the stability of radioactive particles. And so if you have something that can decay, that's moving or accelerating, and you cut the legs off.
No.
I mean, so in other words, won't decay rates start changing if this was really happening?
Yeah, that's the prediction. That's a good point you make. It is a prediction of this. Yeah.
It really. Okay.
Yeah, I hadn't considered that before, but yes, you're correct.
Like, would it be a huge, like a minuscule change that would be very, very hard to detect, or would it be something that people really haven't looked at much yet?
I would expect it to be fairly small, depending on the acceleration you impose. I mean, I guess if you had a particle moving around the collider at CERN with a very high acceleration, it might become observable.
Okay, so we're talking about collider level energies, not not these experiments here. We're talking about CERN type stuff. Okay. All right, that was it. Thank you.
Thank you again, Eric. Okay, well, let me see. Why don't I mute everyone? Okay. And I will go to gallery view. And everyone, let's do a giant thank you again for Mike. Mike, thank you very, very, very much. That was an amazing presentation. That was truly remarkable. Truly remarkable. Okay, so I think we are all set. So again, Mike, thank you very much for presenting today. And let me see, I guess we will go to Jeremiah next.
All right. Let me see if I can get this to work correctly.
Wonderful. And Jeremiah, I should apologize for jumping in a little early. Mike wrapped up his a couple of minutes early, and so we did just about an hour of Q&As. But so I think that we're actually on schedule, even though we're 10 minutes ahead.
All right, let me see if I'm not sure which screen is being shared. I'm pretty sure it's okay. It looks like it put a green border around it, so that's good. Okay, I can jump right into this then. Can you guys see this? Hey Tim, can you? Okay, it looks like Mike Hines is saying that you guys can see the screen then. Okay, awesome. All right, jumping right into it. Let me go ahead and present this. I have never used Google Slides before, so this will be my first run with it. Hopefully it turns out well. All right, reactionless electric field thruster is an investigatory cross-comparison of various gradient field drives. So gradient field drives are an interesting concept. They go back to T.T. Brown's work all the way into 1928. The tech has been around for more than 90 years. There's still not a product on the market that you can just buy off the shelf utilizing this technology. All the recent patent applications that have been filed for gradient field propulsion have pretty much been denied or abandoned. And the modern revisions since Brown kind of started in 1989 with LaForge, and they've continued to this day. The great thing about this tech is that it's extremely simple in principle, although it does require some dangerous high voltages. And the dielectrics can be expensive in small quantities and hard to acquire. Plus, in order to get really high dielectric constants, which are required for gradient field devices, you usually need industrial ceramics processing techniques. So there have been a few inventors that have pushed through for patent applications. None of these were granted, unfortunately, but they contain really interesting and fundamental refinements of T.T. Brown's work that actually offer us some real and engineerable factors on what we should look for and how we can make these drives. So here's some of the claims. Terence Bates' patent application, a practical high thrust engine or thruster requiring neither propellant nor reaction force from the environment. It takes advantage solely of the relatively well-known electrostatic field equations between pairs of substantially concentric cylinders or spherical electrodes. The Sikas, which I can't believe is in the audience today, pretty incredible. He also says the method and mechanism for developing a thrust by means of a system consisting of asymmetric capacitors, which are created along a set of charged metallic elements placed in a non-symmetrical way within a strong insulating dielectric. And so we basically see that there's a consistency here. Even Douglas Torr, an invention relates to an inhomogeneous electromagnetic field. In particular, the generation of these fields will result in a gravitational thrust. So here's systems that can effectively produce a force, freestanding force without reaction mass, without propellant. And what these are not are what we have pictured here. This is a lifter. It's an ion-propelled aircraft. So a lifter accelerates atmospheric gases, and it requires a reaction mass. Gradient field engines do not require that reaction mass. So here's a basic overview of how these devices work. We can see here that we have on the top half here, a high K, high mass dielectric, and on the bottom half, a low K, low mass dielectric. These two dielectric layers with different masses and different K factors are sandwiched between two cylinders or two spheres. So the internal cylinder or sphere forms one electrode of the capacitor and the outer forms the other. This is an end view we're looking at. Of the inventors that have pumped these devices out, we have quite a few variations from LaForge to Terence Bates, Douglas Torr, Nasikas. And if you take a look at all these designs, you basically see something very similar. We have either two different dielectrics like we have in Terence Bates and Douglas Torr, or we have a gradient dielectric like we have here with Nasikas and T.T. Brown. And these same structures, like we see it here in figure 5, and in this picture over here, we can stack these structures up in big arrays in order to amplify the force according to the inventors. So everybody's kind of got their own theory on how this stuff works. Brown's been around for a while, and he is pretty much the initiator of this technology, one of the first people to ever discover and come across it. But it's been a big issue of speculation forever, exactly how Brown's thrusters supposedly worked. So Bates says that the key to making these devices work is by having a very high K dielectric on one side and a very low K dielectric on the other. Well, Torr emphasizes that it's not just the K factor of the dielectrics that matter, but it's also the mass difference in the dielectrics. Brown says that it's mainly about the shape of the dielectrics and the shape of the electrodes, or how massive they are. And Nasikas really tells us that we need to minimize the distance between our wavy capacitor and our flat plate and maximize the potential between those two plates, which means we need a very high potential insulating dielectric. The good thing is, although the theories kind of disagree with each other, they all do agree in some ways, and that is they all require asymmetric electrodes or asymmetric dielectrics. They all state that a higher K equals greater force, and they all make use of gradient fields. So Jean-Louis Naudin tested this idea that we see in our pictures here. He tested this idea with a foam block covered in aluminum foil and a piece of high density foam on one side of this material and air gap as the other dielectric. Now with this system, where you have foam as one dielectric and air as the other, in a system which has symmetrical spacing between top and bottom, there is in fact a small thrust produced. However, if you fill that same gap on the right picture here with that same K, same mass dielectric, the force completely goes away. So this was a great way to actually test, and I'm glad that he verified this. So in terms of my testing in gradient field engines, I just wanted to point out some common measurement errors that I see people make all the time. And that is having your test device located on the scale, on the countertop or the table, just inches away. You have electrostatic forces that are in the kilovolts range, and they have significant attraction to all nearby surfaces. So here's one of the setups that I use. I have a Faraday insulated scale that's completely covered in aluminum and copper tape, which I set on top of a grounded shielded platform. I suspend my test sample from a suspended platform, which is at least 2 feet or more away from the floor, walls, and the scale through these thin wires, filament wires. I make sure that my HV source, which is a multiplier built on board this test stand, has a very, very short lead wire from the output going to the test sample so that we don't have contributions of wires being attracted to nearby objects, and we don't have leakage currents that are present. So all these things help us get a much more reliable test, and they help reduce the sensitivity of electronic or digital scales, which are really a problem when trying to take measurements of electrostatic systems. So Alexander Frolov definitely deserves a mention with gradient field drives. He came up with a very simple system of 2 electrodes mounted on a piece of dielectric material, the other side open to the air, and some kind of divider between those 2 pieces of dielectric. So I tested a variation of this device of what Jean-Louis Naudin called the Frolov's hat. The device statically weighs 82.2 grams, and when it was charged to 80,000 volts in my test stand, 2 feet away from the scale, I did not receive any forces above 0.1 grams, which is the minimum resolution of my scale. So if it did produce a force with no corona, no ionic leakage whatsoever, then it was below that resolution. So we know if it produced a force, it was very, very small. However, our other affiliate labs had also tested this device, and they did receive very small forces in the prediction, in the direction predicted by Alexander Frolov. But we have not concluded the testing on Frolov's hat yet, and we're still looking into other alternatives. Ultimately, we don't think that the use of air as a dielectric is a very good solution for pursuing these drives, so we're moving on to better ideas. I also tested LaForge's idea of a directional thruster. In this case, I used a wax mixture with titanium dioxide powder. And as you can see, the design I have here pretty much matches the geometry of what he's patented. I did reduce the length of the pole legs a little bit because according to Jean-Louis Naudin, the poles did not need to be as long as pictured. But in this device, I was noticing 2 gram spikes. I started out at 0 volts and ramped it up to about 65 kV in 10 gram increments. And every time I would ramp up, I would notice a little spike of thrust, which would quickly go away. And finally at 65 kV, the device started breaking down. So I retired this device. Wax is a pretty crappy dielectric, being honest. And so I'll be moving on to better experiments as well. I also tested other gradient field thrusters like this one pictured on the left here. This is a T.T. Brown style tapered dielectric. And this system actually does produce a very small thrust of about 0.05 grams. Again, it's wax and titanium dioxide, so it has a pretty low K, but it has a reasonable dielectric insulating factor. So it's not a force strong enough to really pursue. So we're giving up on these types of single dielectric gradient field drives for the time being. I wanted to test though the concept. So in T.T. Brown's electrokinetic apparatus patent, he proposes this idea that we see here in figure 8. Here we're looking at a metal toroid, that's part 48, with a metal ball here. And this ball is attached to a high voltage power supply, the other side attached to the toroid. And by moving the ball into or out of the axes of the toroid and keeping the charge the same between the two, he claims that this device will produce a force 54 or 53 in this direction. Now, in my case, I did build a small device like this. I charged my sphere to a negative potential and the toroid to a positive potential and set it up on the scale. In order to keep wires out of my system, you can see here in the picture on the left is a small 25 kV battery powered PSU. It has a small photo trigger right here around where my arrow is. You can shine a flashlight on it and remotely activate it. So in this case, I don't have any wires being attracted to anything. And then here you can see that power supply integrated into the test device case. So in my test results, I was able to receive a small force of about a weight loss of 0.25 grams upwards with the ball facing up when it was negatively charged. And if I flipped it around on the scale, I received a downwards force of about 0.12 grams. The difference between those two measurements is a very interesting phenomena that I'm still looking into. And again, this test setup needs to be put on a torsion balance because I don't feel like I had adequate distance from the test device and the scale. But it looks like Brown may have been right in his patent, so this is looking positive so far, and continued tests are required. Now, it's not just, you know, crazy fringe scientists looking at these ideas of electric field propulsion. NASA gave it a whirl, and in 2000 and 2001, Jonathan Campbell received 2 patents for an asymmetrical capacitor thrust device. And he says, it is well established in the literature that a force or thrust may be generated by a capacitor charged to a high potential. Although there are different theories regarding the basis for the phenomena, there is no dispute that a force is generated by capacitors under such high voltages. But he also admits there is a need for further improvement in the module construction to enable thereof use in atmospheric propulsion or propulsion in space. And this goes in concert with this device that was patented by Jonathan under NAFTA, where a lot of people disagree that this device actually operates by direct forces and say that it's still an ionic force. So there's a lot of debate open on that yet. And we are hoping to close that debate with some better devices. Who else is doing the research? Well, I have to mention Hector Serrano, founder of Gravitech Incorporated, has been developing the technology for a super long time. In 1993, when he was deployed in the Navy, he started playing around with field propulsion technologies by acquiring a hefty, nice CRT power supply transformer from his EE Navy barracks crew. In 95, he finally retired, moved to Orlando, and started shopping at a little hobby store called Skycraft for parts to construct his first field propulsion drive. And then finally in 97, he officially incorporated Gravitech. And by the following year, they had already been doing research in their garage, and he managed to acquire some people to help him along the way. Now, almost 28 years into his research, the newest SFV Gen 3, that's his newest thruster design, is just weeks away from testing. So I've been watching Hector for a long time to see where exactly the SFE is going. And now that we're just weeks away, we'll be watching pretty closely to see where Gravitech is going to take this tech now. And Richard Van Durek also needs huge mention here. He and his team at Field Propulsion Technologies have been working hard to develop groundbreaking propellantless propulsion spacecraft technologies. They claim to have several known working products for spacecraft propulsion based on the interaction of electrodynamic fields using only electrical power. So do they have legitimacy? Absolutely. They were granted several patents on multiple variations of the technology. And DARPA thought they were interesting enough to land several contracts. So because they seem to have the credentials and because this technology looks very promising, I'm personally in the process of independently replicating Richard's earlier tech, his static displacement field drive, and I hope to have test results on that soon, but we'll cover more on that later. So if field propulsion engines or gradient field engines could actually be produced correctly, according to some of the inventors, what kind of forces could we expect? Well, this is actually pretty exciting because if we use some high K dielectrics like 20,000, which right now CCTO gives us a 200,000 K factor, so 20,000 is nothing unachievable. Then with a small micron-sized cable, we can expect that cable to lift more than its own weight. And here he says, since the weight of the cable is less than the net force produced, there is effectively no limit to the number of cables that can be used for lifting purposes because they lift farther more than their own weight. Now that's a hell of a claim for an asymmetric capacitor to lift itself and then some. But it sounds like we're getting into the possible regime of being able to lift their own power supplies. First, we needed some high K dielectrics though, in order to do this. And what do we have available for high K dielectrics? Well, I threw together a chart of everything that we can pretty much buy on the market today. And depending on whether Nasicus or Tor or Bates or Brown are correct, we have a variety of different materials to choose from. So if it turns out the mass of the dielectrics needs to be the most different, lead magnesium niobate at 975.7 grams per mole is a pretty massive dielectric that would be the ideal thing to use. But if the K factor is really critical, then we can use calcium copper titanate as one of our two massive high K dielectrics. And if it is just the density that counts according to Brown, then we can use lead monoxide, the heaviest of the dielectrics I found at 9.53 grams per centimeter cubed. I guess it really depends whose theory is right, if anyone's, and which one will be experimentally proven. So this is what I've started so far. I've acquired some parts for a preliminary electric field thruster. I managed to find some hemispheres online, which you can simply purchase. And this is great because it makes them easy to replicate if this device turns out to work. So you can just buy stainless steel hemispheres and hollow spheres online for pretty cheap. Here on the left picture, I've taken one aluminum foil hemisphere and a dresser drawer handle and encapsulated the low K, low mass dielectric, which is just epoxy in my case on one side. And on the upper side, I'll be adding a mixture of CCTO and epoxy. So to figure out what kind of gradients I'll be looking for, here we can find out that you can actually make your own high K dielectrics yourself by mixing high K dielectric powders with regular epoxies. So in this paper here, there is a pretty good instruction manual on exactly how you can pull that off, but it does look like it's possible just to mix in dielectric powders with epoxies, and you can do this at home. And so according to what I've calculated out, if I use the materials that I've already got here, CCTO as a dielectric and EC690 as my epoxy mixture with these stainless steel spheres, about 60 millimeters in diameter for the ID of 1, 30 millimeters in diameter for the OD of the center sphere. I have a dielectric ratio of about 6.16 to 1. I have a K factor of about 600 to 1, and I should be able to get 150,000 volts into this device, which is well beyond the noise floor of forces that we'd expect to see. I'm not the only one doing it. We have several affiliate labs. Wayne and Nam are both working on the cylindrical capacitor version of this technology. They've been doing really great work, and we're waiting for test results coming in soon. And well, if we can use asymmetrical capacitors like this to produce a thrust, what might they be used for? I guess I'll leave that to everyone's imaginations. So, is it possible to produce a force without reaction? Richard Feynman seems to think so. And in his lecture 17.4, he talks about an interesting idea where a non-zero momentum can be transferred from an electromagnetic coil attached to a plastic disc with charged metal spheres around it. And so basically what he describes here is that in this solenoid with a battery on board, all this being part of the same assembly, the solenoid slowly builds up a current flux over time. And as it begins to build up its field, that field has an interaction with the electric charges in the charged spheres. Now say the circuit is suddenly disconnected. Now that coil and all the electron momentum that was flowing through it suddenly stops. So the momentum that was stored in that field has to be returned. And because the field is no longer tied to the coil itself and it's been radiated effectively because there's a very fast amps per meter change, there is a Lorentz response to the charge on the spheres. And as a result, this entire device should theoretically rotate. Now, it doesn't make sense how you can, basically blow your own sail, but in this case, he gives us a mechanism to do it. And so he describes the mystic circulating flow of energy, which at first seems so ridiculous, is absolutely necessary. There really is a momentum flow, and it is needed to maintain the conservation of angular momentum in the whole world. So if he's right, basically what it means is reactionless force is indeed possible, and we have a hypothetical way to pursue it. So other things that I've done in propulsion research recently, I have developed a little electrodynamic displacement current tractor panel. So what this thing can do is attract any solid material to its surface, both insulators and conductors. It demonstrates a universal high frequency dipolar electrostatic field attraction of any matter. And it's constructed out of trash printer parts. Anyone with skills can build one. So I've got a little video demonstration of that. Hopefully it plays. Now, I know I don't have sound configured to come through, but on the left there, we have that plastic ribbon cable panel. And on the right, we have a piece of thick plastic material that's being pulled towards it. Here I have some pieces of plastic that I'll be picking up just by pressing the power active button, and the second power is let go. You can see it drops them. And so it's not just lightweight plastic materials that it can pick up. Here's a heavy piece of glass, 1/8 inch thick. And as soon as I press the button, it's like a magnet for the glass. Let go of the button and it immediately drops. So what this really shows you is that gradient fields can be utilized to perform real work or exert forces on just about any variety of materials. And engineered correctly, these can have real practical applications. So we wanted to play around with other interesting effects too. We were looking for high impulse power to see what kind of phenomena we might be able to capture, looking for non-zero propulsion forces. And we constructed a huge impulse generator. We just sort of said we stuck a lightning bolt in a box. She can do 9,000 joules at 500,000 amperes, 1,800 volts discharge. It charges at 1,850 watts, 3 pulses per minute. And in terms of the inductance discharge loop, it's about a 16-inch wide, 1-turn loop. So it produces strange effects like softening wires that become solid again. And in the next slide, you can see what it does. On the right, we see a piece of steel wire that was unfortunate enough to be between the terminals. On the left side, you can see the 2 discharge terminals of that impulse generator. And in the middle here is just a quick drawing to show you one of the weird things that happened. We had a piece of 12-gauge solid wire between the terminals. When it destroyed itself and flew apart, that solid piece of wire, if you can see my arrow here, followed between these pieces of wood, actually went between the plywood door and the wood frame, took a 90-degree bend without denting the wood, snaked out, and then was sticking out about 3/4 of an inch on the other side. It didn't damage the wood at all. It didn't puncture through, and 12-gauge wire is actually rather hard. So even moving very quickly, I would have expected it to, impel itself, but that's not what it did, which tells me this wire was in a very, very soft state for one reason or another when it was moving through the door. So it tells us there are interesting things to look into when it comes to high power discharges, and we might be able to exhibit some strange properties of material under these high current effects that we'd normally never see. So I'm going to skip over this real quick, a search for invisible forces, but I will just cover it real quick. When I was younger, I built a 160,000 volt multiplier with a large 6.5-inch diameter discharge terminal. And I noticed a strange phenomena that if my hand was about 1 foot away from that terminal and I would have suddenly discharged it, there was a pushing force, a very quick push away from that terminal that was detectable by me or anyone else that was standing nearby it. And I thought, that's rather strange. I would expect it to be, pulling towards, but I wouldn't expect the push. And so this relates back to the 3M invisible wall problem. In 1980, David Swanstrom, who works for 3M, he was an investigator for 3M trying to solve some weird electrical problems that they had. He was called into a 3M plant because one of the huge conveyors of polypropylene film they were using to make tape was exhibiting strange properties and freaking out the employees. So they couldn't quite explain to him what was going on over the phone, and he decided, well, I'll take a visit there and check it out. When he checked out this film material, he had a voltmeter to see what kind of electrostatic charges it was building up, and noticed that it pegged his meter, indicating to him that it must have had over 1 million volts on the belt. So he decided to walk underneath this roller, which came up the left side, went over the center of the doorway and down the right side, a total of 21 feet wide belt, 21 feet high, 20 feet over, and 21 feet back down. This is a huge belt with tons of charge. He noticed that as he walked underneath this belt, he started to feel pinpricks on his arms and legs. His hair stood on end, and as he reached about the very center of the belt, he got stuck in what he described as an invisible web, almost like a force field, and he describes having to actually peel himself away from it to walk back out, almost like it was a force field on Star Trek. So what the heck happened that day? So polyfilms can develop a huge amount of charge. I'll show you a quick video here. Here we can just see several foot long lightning bolts jumping across the surface of this polyethylene film being unspooled at a not really all that fast rate. And so you can imagine something moving at a reasonably high rate, unspooling quickly, could develop easily millions of volts of charge. And that's a hell of a lot of charge moving really quickly. So Richard Van Derek actually offers us a possible explanation for the phenomena and a way to engineer it. And what he describes to us is that when you have charges trapped on the surface of a smooth plastic and you move those charges very quickly, those charges are effectively open circuit. They're not part of a closed circuit loop. And so when they're moving very quickly relative to a stationary observer, they get geometrically amplified, and the electric fields that they appear to have become significantly stronger. And because these electric fields are relativistic fields and they don't actually exist from the reference frame of the particle themselves, they don't have an equal and opposite force. So this is one way that the force field might have worked. Now, in pursuit of trying to figure out how this could have worked, I decided to build a small version with a piece of polypropylene disc material I pulled from a TV. And although the disc was much smaller than the 3M belt, there was a very weak but perceptible force near the surface of the disc, only when it was rotating, that wasn't present when the disc was stationary. So I charged half the disc up, and on the picture on the right here, we can see the scope trace showing an AC waveform as the charge half of the disk moves past the pickup electrode. Now, as you increase the speed of the disk, naturally the amplitude peaks of the waveform go up, indicating to us there is some geometric amplification taking place. And that's enough data in hand to continue with results and experiments. So if you do charge the disk up and allow it to discharge, you get quite the fantastic snap out of it. I'll play that one more time in case you didn't see it. Here I'm depositing 160,000 volts on the surface, and eventually it gets too high and it leaps around the edge. So the big difference between my system and what actually happened at the 3M plant that day is, mine is moving at 4,188 feet per minute. Well, the 3M belt was only moving at 1,000 feet per minute. They had possibly over 1 million volts of charge on that belt, and I only have 130,000 volts of accumulated potential. Their belt was 21 foot wide, and mine is only 16 inches wide, and they had 3 interacting flat surfaces at 90 degrees to each other, each with its own independent electric field, and all those fields would have been intersecting. Whereas in my test, I just have one single disk that only has one electric field. Plus, in the 3M's case, it was almost 80% humidity that day and a rather high temperature of almost 80 degrees. And so in my case, I'm testing at about 20% humidity and about 75 degrees. And apparently the humidity was a really critical factor, as later in the day, David Swenson reports that when the humidity goes up and the temperature goes up, the effect starts to diminish. Other experiments that I'll cover real quick. I did build a Boyd-Bushman magnetic beam amplifier. He makes some pretty fantastic claims that this device can amplify magnetic fields into a beam form, and it can generate electromagnetic pulses, disrupting circuits that use transistors or other sensitive electronics, and that it can extend the length of a spark discharge from a Van de Graaff generator. So I constructed 2 of these beamers, each of them with an opposite polarity, and I added modulation coils. On the left, we can see a modulation coil between the rear magnet and the rest of the assembly. And on the right side, we can see a wrapped modulation coil that takes place of the rear magnet. Here's a pulse power supply to really slam the modulation coils with lots of energy, looking for any changes in the magnetic field geometry. And then here's a basic test setup that I did. I hooked one of the coils up to a scope that I placed between these 2 points here. And in this coil, I modulated it with the impulse bank. And what I measured on my scope was a pretty insignificant fluctuation of voltage. It certainly was no electromagnetic pulse. And actually what I got out of Boyd-Bushman's claims here were that I didn't get any pulse amplitude beyond what would have happened with my coils if there were no beamers in place at all. So clearly I'm doing something wrong, or the claims of the patent aren't quite as they seem. So if anybody has advice on how Bushman's beamer was supposed to work, it doesn't appear to me too obvious that it works exactly as prescribed. So I have to give up on this project for now and wait for better information. So updates on the static displacement field drive of Bandurk, and this will be one of the last things I cover here. Now, pictured above, we have Richard's original, or one of the original field propulsion technologies drive prototypes. And so basically what a static displacement field drive is, it's a motor with one disc attached to it and a separate disc of a separate material fixed to a frame on the other side. A high amount of charge is placed between these parallel discs, which act like parallel capacitor plates. And because the discs have 2 different fields, 2 different physical surfaces and constructions, there is a very big difference in the complex electric field produced by those disc materials. So when you rotate them, you end up developing a torque or a load on the rotation of one of those discs, which then is converted into an axial force. And without getting into too much detail as far as how that works, let's just go into what I've covered so far with it. My first failed attempt, this is the device that I constructed over at Falcon Space Laboratories in collaboration with Mark, and it was hung on a torsion balance. This system had a couple of problems. First one is that the dot product disc, one of the most important components in this system, didn't hold a large amount of charge and the material was too thin. The second one was that I used an external tube isolated power supply, and it was connected to the device with long wires, and long wires are terrible for this application, so that had to go. In the new version, I'll be replacing all that with an onboard integrated power supply. And instead of using batteries to power the tubes like Richard did, in this case, I'll actually be using an isolated 20 kV transformer to power those tube filaments, since they work just fine off AC. And then I can regulate and drive those to keep constant cathode current from an onboard driver circuit. I'll have also built into the device onboard current and voltage meter, plus onboard tachometer. So this means there are no wires connected to the device. It's entirely optically triggered and battery powered. So again, eliminating wires out of the test stand is ideal because we don't have contributions from wires being, tensioned or pulled or charges on anything. And so in order to make the dot product disk, the thing that actually holds the huge amount of charge necessary to generate forces in the system, we're going to mix some metal powders with epoxy mixtures. And in this case, I'm just using some fine nano powder and max GPE epoxy, which is what Richard used. I needed a sonicator. They're kind of expensive and I didn't have one in time. So I tossed a simple 100-watt sonicator together and this worked beautifully. I just simply epoxied a transducer to the bottom of a glass. So if you need a sonicator in a pinch, this works great, just FYI. Once the epoxy and metal is mixed together in the sonicator and the mix is homogeneous, it gets poured into a circular mold that's sprayed with some easy release. So it just peels right out. And then that is vacuum degassed, cooked in a oven at about 65 degrees until it's cured. And then what you end up with is a composite disc of metal and epoxy that holds a pretty decent amount of charge. And to finish that disc off, I encapsulate the entire thing between 2 layers of polypropylene film, which is a very good material because it tends to have a very low leakage current. And then around the outside, it's totally encapsulated in epoxy so that there's not a single point on this thing where it's exposed to air. I've built several variations. They all tend to work with a little bit characteristics, but none of them are great. And I actually am still not quite happy with what I have for dot product discs. So I'm working on that to this day. Cross product disc is equally important. This is a smooth disc that allows us to amplify the cross product of the complex electric field. And so in this case, you want a smooth material that's able to be spun very fast. And I'm using fiberglass with a highly polished copper clad surface. And I'm using a 3-phase ESC driven motor. I can hit about 15,000 RPMs in this case, which is significantly higher than my 9,000 to 10,000 RPMs on the last design. And so this should be good. And concluding thoughts as far as what we're working on today. Electromagnetic science is full of non-intuitive concepts, things that seem contrary to common sense when from what you were taught in high school physics. But consider, for example, how 2 charged particles interact when one is moving and the other is not, basically when they're in different frames of reference. And then my favorite quote probably of all time, which is, if it doesn't matter, how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. And Richard Feynman is right. If we can't experimentally test these ideas, if they're just theories, and they look great on paper or they're mathematically perfect, but there's no way to actually bring it into the lab, in this day and age, it kind of doesn't matter because those things are going to get us there. But what we need is results now, and we don't have enough experiments going on. So really, I just want to encourage everybody, when you're in your lab working or you notice something weird and unusual or quirky, pay attention to it because you never know which one of those observations might be the key to the next breakthrough propulsion technology. So, all right, folks, that's pretty much it for my presentation. I hope you enjoyed.
Smash that like button. Awesome, 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 awesome.
I don't know if my audio is working. I think my Zoom is crashing here.
Oh well. They just got to him, dude. They shut his computer down. They're like, damn it, we got here like just a half an hour too late. Nah, everyone has problems with Zoom. Sometimes after like an hour it freezes. I'm surprised mine's been running for 4.5 hours and without any problems. That's pretty crazy. So I don't know where Tim is. I don't know. I think Tim is AFK. I can't unmute my mic because I'm not allowed to. It won't let me. So they can't hear me in the chat group, but I'm pretty sure my live audience can hear me, and so I'm continuing the call here. Let me call Tim on the phone and get him to jump back and give me the reins. Tim Ventura. Give you a call.
Okay, I think my audio is back. Can someone say something?
Yeah, no, sorry, that was me.
Oh, there he is.
Sorry. Oh, look at that. I did. Yeah. Well, it's only been 2 minutes. Okay. My apologies. I stepped away to use the restroom. Okay. So yeah, who wants to ask questions first? Does anyone have questions for Jeremiah? Jeremy does. Okay, go for it, Jeremy. And you guys can unmute yourselves now. I changed that setting again.
Hey Jeremiah, thanks, and once again, awesome presentation, man. This is looks like you put a lot of work into in putting this together. I just wanted to know a little bit about what you're working on next, and where do you see like where do you think like the best, like we've taken a look at so much different stuff. What do you think you have the most hope for right now as far as an experiment, and for like we're just banging out cost-effective stuff right now? Is that the deal, or is it?
No, actually, right now I'm revisiting some old ideas that I've always misunderstood. It's easy to read through Brown and completely misunderstand what he's claiming. Plus, he's not really that clear with it. In fact, a lot of these technologies operate by mechanisms which are not obvious at first. So as I learn more, and especially thanks to APEC and all the people that have just poured out information that's kind of groundbreaking, I've had to revisit a lot of the old concepts that I previously gave up on. So it's not so much that I'm going back to simple or cheap. I'm going back to things which I think have been around for a long time because they're the most easy to replicate because anybody can do them. And my main goal is to test out technologies which I think anybody can test. Because quite frankly, it doesn't matter if you have a really groundbreaking technology which requires super exotic components or really expensive parts or unobtainium. If it can't get into the market in a mainstream way, if people can't build it themselves, if they can't test it, it's never going to get out there for all of us. So we need things that are actually usable.
I also point out that like a lot of things that would have been super materials back in the 50s when Brown started working on all this stuff are readily available now for really cheap prices. We have way better dielectrics. We have way better semiconductors. Way better. There's a lot of material science that has evolved in the years, in the 70 years since Biefeld Brown was first doing a lot of these experiments. So we have that advantage to this as well. Could you comment on any of that with regards to other people out there, meaning trying to start their own labs up? I mean, we've thrown some ideas around about I know a lot of people have thrown this idea about like a ranch, like a collaborative effort where we can all get together on like a big, project. And then like we've talked, then we've had other members of the group say, oh, we don't need so many cooks in the kitchen, too many cooks in the kitchen spoil the soup. So it's like maybe a big operation isn't a good idea. It's better to have these small like groups that are like kind of working on it. And I don't know. I kind of bring a lot of these people together, and I'm sure after the conference, a lot of people are going to hook up with one another and have their own, go off in their own directions, hopefully, and add more to, other people abandon teams that they were on and join other teams as this crisscross and stuff. I think there's a lot of stuff going on right now. Could you comment on any of that you know about, or?
I wish I could comment on more of what I know is going on right now. Unfortunately, the reason why I only mentioned Hector and Richard in my slides, and why I just briefly mentioned the Sekas, is because there's not really a lot of people doing this specific type of research. Now I should probably throw in, just for the record, that the technologies I mentioned today are just a fraction of what we're working on. We have Ziggy's drive. That's going to be a huge thing that requires a lot more construction yet. I've been pretty booked up for time. We have a lot of different technologies that we are dabbling around with right now that I'm not going to get into just because I don't have enough data to really say one way or the other what I think about whether they work. But just keep in mind there's good things coming around the pike, and if this one doesn't work out, there's a lot more where that came from.
Also, what Jeremy was talking about earlier with the new and the cheaper, the better technologies that are available with power supplies and components. Some of these experiments actually require the older stuff, like the vacuum tubes that you can only buy new old stock. So it's not all that technology got better, and this stuff is more readily available. In some cases, it's harder to find those old components that are no longer manufactured.
Yeah, that's another really good point too. Is especially Richard Bandura points out again the point of isolation, where tubes are probably one of the best ways to actually do that, because almost no solid state semiconductor diodes offer the same or even close to the degree of isolation that good old fashioned electron tubes do. And Jeremy, to your point, to answer your question about collaboration, there's never been a better time for people to collaborate. If you're not collaborating in person, if you don't have a lab to work on, but you have great ideas, at least find somebody online, find somebody on Zoom, on Skype, on Google Voice, find somebody that you can talk to that is working on this stuff, and get together and start to share your ideas, because it is the prime time to do it now, and you're not always going to have that chance.
No, it's super interesting about that is the tubes thing. Those things went out when the transistor sort of took over in the 50s with microelectronics and semiconductors. The tube industry kind of fell out, so the only ones that kind of picked it up or kept it going were actually guitar amplifier manufacturers, because you can't get that classic tube sound without the tubes. And so if we're going to reach out for anyone who's improved, because think if the tube industry had the funding to develop over all these years, what kind of tube technology we'd have by now, as far as the materials for constructing tubes. But I assume that some of these guys have some stuff figured out with the guitar industry. I wonder if it's similar for the.
Let me guys, let me jump in real quick and go to Thomas, because he's had his hand up for a bit. Sir?
I just wanted to say I have a electrical engineer friend here in New Jersey who works on guitar amp tubes. I'm going to bring him down to the lab next time Jeremiah's down.
Okay. Okay. Thanks, Martin. Let me get Thomas in. Thomas, go ahead, sir.
Yeah, I was just going to say I actually have a couple points now, because the conversation continued on and it created more more content, I guess, to kind of vomit out here in to the ether, so you guys can basically consider it. When you mentioned the glass tube, the tube technology being phased out with the transistor technology, it pushed it out of the public view. But it's still there, because transistors can only be made in vacuum tubes. The vacuum chambers that they use for that. So that might be something you need to think about when you're trying to communicate with someone about information about how to basically work with them, would be to approach somebody who works in the industry for manufacturing transistors in maintaining those tube arrays, in order for them to basically grow like their films and whatnot in the vacuum chambers, or with a chamber that they're controlling a set amount of plasma for plasma deposition and whatnot. The other thing I was going to say is somebody to maybe look up on YouTube would be Glass Slinger, because he does a lot of vacuum tube rebuilding. So for information, so that if you want to work with glass tube technology, rather than trying to hunt down new old stock, just build some new stock. I mean, glass is fairly easy to come by.
Said Glass Slinger?
Yeah.
I'll go check it out. Where can people find him and more information on him on YouTube?
That's his YouTube channel name. So.
All right. Yeah, YouTube Glass Slinger. I'll type it in the live chat. That's good call.
Right. Yeah. I mean, he's the first person I heard mention how when he was trying to lower the vacuum inside his tubes, and he was having issues with getting low enough, going through a whole discovery process where he finally kind of stumbled upon the getter technology, which is just something to absorb the rest of the atmosphere out of the environment when you heat it up, to create a chemical reaction, and that would drop the vacuum down, because Like if you're using iron and you're trying to get rid of oxygen, you react it with the iron, and the iron oxide can't evaporate into the chamber anymore, so it's now a solid. It
Oh, they'll
gets it out of here.
do it in pure nitrogen, and then they'll put a component which is a nitrogen harvester to suck up the
Right.
rest of that light nitrogen that's in there.
Right, right. So, I mean, I looked at using something similar without realizing that it was a getter technology for clearing out like the oxygen trapped inside of like an argon tank while you're
That's brilliant.
doing work with like just, you know, candles. Turn it into carbon dioxide, because at least that's less reactive. Plus it weighs it down, so it'd be easier to extract out of your chamber and repurify your argon. Just keep reusing it. It was just, you know, a simple concept, 2 chambers. You're using a welding mechanism for laying down traces of metal, and then to get in and out to get the stuff, you want to pull all the argon to another tank, extract, close the tank back up, then cycle everything that's in that chamber back out, and, you know, the argon back into the chamber and start the process up again. So I was going to say about the lab system. Has anybody considered the idea of breaking between the two of the giant collaboration and the too many cooks in the you know, ruining the soup, where you basically have multiple facilities and have a free like exchange of you know, people being able to move between facilities at different locations? So it's something that I had thought about doing a long time ago. That's kind of a little bit of what this whole thing is here, is that, you know, it's the idea of building up the atmosphere of the environment that you're working in, so it feels more like you're in a more futuristic environment to, you know, keep people's energy level high, so that way while they're working, they're not, you know, even if they're having mistakes or something like that, or failures and whatnot, it's not going to lower their mental level, so that they'll basically, you know, want to stay in bed the next day instead of getting up and actually trying to work on something again, as well as kind of foster that kind of, you know, the concept of being on a starship. You have to work with other people. That means you're most likely going to have bunkmates and, you know, people that you can't get away from. If you can foster that idea of more of a camaraderie like that, like you see imagined in things like Star Trek and whatnot, not only will you be able to basically work longer periods of time and get more productivity out of it, but you're talking about the financing at one point too. People are going to want to basically tune in and see something where it's, you know, exciting looking.
Well, the thing is, right now with COVID and everything, where everyone's locked down, we have all these independent labs. So I think I like this idea of just being this beacon for all these independent labs to get together and work on this stuff. Right. And then we're trying to get the attention of guys like Electric Boom to jump on board and be like, hey, let me start getting involved with this, or let me give you guys equipment, or start, you know, talking about what you guys are doing. That's kind of the direction I'd like to see it go. Rather than build one single Titanic ship, we need to build like a whole armada, or you know, it should be like a series of ships, you know, like where it's an unsinkable fleet, rather than put it all in the Titanic. And what happened to the Titanic, right?
Well, the other thing too is he mentioned the humidity in that one experiment. If you have multiples of these places across the U.S., you're going to have different environments to try things out simultaneously. Like you could be doing something close to the Great Lakes where it's cooler and maybe a little higher humidity. Somebody else is out in the middle of the boot heel of New Mexico where it's super bone dry and the temperature can be really high, or it can be really low depending on what time of day, because at night the temperature drops down to freezing, whereas during the day it could be over 100 degrees and, you know, you wouldn't break a sweat because there's no humidity in the air.
Well, Thomas, let me jump in real quick. Franklin, you had a question. So Franklin, let me get you really quick, and then we'll kind of come back to this.
So my question is, I noticed, Jeremiah, that you dismissed, say, the lifter technology very quickly in the beginning of your presentation. Now I haven't actually done anything with those lifter tech, but I've seen like the videos, and you see these things just leap off the table. And, you know, I'm familiar with things like ionization generators, you know, and you know, they produce a breeze.
Well, I can answer that question, Franklin, right off the bat. I've spent a good number of years working on advanced lifter tech, up to the point of producing ones that are just damn near close enough to lift their own power supply. As far as lifters go, my best thrust to weight ratio is about 4-to-1. So when one of my thrusters kicks up, it will tear off its own threads and then continue to tear off its own wires with its upward momentum on a single ascent. So in terms of ion propulsion and the amount of thrust that you can get, it is huge. In fact, it's over 40 times more efficient watts per gram of force, theoretically, than the best propellers or jet engines. It's just that to try to get those efficiencies out of ion thrust, you need an incredibly high ion saturation, a control magnetic field, in order to keep the ions constrained, and then you need multiple correction electrodes to keep the electric fields from having to reverse the electric field component that would cancel out their forward momentum. But long story short, ion thrusters are certainly not lacking the thrust. So when you see them pick up off the table, it's not because it can't be ion power. It definitely can be. And then secondly, to answer your question in the beginning, I didn't dismiss ion thrusters. There is a small electrogravitational, or theoretically a small electrogravitational thrust from ion thrusters, but it's actually in the opposite direction of the net upwards thrust. That's the reaction force against the surrounding medium. And so the amount of gravitic thrust from those systems is so small that you'd never be able to see it under normal conditions or even under atmospheric conditions, because you couldn't get the potential between the electrodes high enough to get that number big due to ionic leakage. So it's not that they don't generate anything other than ionic thrust. It's just that 99.9% or more of their actual thrust is in fact reaction mass.
Now, the fascinating thing I saw was your plastic panel that can attract everything. I thought that was great. I mean, what kind of how are you achieving that? Because I know that any central spherical charge can attract anything, but what you had there certainly wasn't spherical. So I'm just kind of curious.
But it actually was. It actually was, and that's the funny. No, you're correct about that. It's a hemispherical charge. So that panel wasn't just a flat panel. It was actually a ribbon cable that was pulled out of the same printer the transformer came from. It's a 1 1/4 inch wide by 4 1/2 inch long ribbon cable. It has some 30 conductors in it, and every other conductor is attached to the same row. So there are 2 rows, and they just back at 1 2 1 2 1 2. Those series of conductors are hooked across the high voltage output of a 7 kV transformer, and then they're ramped at about 250 kilohertz. And so the AC field developed between those 2 lines going across that entire ribbon cable that are parallel develop an electric field between themselves and the surface of any other material, whether it be metal or dielectric. And so the divergent field coming off of those flat electrodes means that anything trapped within that field will want to move towards the place of highest energy concentration, which is of course right up against the panel. It is a near field effect. It only is effective at about maybe 3 or 4 millimeters away from the surface. And the primary reason is the separation distance between the conductors is only about 1 millimeter. So if you were to separate them out to about 4 or 5 millimeters, then you would get about maybe a 10 to 15 millimeter range. And I've tested it as wide as 1 foot, and you get about a 2 to 3 foot range out of it. So it works better as it gets bigger. But you also have to have a consequently higher voltage to pump it, because you need those volts per meter. It's not just about the frequency, it's about how many volts you have in a given small volume of space in order to create that attraction force through the, what do you call that, the displacement current that takes place. Go ahead.
Yeah, you mentioned that it's hard to build these systems to measure thrust because the wires themselves are exerting a lot of force. Personally, right. I think that gravity is probably that force. So in some ways, it's like you're throwing the baby out with the bathwater. It's like that attraction of the wires to the wall. That is what.
Well, that's called electrostatic field attraction, and Franklin, the way that we get rid of that is by getting rid of the wires. And we can do that because luckily in 2021, parts are small and components are amazing. So instead of using large benchtop power supplies with large feed cables to run my experiments, I'm just building little battery powered supplies and putting them right onto the experiments themselves, getting rid of the wires. And that means if the engine works freestanding of its own accord with no other external connections, then it should work in space. At least that's the idea. And when you have the wires, they contribute error, and you want to eliminate all error if you're trying to do a good experiment. Wires just are another place for error that you should get rid of if possible.
Okay, you know what? Let me go to Eric Hermanson, who is asking about the Can-A drive. Eric?
Yeah, I just wondered. I haven't heard of it. Yeah, I heard a lot about it about 5, 6, 7 years ago, and I looked into it a bit, and then it just disappeared. Does anybody know what happened?
I would certainly like to. What is it? Can you describe what this drive is real quick, Eric?
It was a real interesting looking thruster. It kind of looked like one of those Roomba vacuums. I mean, it was like disc shaped, but then it also, I mean, you can look it up on the internet and find drawings of it. It had like all these notches in it, and it was really futuristic looking. And it was some type of RF, I think RF type thruster. They had a theory on their webpage that was derived. It didn't look like a very clean theory. It looked like sort of like a Taylor series expansion of a force equation. Sort of. It was like a bunch of terms in this really long equation. But I don't know. It got a lot of press for a while, and I don't even know who is behind it. But actually, Guido Feta, I think, might have been his name.
I have a photo that's up in the message there. There's an article on The Verge that shows a picture of it. It does look like a cousin of the EM drive.
Okay, yeah, there it is. I saved the website because they took it down, but it looks like it's back up again.
Can I add something to this?
Yeah.
Yeah, I know about it.
Okay.
Because
what's
I know who tested it. Let's see, Jess Spawnable, the same guy that was funding my research, was from DARPA at the time. He was the one that was basically courting them. He also paid Sonny White, which was Eagle's Works at the time, to do vacuum testing on it. And in fact, you can find it under Sonny White. And if you put in Kinetics Drive and NASA Eagle's Work, you will find the basic report that talks about the testing. And in fact, I just forwarded that PDF to someone else who was asking me about my own asymmetric capacitor stuff from DARPA. I have it here somewhere. I got to find it real quick. I think things on my other computer though.
Yeah, thanks,
okay,
Hector.
but it sounds like there really hasn't been any news in at least 5 years though.
Yeah, the last I checked, that was all that came to it, and they were still looking into it, but it didn't seem like it was moving forward at all. In actuality, the last thing I remember, yeah, it was considered like a knockoff of the EM drive.
Actually, if you hold on a second, whenever I see a site like this, I usually use my website down. Hello?
You can try Wayback Machine and probably get the older version.
Oh yeah, you could do that too. I usually save the website with a script. I have some pictures of the device, but I guess it doesn't really make sense to show them. You could just go to archive.org and see them.
Yeah, and also I want to try and keep things focused on Jeremiah's presentation, because we actually have a surprise mystery guest at some point. I'm not kidding. It's a surprise to me, so hopefully they're dressed.
Okay, well, I'm done.
Okay. Well, does anybody else have questions for Jeremiah? Now he's laughing at me. I'm serious. We have a surprise mystery guest.
Oh, I was laughing because I was thinking, Tim, you're no fun.
No idea. I know.
You never know. If it shows up, you can always kill somebody's video, but the rest of us can laugh about it.
Well, somebody has to be the downer, right? Somebody has to be the town downer. That's me.
I guess. I thank you for taking on that responsibility. That's
right. That's right. I'm a ray of darkness in a room of light. So
I think
we all know it's thanks to you to make this happen, Tim. We can't appreciate you enough. That's the truth.
Well, thank you, sir. Thank you. But
Ron Kita has his hand up.
Ron, do you want to go for it, sir?
Unmute. Am I there?
There you go.
Okay, for Jeremiah, I mentioned a while ago, Rex Schleicher, Colonel Rex Schleicher has the NEMPS patent, nonlinear electromagnetic pulse patent. And I'm not sure if he ever investigated that, but one of the things that I shared with, when I was friends with him, he's now living in Albuquerque, New Mexico. And we were in, you had it on your slide, it's called the Feynman disk paradox.
Yeah.
Okay, the Feynman disk paradox, I think there was one configuration, instead of steel balls, they used electrets in terms of having a better charge. But also what I wanted to mention is, I was always intrigued by it and used the word theoretical. But you ever hear of Graham and LaHose?
No, I haven't, but I'd like to know more.
Okay, if you type in Graham, Graham, and LaHose, LaHoz, you should find that they supposedly they did the confirmation. It took me years to find a confirmation of the Feynman disk paradox. And
you actually found it? That's amazing. No way.
Well,
okay, this is great.
It's just a question of time. It should be. Did you find it there or not?
I'm looking. It looks like there's a. It looks like in 1980 there was a experiment that they did. I'm trying to find the actual paper if I can locate it. Experimental decision on the electromagnetic momentum.
David Mathis just wrote Graham LaHoz. I think that may be LaHoz. Graham LaHoz. David just wrote that in.
And also, in my concluding remark is, as far as kinetic technology, I forgot who asked me. It may have been somebody asked me, Frank Mead or somebody. They said, you know about them? I said, well, they're located in my town, Doylestown, PA. I was to meet with them over the years once he never would meet with me, but if they exist, they now exist in Warminster, PA. That's my comments. So.
Thanks, man. I've got that paper. That's it's pretty awesome. It's a huge paper, 311 pages. Looks like in total, but of it, just the 16 pages I think relevant. Looks like it's a snip out of a bigger book. Eh?
So let's go to. I think Michael Himes has a question. He's unmuted himself, sir.
Yes, please.
Yes, Tesla had a tube rectifier in his electric car. He harvested the Alphen ring current. Now, I'm revisiting that because I believe people are unaware that when you have a scalar field or a longitudinal wave function, it links with the Earth electric circuit.
I've read a lot about trying to link with the Earth electric circuit and the interesting tests that are done in Faraday cages that apparently do affect measurements that are taking place of it. So I know that some of the experiments we did worked fine without the Faraday cage, but the second you put them inside, they no longer work, and that's a report that we've read multiple times. But what I'm really interested in, Mike, is, I mean, you know all about the chirality of materials or the chirality of materials, and I'm trying, I'm trying to still fully grasp or wrap my head around how to produce these Alphen ring currents and how to pump the Chiro ring resonator at a frequency that's close enough to, something that I can actually get it ringing at, because it's an awfully small set of rings, and I was trying to drive it at a frequency significantly lower than its resonance.
Your resonator, the one that you use for mixing up stuff, the 100 cycle one, anyway, the ultrasound, that's the frequency, resonant frequency of silicon or silica. And that's good enough to stir the Alphen wave ring currents. It's like an LC tank. You have your resonator and then the mirror image of that resonance in the ground. And it stirs the earth current. It's the way you access. Tesla found that out, and that's how he ran his electric car.
So in that case, when I really get it ringing hard, it's actually pushing against the ground that causes the lift?
It's a field effect. It's an ether effect, as well as ion discharge.
Oh, cool. Because I did not realize the contribution of the ionic component in that circuit.
It's a matter of density. your phonons are being shed by your transmitter, and it's becoming lighter, and there's more pressure from below. So it's like low pressure above your disk that you're wanting to lift and high pressure below. And what people don't take into account is there's so much current in the alpha wave, it's unimaginable. It's the Earth capacitor discharging. And it doesn't matter the size of it. The resonant frequency is critical.
That's very interesting. It's going to take me a while to wrap my head around all the concepts to be able to actually build this thing. I've been playing around with different chiral materials. I have been, I've been playing around with one specific mixture, which you're quite familiar with, and I've had pretty good results creating a nice set of film that has graphene and some chiral molecule in it mixed with a decently strong, 99% acetic acid. But I still have yet to play with some of the other newer materials that are out there, and I'm still not sure how to drive the entire array yet. I was thinking of just ordering some PCB printed chiral resonators, but then I was wondering whether or not I'll actually be able to drive them correctly.
If you want to see the separation of electrons, your valence electrons and the other kind, look up the Hirsch vortex tube technology. It goes hot on one side and cold on the other.
Yeah, I built quite a few of those things. They're a lot of fun.
Well, they're not just a lot of fun. It teaches you that the phonons are being discharged. That's where the hot end is.
I've never thought about it like that.
It's the vortex effect.
And how does that apply to electromagnetics in this case?
Well, a vortex is going to create its field.
Because I get the heat. I mean, I understand the heat exchanger phenomena going on in the vortex tube, and it operates very much like a conventional heat exchanger, only you don't actually need a barrier wall between the two counter-flowing air streams. But in terms of electromagnetics and electrodynamics, I guess I'm having trouble linking the analogy.
Well, it's the spintronics of it. That's where your magnetics are.
Yeah. Well, let me jump in really quick. I think that we're just about, let me meet you out, Michael. Thank you again. Jeremiah, I think we're just about done with the Q&A. We do have a mystery guest. Should we switch over to that individual now?
Yeah, I'm all good to go if everyone else is. I can't wait to see this.
Yeah, I'm a little terrified, actually. So without any introduction whatsoever, here, I'll mute Jeremy out. And okay, you are ready to go, sir or ma'am. Can you start your camera?
Well, I have tape over thing. Anyway, let's see. That should be there. And then, we'll put it in the presentation mode. Can you see the presentation? Oh, let's see. That's not what I'm doing now. What am I doing? Start from certain. Okay, cool. So let's see. How to secure the future. Yeah, this one's going to be targeted more towards like the average listener, college student, whatever. I'm not going to go too much into the mathematical details, but I'm going to try to point out a bunch of places where anyone watching here can help, even if they're not technically, like, they don't have like the technical background or whatever. Just making sure, can everyone hear me? Tim, you're muted.
Yeah, sorry about that. Yeah, I can hear you fine.
Perfect. So anyways, let's see. This thing's going there. So yeah, the problem is, in the modern era, we're all wage slaves in a sense, and that's kind of like, we all have to work to feed our families, whatever else, and in most cases, that means we have to choose between that and like, oh, if Amazon does something bad, we can't just all boycott Amazon. We don't have that freedom. We're all part of this interconnected system. And I mean, we can do better than this. We're almost at the, technologically at least, at the level of post-scarcity, as I will show with some of my things. Let's see. And there's the wealthy in the world, generally, they have a lot of responsibilities and also incentives to not really help either, even though in principle they have economic independence and they can they have sometimes the freedom to do something, like in the case of Elon, perhaps. So various political systems, they all corrode over time, I would say. Communism is often seen as a power vacuum, and then it requires a strong central government to enforce, and then a bad actor can come in and take control of that. Capitalism, if you have pure free market capitalism, eventually what you get, some people do better than others. They use what they learn and the capital they have to reinforce their position, and you just eventually get a corporate oligarchy, a system of monopolies or other structures. So we don't really have a stable social structure over really long periods of time. And also, legally speaking, we have like no garbage collector. That's a programming term. In programming languages, there's this concept of if you have, and I'll get into more technical stuff soon, but yeah, so in programming, a garbage collector, basically, it takes like data that's not being used anymore and frees up the space in the computer. And most governments that exist, most social structures indeed, they have systems that build up complexity, but they never have a way of deciding when a component of that complexity is no longer required or needs to be revised. I mean, sometimes they have a little bit of that structure, but it's like Elon Musk said, it's generally, if you don't have a way of getting rid of old laws that are not necessary anymore, your system will grow more and more complicated until like no one can get anything done by red tape. So what we have constructed as a global society is a paperclip maximizer for GDP. And that's not good because there's a whole bunch of other things we might want, like the environment, our own well-being, et cetera. And yeah, I mean, if we don't have our own personal freedom and economic opportunities, then the system is very brittle. It's very top heavy. And if structures at the top fall apart, then we're kind of out of luck. So what solutions do we have? Well, so some people are thinking like transhumanism. If we can change the nature of people, then we can make a capitalist system or a communist system or whatever else that is stable. That's going to take a long time, although there are things we could potentially do, CRISPR, Neuralink, but whatever. A lot of this is controversial, understandably. And I'm sure that there'll be a lot of feedback and conversation in the comments. Constitutional conventions, I mean, that's another thing that we should consider. But anyway, getting down to what we can do technologically outside of all of those social structures that move slowly and change slowly. We should cut out all the noise, focus on actionable intel, test real devices. This has been something that's been absorbed by the APEC crowd very well. We shouldn't generally trust concentrated power structures. Like in the US, generally conservatives trust corporations and not the government. And on the other side, on the liberal side, they trust government but not corporations. Really, you can't technically trust either. I mean, in some sense. Anyway, but we can get our economic independence by technological means, and it's not really new. Like, it's as old as history itself. Hunter-gatherers were technically independent. The Amish are independent with a lower standard of living. The monasteries after the fall of Rome had to be self-sufficient or they wouldn't have survived. So it's possible to be self-sufficient without advanced technology. However, if we want a modern standard of living, we need to work a little bit harder. So there's a whole bunch of areas where people can contribute, even if they don't necessarily know any of these propulsion technologies. So making fully general manufacturing capability, like something that someone could have on a tabletop that can print an iPhone. That's a very complicated problem, but there's a lot of people working on it, as I'll mention a little bit about. Recycling and raw materials processing, that's key. I mean, ultimately the only limited resource is energy, and that's maybe even not true, we'll see. Yeah, and then food, energy production, mobility. If we have all those basics and we can like print an iPhone and print all the modern things that we might need, we're in pretty good shape. We don't have to participate in a greater economy if we don't want to. And we can walk away from any power structure which is becoming hostile. So another important part of this, I think that it was mentioned in previous APECs and maybe not understood by some of the older people in the crowd, is the open source strategy is very important to what we want to do, especially in the US. So where did I mention the patents? Oh, I'm missing a little bit. Well, anyways, yeah, so in the US, it's first to file. It's not a common thing. A lot of other nations just have first to like post information about or whatever you call it. But the other problem on top of that though, is that, oh, maybe it was one of these. Oh yeah, the patent dilemma, here it was. So anyway, yeah, you need a provisional patent to prevent others from patenting within the first year. But then if it's something that the military wants not to get out, they can just take it. And if you don't get that provisional patent, someone else who wants that thing can get it, but then the military will just still take it. So that's tricky. And what we do to get around that is this open source stuff. So, I mean, if you're not making any money off of it, they can't really tell you no. If it's fully open source, it's not ideal, but like, I mean, you can't make money off of it while the patent exists. But it's better than the alternative because now the information's out there and people are benefiting from it instead of getting locked up in some like classified thing and never being released. So that's something. And then there's just some useful tips and tricks. SEL4, CubesOS, all these things are, I mean, you can go over them in more detail. Influence mapping is an important tool for understanding the modern world, generally speaking. And there's a few sources of information done in Bradsheet, SEC, Edgar. These things are still untainted by like fake news and other things because there is a legal responsibility with teeth for corporations not to lie in these sorts of information references. Anyways, I'll get into some of the things that we can actually do. So nested greenhouses, and in space, bonsai might be actually a very useful thing. Growing things smaller than they grow in nature may be useful for actually getting like large trees and things growing in space. If you're talking about making some food growing apparatus, because that's going to be at a premium because you're limited by the amount of surface area of your habitat in space. Anyways, ecosystem engineering, we're going to have to get good at that, whether or not we get off this planet. Just, I mean, a quick calculation, and this is extremely conservative. Our ecosystem is worth like 1,000 trillion, even just in pharmaceutical value. So like, that's not accounting all the other positive externalities, like the air that we breathe. So any other species out there in the universe that are looking at us right now, they must think we're insane to destroy literally the most valuable thing that we have that doesn't exist anywhere else in the universe. Just because of combinatorics, to find an equivalent species to something on Earth out there in the universe, you're gonna have to, like, just by probability, you're gonna have to travel some enormous, ungodly, impractical distance, even for whoever is out there now, probably. So, I mean, there's tremendous value in there. And there's a lot of places that have done some interesting work, like Las Gaviotas, Colombia. It's a little town. Oops. Why did it jump? Okay, cool. So yeah, Las Gaviotas, Colombia, they've done a lot of cool work with producing a society which is in harmony with nature. It took them a while to figure it out. But then eventually they found a way to use regenerative agriculture to reclaim savanna into rainforest and produce a profit in the process. There's ways to do this. That we need to figure this out as a species. Anyways, Permian mass extinction, I was gonna mention this, climate change, another, I mean, some people consider this controversial, but could be even worse than any of the predictions, because, I mean, we should be looking also at deep ocean CO2 concentrations. Once that gets toxic, things in the deep ocean will all just die, and that gigantic biomass will release hydrogen sulfide and probably start killing off a lot of things on land at that point. So we don't want to be in that situation, but it looks like we're barreling right towards it, and no one, not many people talk about that. But I mean, maybe people think other things will happen first. But and I mean, for those who like are skeptical about all the climate change stuff, just ask any oyster farmer, not even necessarily like a climate scientist or whatever, just ask an oyster farmer about ocean acidification. They have to literally, when they're growing their new oysters each year, they have to like fix the pH of the ocean water with bases to reduce the acidity of the CO2 in the water before they can actually grow oysters. So there's other ways to find out this information if you think that someone's co-opting the other information, and then you can figure out who's really telling the truth. Anyway, electroculture is interesting. I think that guy, the old scientist on YouTube, was looking at this. Ooh, it jumped again. And that's using electrostatic and electromagnetic fields to affect plant growth. Interesting idea. I think that it's mostly because of the modulation of enzymes and other protein activity in cells, because you can affect that with electrostatic and RF fields if they're strong enough. You can actually modulate, you can modify protein conformation, because the conformational change energies are at, they happen at similar electron volt levels to like radio frequency. So that's something that people should be playing around with a lot more in terms of like cures for things, diseases, etc. You could do a lot of interesting things there potentially. And I don't think people have considered that possibility very much yet. So play around with RF, see if you can like figure out what frequencies different proteins resonate at, if you can get protein samples. That might be interesting. And then there's something else, incinerating toilets. This is a strange thing perhaps, but really if you think about it, the system we have now is even stranger. We take our like sewage and we run it through pipes to a centralized center to treat it. And those pipes are just supposed to last indefinitely. They're infinitely strong, never corrode, whatever. That's not sane. That eventually that system will break. So if we can have waste treatment on site at every like house and home for a reasonable amount of energy, and there's interesting things. There was a technology I saw in Vancouver where they actually separated urine from feces using a conveyor belt at an angle. There's things you can do, and this stuff, once you've incinerated it, it's excellent fertilizer, and all of the stuff that would have made people sick is destroyed. So then you can start thinking about growing most of your own food and recycling the waste into more food and continuing that whole process indefinitely, and growing things on site, not wasting like energy on shipping and stuff. Yeah, so there's a lot of interesting opportunities. And actually, what's interesting is the incinerating toilet idea. Bill Gates has been doing that a lot. And,
Sorry, this is Tim. If I could jump in really quick, and I, let me apologize for interrupting, but
Sure.
Does this tie back into advanced propulsion, alternative propulsion at all? How does this tie into kind of our conference topic, I guess?
Right, yes. So this is, I'm trying to provide a slightly more broad perspective of all the things that I'll get into that. I have the manufacturing, and then we get into energy and stuff. So it's almost there. But all this other stuff is like things people in our audience, maybe they're not like physicists, but they want to contribute somehow in a meaningful way to securing the future. That's the idea. Does that make sense? Tim?
Yeah,
Cool.
Absolutely.
So because it's a more multifaceted problem, making sure our future is secure than just the propulsion aspect. But I will get there, and I have a lot of cool things I think people will like.
Okay. Yeah. If there's a way to just kind of move towards, I've had a couple of questions who were asking how it ties back. That was why I wanted to touch base.
Fair. So. It's a slightly broader perspective, perhaps, but I think it's a valuable one. Anyway, going towards manufacturing. So how do we achieve this sort of capability? There's a bunch of companies that have been working on circuit printing. It's still in a relatively early stage of development, but there are people who have their eyes on it. Polyhydrocarbon, I know Jeremy's mentioned that a lot. I was the one who originally mentioned that to him. You can electrolyze iodoform, bromoform, and a bunch of other brominated hydrocarbons to produce polyhydrocarbon. And then this material can be reacted into Lonsdaleite and other diamond-like carbons for 3D printing purposes. You can do that sort of thing. So there's some really advanced materials in the works. And then printing all of this stuff together is like very important to figure out how to do that. That's something I'm working on in a separate project. Perhaps I'll talk about it in the future if people are interested. Integrated circuit etching. There's someone who's actually done this in their basement, Sam Zaluf, good friend. Like it can be done, it can be scaled down, and people are working on it. Raw materials processing, there's a lot that goes into that. Physical sortation. In China, actually, they have a lot of good methods. They have like magnetic electric sortation, and also they have these spiral separators which separate by density. And then chemical sortation, that's like using chlorine to extract aluminum from sand, and aluminum and silicon. And then also you can use carbon monoxide to harvest asteroids, perhaps in space. You can actually carbon monoxide dissolves nickel and iron at different pressures. So that's most of asteroids. And then you can just collect whatever dust remains. So digesting asteroids, cool idea. More people should play around with that. And then there's the Open Source Hardware Association. If you want to get involved in making us basically have Star Trek replicators, because that's what this is going towards. Anyways, getting towards the energy that I'm sure people are more interested in. So more practical things that people should be looking at are like aluminum batteries. Aluminum is far more available than lithium, and it has a similar or even sometimes better energy density. Not with this particular chemistry that I'm showing here with the aluminum chloride urea solution. But there are other aluminum batteries that have incredible energy density and don't really combust like lithium does. And yeah, I mean, it needs more people looking at it. Then there's cheap photocatalytic water splitting. This is fascinating. There's a lot of catalysts that split water. And I mean, one of my favorites is graphitic carbon nitride. That stuff is amazing for splitting water. And you just pyrolyze urea, very cheap urea, to get this material that splits water into hydrogen and oxygen. It does so at maybe 5% efficiency if we're being generous and modifying it the right ways. But it's so much cheaper than solar panels that it's just amazingly scalable potentially. It also avoids all of the conduction problems of solar panels with the collector grids on the top that have to be optically clear. Heat pumps, simple thing that people can do to modify their homes and stuff. Basically, if you have a heat pump instead of just a direct heater, you can multiply the amount of thermal energy that you're pumping into your house relative to the amount of input energy. It works the same way as a refrigerator, but in reverse. Or I guess it refrigerates the outside, but whatever. Anyways, solid phase fuser. So this thing was, yeah, actually what was interesting about the Sal Pais patent is place I was working at had a bunch of military folks come in one day, and I was chatting away with a lot of them, and I was like, well, you know what? I don't have the resources to do this, but if you spun some disks really fast, you could generate an amazing magnetic field and make a magnetic bottle for fusion. And then this patent comes out like a few months later. They probably had a bunch of like, I don't know, maybe they added something to the provisional because of that. But that was an interesting conversation that happened. I don't know whether it was related or just coincidence, but we were thinking along the same lines. There's one thing that's important at the like high megavolts to gigavolts field that you're talking about. You're also talking about giganewtons of attractive force between these cones. That's an amazing amount of attractive force. So, I mean, obviously you're gonna have to have some way of repelling these from each other to counteract the attractive force between them. The way that I could potentially see this happening via conventional physics is by electrostrictive relaxation. If the PZT film on the surface has some finite electrostrictive relaxation time, and you're running this thing at a faster, like at a higher frequency AC field, then the electrostrictive relaxation will take too long, and your field starts to repel the PZT surfaces. So that might be a way. I'm not sure if it's sufficient. The other way I had considered, after talking with those folks, I don't know if they're still interested in further modifying their patent, but if you actually take a capacitor, which is also a gyroscope, what you can do is the central capacitor plate, just make that like a sphere or something, and then the other capacitor plate's a torus around that, and you spin that torus up as a, what do you call it? As a gyroscope, and you charge it up to some ungodly amount of electric field. If you also have this be boron doped diamond, or at least you have diamond which has boron doping at the surface of it, then you can sustain crazy electric fields without discharge of that system. And the diamond can actually take the compressive force if you have the boron doped diamond at the outer edge that's charged. So that's a thought. And that thing, that you can get that spinning a lot faster. This Pais patent was, I think the maximum speed they were talking about, was it like 300,000 RPM, something like that? But you can get to millions of RPM if you have like a diamond-based spinning gyroscope device, which you're using the electrostatic field to counteract the centrifugal forces on that spinning component. I mean, the original idea behind that design was to get to relativistic speeds. That is going to be challenging just based off of the amount of active correction to the gyroscope that you would need to prevent it from processing at those sorts of speeds. But you can definitely get ungodly magnetic fields out of that, like hundreds of Tesla for a magnetic bottle for fusion. And that's without whatever anti-gravity the Pais patent suggests it needs. So you don't need any of that exotic physics. You could do that with normal everyday physics in principle, and a lot of engineering. Anyway, let's see what else. Yeah, so now we're talking about fusion mechanisms. So lattice confinement fusion, NASA put out an interesting paper, and actually, I think it was a week or two ago, I was talking to a guy who worked on the nuclear submarines and also at some nuclear power plants. And he was mentioning NASA was thinking about, well, actually, he and another person I talked to, they both mentioned that NASA was trying to replace the radioisotope thermal generators that they use that have plutonium in them, because of course, I mean, that's a proliferation hazard and all sorts of other problems. So the idea was, if you can get lattice confinement fusion to be break even, you could send out probes with that. And we talked about a bunch of different ways that they could do this. So nuclear isomers. Oh, I misspelled. Well, whatever. But yeah, you could have nuclear isomers, which you give them a kick with some X-rays or something, and they release a gamma ray, and you can use that to power the lattice confinement fusion. Generally, bremsstrahlung radiation is not very efficient, but if you have a radioisotope doped into your material, if you have like lithium hydride doped with tritium, that tritium can release electrons, beta particles, and then those by bremsstrahlung will release X-rays. And the other thing is you can dope your lithium hydride with X-ray fluorescent materials. And these X-rays, they'll have a lower interaction cross-section to induce lattice confinement fusion, but also they're way lower energy than gamma rays. So you can have lower performance if the cost trade-off of the energy to produce them is right. So yeah, so the lattice confinement fusion, there may be a pathway to break-even fusion via that method. Even perhaps brute forcing it with an X-ray gun out of like an X-ray machine at a dentist's office or something. You could, there's things to play around with there for sure. So then there's muon catalyzed fusion. I'm sure everyone knows that, or people, the more technically minded people around here would. But that's basically, a muon is like a heavy electron, and because it's heavy, the orbital distance around the nucleus is very small. So then if you have like hydrogen with two muons instead of electrons, like a hydrogen molecule, then the hydrogen nuclei would get very, very close together, and they can in fact tunnel into each other and fuse, even at very low temperatures. So muons are really expensive though, and they get trapped on hydrogen, on helium, sorry. And the issue with that is, once they're trapped on the helium, they can't catalyze more hydrogen fusion. One thing that people have looked at is hitting the helium with the right frequency of X-rays or gamma rays to knock off the muons so that they can keep catalyzing the reaction. That is another potential way to break even. And then the other thing that people should look at more is catalyzed fusion using heavy quasi-particles in matter. Typically, those quasi-particles are not as small in terms of their wave function as a muon, but you can have metamaterials in your matter. You can have structured layered things, and those layers in your material can reduce the size in at least one dimension of those heavy quasi-particles. And then those heavy quasi-particles can behave as muons in a lattice that contains hydrogen. So, at least in principle. So there's a bunch of ways. And then definitely check out that guy at MIT, Peter Hagelstein's work. He's doing some really good stuff with Mossbauer coupling that could explain. But yeah, I mean, this is all stuff Jeremy's mentioned that I've talked to him about in the past. So one other thing I think that hasn't come up much, which I think people should check out, is negative entropy systems using absorbing Markov chains. So if you're familiar with thermodynamics, second law of thermodynamics has an implicit assumption that there is no microcanonical ensemble, which is an absorbing Markov chain. And that allows thermodynamics to operate as, that allows the second law to work. If there is a microcanonical ensemble that can be built, which is an absorbing Markov chain, then the second law of thermodynamics cannot apply. And in fact, we may have some examples. There's the graphene energy harvester, first thought up at the University of Arkansas, I believe, and now there's a company that's trying to commercialize it. What was their name? They were, I forget, I can put it in the comments later, but anyway, there's the MIT 200% efficient LED. Based off of the emission spectrum of that LED, if you did attach to that LED a multi-junction solar cell, you would probably be able to get at least 60% absorption efficiency, and that would make it over unity via a similar mechanism. Basically, All of these absorbing Markov systems have some things in common. The graphene energy harvester and the MIT LED both have some energy as part of the system that kind of biases the direction that the other energy flows. In the case of the graphene energy harvester, you have a charged flake of graphene between two capacitor plates, and because the graphene plate is charged, when it oscillates back and forth by Brownian motion, by thermal motion, whatever, then the capacitor plates on either side of it pick up a slight AC signal. And it doesn't work without that charge on the graphene. And also the same thing with the 200% efficient LED. It needs a bias voltage on it so that the thermal motion, the phonons in the system can get over the emission limit and actually emit a photon. There's possibly a way to do this in a backyard, scientist sort of way that doesn't require MEMS, micro electromechanical devices. And that's with Neal relaxation or electrostrictive relaxation. And these things, basically, if you have just a solenoid coil with a core, and it's a paramagnetic or paraelectric core, then it has a certain characteristic time scale per unit time. I mean, at a given temperature, it has a characteristic time scale called the Neal relaxation time scale or the electrostrictive relaxation time scale, where at that temperature, the thermal motions in that material disorder the dipoles in that material over time. And if that time scale is different from the resonant frequency of a solenoid built using that coil that material at the center, or capacitor with that material inside it, then you can get some signal that's not at the resonant frequency of that coil system, and you can use a bandpass filter to pick that up and harvest it, in principle. And there's a few free energy devices, quote unquote, that have been seen online, where they also mention that the temperature of the system actually decreases. And that would probably be because it's this sort of electrostrictive or Neal relaxation device. So what's interesting, yeah, I mean, so that you're not destroying, you're not creating energy out of nothing. You're taking it from a disordered state and putting it into an ordered state. It's a negative entropy directly. Anyway, and impedance modulation, this is something I was looking at during my college. Where is it? Sorry. Okay, yeah, impedance modulation. I would say everyone should take a look at this paper by Friedrich Morgenthaler, Velocity Modulation of Electromagnetic Waves. Oh, my screen's still shared, right? I don't see the yellow, the green around the edge.
Yeah, no, we can still see you.
Good. Anyway, impedance modulation. So in this paper, Velocity Modulation of Electromagnetic Waves, Friedrich also accidentally proved that you could modulate the impedance of a wave, of a wave system. And he didn't see it because of the way he formulated his equation. But if you switch out mu and epsilon for gamma and v for velocity and for impedance, not in that order, then you get this other equation here where the new energy is equivalent to this velocity metric, v2 over v1, and then you have this other term, which is 1/2 gamma 2 over gamma 1 plus gamma 1 over gamma 2. What's interesting about this term is it's not time reversible. So if you increase the impedance and then you decrease it again, energy will just increase again. And actually, we found that this only seems to happen at resonance, but this might be another way to break CPT symmetry and extract energy that people can play around with, because, all you have to do to play around with impedance modulation instead of velocity modulation is you have to vary mu and epsilon inversely to each other instead of directly with each other. And there's potentially materials that do this, like magnetoelectric materials. And And there's some composites you can make. Stuff to play around with. Anyway, mobility. This is what people want to hear about, I guess, at a conference like this. But energy is probably useful too. Anyway, so my approach at present to all this research is, I think that gravity actually unifies at low energies. So sometimes they'll show you this like graph where electricity and magnetism unify, and then those unify with the weak force, and then those unify with the strong force. And then people assume that gravity unifies at even higher energies, which that doesn't make much sense to me, because if it unified at such high energies, unless it's some sort of entropic gravity model, then you would expect the graviton to not travel far distances, travel slower than the speed of light, basically have an effective mass. And we don't observe that. We observe a gravity that travels at the same speed as light, over the same distances as light for the most part. So I think it seems more likely that electricity and magnetism unify, then those unify with gravity at low energies, and then all of that unifies with the weak and strong force afterwards. So, and then there's also something, flying donut pulses and spatiotemporal optical vortices. Jeremy's mentioned this because I mentioned it to him. These are interesting, and they kind of demonstrate we still don't know everything really. These are Maxwell's equation solutions, which are toroidal in topology or geometry. So one of your fields is going around the ring of the torus, and the other is going along the axis of the torus. And that still obeys Maxwell's equations. It's still, everything's still right-hand rule and everything. But it's just a different way of looking at the photon. I mean, it's if you superimpose it, it's like composed of a bunch of photons that are going at 45 degrees or something out in some direction. Anyway, this shot noise, this is really important for understanding gravity, I think. There's actually a very elegant way of unifying them. And Todd's talked about an equivalent model. Jack Sarfati's talked about equivalent models. Basically, this squeezed vacuum state at the bottom here, that's your graviton. Imagine rotating that around the 2 pi here by 180 degrees, you get the same thing again. That just demonstrates you have something that's spin 2 geometrically. So, and there was another, I think there was a mathematical proof or some physics proof or something that said that if something can be found that is spin 2, then it probably must be the graviton. I think there was some sort of paper along those lines. In any case, a lot of these propellantless drives, like the Woodward thruster, I think at some other conference, the Estes Park, I think, they mentioned that it required second harmonic generation to function. And in fact, a lot of these apparently propellantless thrusters seem to require second harmonic generation. The thing about second harmonic generation is once you have that, you can have vacuum squeezing. So they could be actually graviton thrusters, potentially. Yeah, the other papers have shown that these squeezed vacuum states seem to carry energy and momentum, seem to have interaction cross sections with atoms, like a normal photon does, because they are in a sense a photon. They're just some entangled state of 2 photons, which is an equivalent way of looking at it. What's interesting though is the structure of this squeezed vacuum state is a variable amount of shot noise in the vacuum with a periodic with respect to space and time as the thing travels. And this, if you just take the shot noise as a concept and you imagine that, well, an atom has a lot of electromagnetic waves that it should be emitting by all the orbiting electrons, but those are all canceling out. Well, consider that if shot noise is a random variable, it probably can't cancel out perfectly. So all atoms are probably emitting shot noise around them as almost like light. And that would spread out with an inverse square law, just like the gravity field does, in the far field at least. So if you superimpose a whole bunch of random shot noise, what do you get? Well, I mean, if you roll 2 dice, the most likely thing you'll get is a 7. And the least likely thing will be a 2 or a 12. And if you roll n dice, you get a binomial distribution, and infinitely many, and you get a Gaussian distribution. And the outliers would be high energy events, and most of the time you get basically nothing. What does that look like? That looks like vacuum. That looks like our definition of the vacuum with quantum fluctuations. So what I submit to you is vacuum refractive index is defined by the shot noise emitted by matter. And a refractive index model, as people have been saying, there's Unziker's Real Physics, who talks about Einstein's original model of gravity, which was based on a refractive index of space, not a space-time curvature. Refractive index models and space-time curvature models are equivalent. But the refractive index model, in this case, gives you more insight into what's actually going on and why we have a gravitational field, potentially. The other interesting thing is the fine structure constant could be also considered a refractive index in close proximity to matter. It could be considered like the gravitational near field of a particle. And that has a lot of really cool implications that require more study. So, but why do we as observers see a constant speed of light? Well, particles, if the weak and strong forces are, well, let's say refractive index. If we have a variable refractive index in vacuum, then at high energies, what's to say we don't have nonlinear optical properties? Nonlinear optical properties lead to solitons and other behaviors. So what if we can derive the weak and strong forces as nonlinear electromagnetic equations? And I believe that's actually how electroweak unification was done. I'm not so sure about the strong force, but I'm learning still. But anyways, if we can describe these as the particles as nonlinear optical solitons, then they're still affected by this refractive index in space. So the reason that we observe a constant speed of light is because we're simply affected by the local refractive index also. And let's see, it's an interesting concept. I have a few more things to say about that, if I can. But anyways, yeah, so the other cool thing about this is it may actually allow us to unify, it may allow us to understand the limit case of natural laws at the surface of a black hole. Because what happens by Todd Desiato's model is these matter particles actually shrink at the surface of a black hole. So we don't necessarily need strings. We may be able to use classical particles to describe the hair, quote unquote, at the surface of a black hole. I don't know how you get unitarity back out of that, but it offers up some interesting possibilities. Basically, if you have a map of electrostatic field at the surface of a black hole based on the locations of all these particles, then you can have a relationship between that map of field and the places where virtual particles, where Hawking radiation appears at that surface of the black hole. Because, I mean, it's just electrostatic field right there. So you're going to bias what pops into existence. So there's a start of something there. And yeah, it could, the other thing is, let's see, where did I put that? Oh, that's back. Yeah, okay, here it is. No. Sorry, my bad. Okay, yeah, here we are. So looking at the Tic Tac UFO, there's some interesting stuff. I did want to mention something just to clarify. I saw Jack Sarfati and Todd Desiato talking about things. I think they're confused. The loss terms, they both use loss term, but they're using it in different contexts. The loss term in Todd's model describes the state of an atom. The loss term in Jack's model is talking about, well, essentially the transition from electromagnetic radiation to squeezed vacuum states, which is not like a classical electromagnetic. So it's that energy would be considered lost from the perspective of just the electromagnetic wave. But it's really just a conversion term to gravitons, sort of. So it has nothing to do with the size of the atoms. But I just wanted to hopefully help clarify that for them. And the Xanadu quantum computers, I just saw this recently. I was fascinated. It looks a lot like the bismuth magnesium metamaterial with the cadmium sulfide selenide, whatever it was, nanoparticles at the surface. They have some quantum squeezing resonators, and these provide squeeze states of light, and they go into an interferometer, and that geometry looks very similar to the bismuth magnesium composite with the nanoparticles at the surface for terahertz behaviors. If I had to guess, I would say that surface material just generates a massive quantum volume and just never measures it. And maybe that does something with gravity. I'm not really sure, but it would be interesting to play around with such systems. So one thing that people should know more about is, in terms of Jacques Sarfati's model, metals have refractive indices too. They just have a complex number as their refractive index, where the real term is the same sort of refractive index as like glass would have. And then the imaginary term of the refractive index is sort of the loss coefficient, like to conduction losses. And a lot of metals have really high refractive indices, but that doesn't necessarily get us something with a high gravitational refractive index, because if we assume that squeezed vacuum states are our graviton, that may have different interaction cross sections than normal light. Therefore, we can expect that if we want to extend the dispersion relation to include gravitons, we're going to have to take that into account, and it's probably not going to be the same refractive index as for a normal photon. So we have to. That's something that needs taking into consideration. Let's see. Oh, and properties at resonance. Yeah, this is cool. So there's something called a zero index metamaterial, and there's 4-wave mixing. And I want to clarify something that for Jeremy and others, 4-wave mixing really only happens at very high light intensities, because it goes to the third or maybe fourth power, I think third power of the, but I might be wrong on that. But yeah, it goes to some high power of the light intensity. So at low light intensities, the effect is not really present, just by the nature of the order of the effect. And so zero index materials and 4-wave mixing, these are both properties that matter has at resonance. So if we look towards the bottom of the page, this diamond thing that I have here, if we imagine that that's a space-time diagram with the past and future light cone, then if you initiate some event at some moment in time, if you bring your system into resonance, then in principle, it can have access to all the information in that whole time cone within that resonant state. And that's the power of these resonant systems. That's why they can have properties that matter does not normally have at when it's not at resonance. So zero index metamaterials, they really only have a zero refractive index, or appear to have a zero refractive index when they're resonating. Stuff like that. Maybe there's exceptions. I don't think there are, though. So what's interesting about this is you can think of vacuum as a zero index metamaterial for electrostatic fields. Once an electrostatic particle comes into existence, its whole time cone will be filled with that electrostatic field. It is an electromagnetic wave of zero frequency. Therefore, it takes zero energy to emit it. So anything and everything in its future time cone will be able to observe that electrostatic field, even if it falls into a black hole, because the black hole, if that particle is created outside it, can never swallow the whole time cone, as far as I know. Maybe there's some weird black holes with spin or other effects where that could happen. But for a non-rotating, non-charged, normal, everyday black hole, it cannot swallow the whole time cone of that particle. And that's why you would see charge on the surface of a black hole after you throw a bunch of charged particles into it. But what that's also saying is that in some sense, this electrostatic field is traveling faster than the speed of light, but it's not in the sense that you would expect it. So if you're outside its time cone, you're still not going to see it. But so if we take a look at this diagram in the diamond, you can imagine this is this dot represents an electron-positron pair that's created, and this path represents that electron's path through space-time towards an event horizon of a black hole. Well, if you're positioned anywhere in the shaded area, you will always see that electrostatic field, even if it's just directly straight across instantaneously to the edge of that time cone. So that's instantaneous propagation in a sense, but only because you can think of the vacuum as at resonance, quote unquote, with zero refractive index for electrostatic fields. It's a limit case, which does not apply to material, to wavelengths, to frequencies greater than zero. I mean, in a zero index metamaterial, now you can get a non-zero frequency that has apparently zero refractive index within the metamaterial. Similar idea. So what that gets us is something interesting we can play around with. We should be playing around with topological Tesla coils. Basically, that's this in the corner here. There's this idea of a Tesla coil where one of the top loads of the Tesla coil, it's a bipolar Tesla coil where one of the poles surrounds the other and is spherically symmetric. Once you have this geometry, now when you pulse that, you're going to get a near field at the surface, but not necessarily any far field transmission. So that lets you play around with these electrostatic fields in a way that you can squeeze via quantum squeezing. And I'm thinking that'll have some interesting effects, because actually it's really important for warp drives as well, because warp drives suffer from something called the horizon problem. Basically, how do you project your field in front of your spacecraft? And the way you would do this is with these electrostatic-like fields. So you bring this coil to resonance, and then you squeeze the resonance, so you have some squeeze states. Maybe you do some entanglement, whatever you're doing to it. Near the surface of that Tesla coil, as our first speaker today mentioned, you should expect this electrostatic field to travel faster than light, because it's essentially tunneling, and it's taking advantage of the fact that this electrostatic field is not affected by the light speed, the usual light speed. And that effect obviously falls off in the far field. And in this case, there shouldn't be any far field radiation at all. So I think it goes like exponentially relative to the surface or something and dissipates. But anyways, if you have this field that can get faster over the speed of light surrounding the craft, then you can build an actual warp drive, because now you can project a field in front of you, which normally with normal light, you wouldn't be able to do that. So yeah, play around with that, see what you get. It's a simple geometry to manufacture, especially with some of the technologies I'm working on. So now I'm just going to talk about random things that I've also brought up to Jeremy in the past. So I think Elon Musk recently said, if you can find a cube of titanium, like somewhere in the ground, then I'll be interested in looking up, like researching all these aliens and things, something along those lines. I'm paraphrasing. But we have something like that already. And if anyone knows Elon, let him know about this. So there's these Carbonado diamonds. They crashed probably around 2 billion years ago between South America and Africa before the continents drifted apart. And you can actually find in Central Africa and in South America deposits of these Carbonado diamonds as alluvial traces in sedimentary rock. So what's interesting is, upon inspection under SEM, we found some tiny pieces of we found all these like flakes of titanium, little, I think it was about 10, 15 micron rods of titanium embedded in this diamond throughout. There were some other papers that mentioned there were other metals. In the samples I found, I didn't find anything but titanium. I don't know of any natural process Like there are some people that would say it was from these carbon diamonds came from a supernova. But if it was from a supernova, I mean, even if it was a reducing atmosphere because all your oxygen is burned away, you're still talking about, you're probably gonna get alloys of metals, not just pure titanium necessarily. Unless, no, yeah, I mean, there should be chromium. There should be chromium if this is from a supernova. It should be mixed with chromium and vanadium and other refractory metals. But it's just titanium as far as I can tell. And we also, at the bottom there, the orange is oxygen. So this structure, it might look like rutile that was deposited afterwards perhaps, but and also, by the way, the striations in the EDS spectra here, or the EDS image, that's because the filament in the electron microscope we were using was about to burn out. So that's that. That's just something that's unrelated to the thing. What you should be looking at is the green versus the carbon background, the purple. So another thing that's interesting is people should be looking at gene drives. They should be looking for messages instead of using like SETI and radio waves. Well, first off, they should be looking at gravitons. If squeezed states and squeezed vacuum can be used for communication and happen to be gravitons, they'll go right through planets, or at least the interaction cross-section will be way different than a photon. So people should be looking for those using balanced homodyne detectors if they're looking for alien communications. But on top of that, we should be looking into gene drives, because there are lots of species that have been around for maybe 500 million years, maybe 300 million years. And if anything visited within that amount of time and was technologically sophisticated enough to edit DNA, they probably would have left at least something. Even if it was just accidental horizontal gene transfer, assuming that species had genes. But yeah, we should see what there is to find in other species, like ginkgo biloba, like blue-green algae, etc. There's a lot of sophisticated signal analysis and signal processing that people have been using in SETI that could be turned towards reading DNA. And that would be interesting to see. So consciousness, the nature of consciousness, people think about this in all sorts of ways. I'm thinking it might be simpler than a lot of people think. Oops, my bad again. It may be as simple as our minds are in some sense a neural net where the outputs of our neural net are also its inputs. That's all it needs to be, really, because so being aware of what we're doing, that's our outputs. So those are just our inputs as well. Now the specifics, I mean, of course there's quantum properties, because otherwise why would sleep evolve as a property? This is something that Jeremy has also mentioned, because I mentioned it to him. So we know there's some quantum processes in the brain, but with or without those, it's still some sort of neural net where your outputs are being reloaded into the inputs continuously. Now that provides some interesting things like, well, this is just another thought, I suppose. Telepathic communication, we're not anywhere near there yet, but if all of our abstract concepts are weights in some neural net, then it may be possible to design a system which basically goes inside your brain with quantum metrology and finds the nearest neighbor structures that would describe a concept and then activates those. There's something called a superconducting quantum interference device. That's kind of the closest we have for now. But I mean, now with squeeze states and other new properties, quantum metrology is about to get a lot more advanced. So we should expect that field to be able to really improve towards like reading brains at a distance. And I mean, Neuralink is still better for now, but one day, who knows? But yeah, I mean, if you can find, but the other implication is if you have a telepathic system like this, then it's going to be limited by how similar your neural connections are. So you'll be able to receive information better this way if you already have a matching concept in your brain that you can map to the concept that's being transmitted. Stuff like that. Anyways, some other things. Actually, for Jeremiah, he was just wondering about the magnetic beam device. It was interesting, actually, this morning I was thinking of exactly the same sort of thing. What if you had some wedges that have north and south poles at the inside and outside, and you put these together into a sphere? You have like 8 of these wedges and you stick them together. Well, south pole is supposed to, like, magnetic field lines are supposed to terminate on one of the poles. So if you trap this south pole somewhere, what happens? I'm guessing it kind of squeezes out through whatever hole is available. So if you have that magnetic beam device, you've got a bunch of north poles facing a certain direction, and all of that has to come out in one direction. I don't think it goes to a distance or something, but if you have a single hole through this sphere, then all of the south field or all the north field, whatever's inside, will have to escape through that single hole. So you can probably concentrate an extremely substantial magnetic field into a very small area that way, especially if you have very, very hard magnets. I imagine this configuration will probably destabilize the magnets fairly quickly if they don't have a hole like that. What else? Oh, so people should take a look at Emilio Loretti's work. Kind of quirky friend of mine who seems to be putting a, what do you call it? Knights Templar logo on all of the stuff he builds. I think the Knights Templar are still around. Well, whatever. He has a lot of interesting ideas regarding just classical electromagnetics. There's all these arrangements he's found in the past which appear to, at least via classical electromagnetics, produce a net force. So for example, here he has a dipole antenna, F432, where the currents in these wires cause the wires to repel each other, and that produces a force. I thought that was an extremely wasteful device because it's just a radiating dipole antenna. So I thought of an improvement here where you have a quarter wave antenna and you just have a whole cone that's all conductive. And then you have a capacitor plate that like attaches to the end of the cone with a really good dielectric in between. And then you just pump lots of amps into that cone. And you're going to, what you'd probably get is essentially a Z pinch sort of effect, but you have a slight, because it's a cone, you're going to have a slight angle. And a Z pinch effect can be very strong if you have a lot of current. So even though you're not, all of your force in a particular direction is, it's like partially canceling out. The force all over, like the force total is very strong. So the part that doesn't cancel should be quite a substantial amount of newtons. If it does indeed work that way, we'll see. So, and this design is nice because it's quarter wave. You can probably encapsulate it and you can minimize the far field radiation, and you can probably throw the Q factor way up there. And my guess is I don't think that these systems violate conservation of momentum. I suspect that most of these systems produce flying donut pulses or spatiotemporal optical vortices, or perhaps the squeezed, like the squeezed vacuum states. Those probably carry some amount of energy and momentum as well. In any case, some weird things to play around with. These are some places people should be paying attention to: Open Source Hardware Association, Hackaday, Open Source Ecology, more towards all of the self-sufficiency technology. Sabine Hossenfelder, of course. Eric Weinstein, Lex Friedman, they're good. Noam Chomsky, that's more political, perhaps. I hope I haven't rustled some jimmies with politics today, but whatever. So let's see. Yeah, and then some just good YouTube channels. The Hated one here, he's got some really good explanations of how to like do personal security, like internet security properly. ADV China, Lao Wai, those were the guys who figured out the stuff at the Wuhan lab. good on them. I hope they don't get in trouble with China. Anyway, I think that's just about everything. There's probably some stuff I'm missing, but any questions?
Okay, well, so let me do this. Let me mute you out first. And again, thank you for the presentation, everyone. If you are able to, tune in and give him a big hand. Okay, sorry about that. And I should apologize for interrupting you. I just wasn't sure. Jeremy Reese had me a little thrown with the mystery speaker part of it. But so let me see. I will unmute you again. And I think we had one hand up, and that was Evan. Ah, there we go. Go ahead, sir.
I'm sorry, I just hit the wrong button.
Oh, okay.
I was clapping.
Oh, no worries at all. No worries at all. Well, okay. Does anybody else have questions? And if not, we could just go to open discussion, but.
I actually have, if nobody has questions for the mystery guest, I actually have a couple.
I got a question here before you go on, Mark. Yeah, okay, a mystery guest. Please tell me how the heck to make these things work. Okay, because I pulse these coils every which way to Sunday. I cannot make this thing amplify a magnetic beam.
I don't think the intention. Oh, I don't think the intention is to amplify a magnetic beam at a distance, really. I mean, maybe. Well, so if I were to optimize this,
Bushman, the inventor, that's exactly what it's supposed to do.
Yeah, I don't think that's like he's probably. I don't know what he's doing, but if I were to maximize the field emitted by this thing, I would basically make like a solid sphere of magnetic material with a small hole coming out somewhere, with all the poles on the inside. Basically, if you have a really hard magnet like that, the preferred path for the magnetic field out of the center of that is wherever there isn't that very hard magnet. The permeability will just be too low any other direction. So I think the point of that was to concentrate the amount of magnetic field even more past what you would have been able to get with just those magnets, and the amount, what was it, the BH max, the maximum field that they can sustain.
Yeah, well, I mean, if you look at the design of the Bushman beamer, and it, as a predecessor to the David LaPointe magnetic system, he effectively just has a magnetic beamer, only instead of using just 4 or 5 magnets, he ends up using a plurality of magnets around the hemisphere, all pointing in towards what will be the focal point of that hemisphere. So it's just a different approach to basically doing the same thing. You're synthesizing a monopole on a macro scale by using a plurality of individual magnetic components. And
this is important. Some people were confused about this in the comments. So what I forgot to mention this. What I was trying to say about monopoles here is it's kind of a matter of semantics. Any dipole is 2 monopoles next to each other equivalently. And the thing with the vacuum in our universe is it's really easy to create monopoles of electrostatic stuff because particles have net charge. It's vacuum really doesn't allow that so much with magnetic fields, but you can create effective monopoles by arbitrarily moving the north and south poles relative to each other.
Well, right, and like an example of that would be buckyballs, right? C64 fullerenes, because if you take a look at the assembly of those atoms, what you end up with is a negative charge pointing towards the center of the buckyball and ending up with a positive charge on the outside, which actually allows these fullerenes to not absorb but adsorb, as in electrostatically attract other free radicals in the system that have either a neutral or a net negative charge. And so this is one of the reasons why if somebody eats something toxic, one of the first things that medical staff will do is feed them a huge amount of either just graphene or graphite or buckyballs in order to clear the system out and pull all these toxins out, because they're electrostatically charged. But the thing is, they're not actually monopoles they really don't exhibit true monopole behavior if you send them through an EM field, because they do have a balanced number of positive and negative charges. It's just that the geometry of those charges is not symmetrically oriented.
I think that's more adsorption chemistry you're talking about. When you have very, very high surface area carbon, just like activated charcoal, for example, it just likes to adsorb things.
Right. What I'm specifically talking about, though, is a true monopole in the genuine sense would be something that just had a single pole. So an electron is a true monopole, right? It only has one single charge. A proton is a true monopole. It only has one single charge. When talking about, this on a macro scale, you'd almost have to find a way to cluster these materials together, which is why electrets are great. And, listening to Ron Kita, which I'd like you to actually look into, if you've looked into Ron Kita's work yet, or if you haven't, I'd encourage you to. He talks about a number of ways to generate monopole materials, as in materials that have either a net lack or a net excess of electrons, therefore giving them a net monopolar charge, and therefore they will not respond to a motional electric field in the same way that, say, a balanced material, like almost everything else that we see in everyday matter, is.
Yeah, but that's electric field, though. So with magnetic field, it's just really difficult compared to electric field to move the poles relative to each other. But there's nothing physically saying that you can't move them arbitrarily relative to each other. For example, in spin glasses, like I mentioned to Jeremy at some point, you can move these around. Essentially, the magnetic monopoles become quasi-particles in the material. So, I mean, there's ways to move these poles around relative to each other. And that's really all that means. Like there was a video that I think you guys found a while back where someone made a solenoid coil where one of the poles was larger than the other, was like a cone shaped, and they were able to get a magnet to fire through the thing instead of getting trapped in the middle due to the geometry of the thing. And when you take that integral, but that's what we're talking about. Now one of the poles is spread out relative to the other. It's moved around. You just change the shape of the coil. You get a different, you just move these things relative to each other. So, I mean, you need essentially a metamaterial or you need to make a quasi-particle in matter. But I mean, effectively, if the poles are far enough apart, as distance goes to infinity, limit case, it behaves like a monopole. Anyway, but there were many other things discussed. Were there any other questions?
Okay. Well, I think, so why don't we do this? Thank you again for the presentation. I think, Mark, did you have something, or are we going to open discussion?
Just a short thing. I wanted to show the electromagnet that arrived, and there was a couple mystery items that were that came with it.
Okay. Well, so again, let's thank SPFL for his contribution and for that presentation. I think that worked out pretty well. It was a little slow to get started, but but definitely some good material there towards the end. And I will try and do the best write-up I can on that from the slides and stuff. So let me mute him out, and then I'm going to mute. Let me see. Oops. Sorry. Okay. So Mark, why don't you take it away, sir, for a bit?
Okay. Do you see the pallet in the warehouse? I'm sharing the screen. Do you see it? Do you see a black box? Okay. So this arrived. This was the only electromagnet that we could find that people were actually responding to emails, and it weighs over a ton. So we needed the forklift to move it in. Oops. And let me see. Okay, there we go. This is how it was packaged. That is the space. Now these two plastic acrylic things were actually easily removable. These are those double-sided threaded rods that you can just turn them around a little bit to expand it in and out. And I'll show you what that was in a second. These are the casters that came with it. We had to replace those. They're garbage. It also came with a Hall effect sensor, although there is no tool to attach it to. So, now this is the acrylic pieces. It had these little coils in them, with wires going to each coil, and still unsure what this was for or what it was used for. But you notice that the connections over here are all brass. So they were using non-ferrous materials for whatever it was they were doing. Not really sure what this was used for, either detection or modulation of the magnetic field. And that is the connector port at the end of it. This is the space. So we have like a 2-inch space between the plates, and the plate's diameter over here is 3.5 inches. So it's a pretty sizable space. I hooked it up to our KEPCO power supply, which is the bottom one over here. And I used this Gauss meter, which was recommended at APEC, at the last APEC conference. It's the Alpha Labs one. We also got the zero Gauss chamber to calibrate it. The magnetic field is pretty homogeneous. It's not like 100% perfect, but it is a lot tighter than anything we've achieved to date. And here we're just lifting it up and putting on the new canisters. And I'll just get a couple pictures, and there it is, sitting right there in our lab next to the Marx generator. So that's just an update from the lab about the electromagnet. This thing is very heavy. Pushing it around is kind of dangerous because, like, once you get it moving, it has as much momentum as a pickup truck. Really, it's a if you don't push it in the right direction where you want it to go, it'll smash into something and crush it, even going like 2 miles an hour. Really powerful. Okay, that's it. Any questions, any comments on what that little coil thing was? I guess not. Oh, Todd wrote in the comments, those are pickup coils. Well, wouldn't it only be able to pick up a changing magnetic field? Because
well, I think are we in open discussion now, Mark?
Oh, to pick up from the signal from the sample. Okay, I get what he's saying. Yeah, it's for NMR then, right? I'm reading off of Todd's comments in the chat.
Oh, okay.
Yeah, he said, yeah, that would be used for NMR for the to read the signal coming off the sample. Okay, that actually makes a lot more sense. Okay, I guess we're ready to go to open discussion then.
Okay, let's do it, guys. Let's do it. So we have had a big day today. Lots of coffee and lots of bathroom trips. I should apologize for that one that I didn't get back from in time. So yeah, I would say anybody who wants to join in, open discussion time.
How much Tesla we can get out of it. With our power supply, we're able to get 0.86 Tesla. And I think Thomas Anderson has a question for SPFL.
Yeah.
Yeah.
Yeah, and SPFL is still here. So I would say go for it, guys. Thomas, go for it.
I wasn't watching the chat, so if anyone had questions, feel free.
Oh no, it's my fault too. Yeah, I would say just let's just do open discussion now, guys.
I wanted to ask more about talk more about squeeze states and how that relates to polaritons.
Well, polaritons are one of many nonlinear materials. Well, so polaritons arise in nonlinear materials and allow very strong light matter interactions. So basically, if you have a material with very strong light matter interactions and nonlinear interactions as well, then you can get various quantum entanglement in the light. So 2 photon states, 3 photon states, whatever else. It's all about the, I mean, I've talked to you in the past about like parametric amplification. If you can make parametric, if you can drive a parametric oscillator at twice the resonant frequency, that is the most efficient way to produce squeeze states I know of. You can do it at 3 times or n times the frequency, but you're going to have weirder entangled states and produce less efficiently. But I assume those sorts of states have uses. So it's really, that is a type of materials that have polaritons in them interact strongly with the light and allow you to squeeze it. The polariton itself is just a means to getting that nonlinear coupling in this specific instance. I mean, you can use polaritons for a ton of other things too. You can use them for the photocatalytic water splitting that I mentioned with graphitic carbon nitride. You just have an exciton, and then you add some graphene layers to trap it as a polariton with a longer lifetime until it has a chance to split an atom of water. Stuff like that. There's other uses, but it all involving light matter coupling.
How do squeeze states interact with gravitons and gravity?
A squeeze state in this case would be a superset of the graviton, which unifies it with the photon. So the graviton that we're searching for in physics is in this case, in this model, what we think of as a graviton is the squeezed vacuum state without any necessarily like photon amplitude. So if you took some sort of squeeze state and you canceled out all of the net electric and magnetic fields, what you'd be left with is a wave of shot noise. And that is equivalent to the graviton in this case.
Hey, Victor Wag.
Oh, and if anyone has other questions, I'll put my email in the chat.
Victor Wag has a super chat for $35 in our live chat. He said, "Thank you to the mystery guest for an incredible introduction to the layperson like himself. Extremely valuable." Yes, I agree, and you know, hopefully providing that barrier or that bridge between these really smart guys in the academic world and then some of the experts that come on here. And the layperson, because breaking this down to ways that we can all understand it and sort of work with it in different ways. That's hopefully what goes on here. And thank you for that.
I was just going to say one thing I wanted to interject was your discussion about economy and whatnot. I think the problem is that most people want to jump straight to that Star Trek future and they don't want to do the legwork to get to it. But every time I talk to groups that are doing research and work in the background, I always hear we need, this equipment, or, it would be great if we could get somebody to give us that equipment, or if we had more money. And I think if they would spend a little bit of time focusing on that aspect of it to kind of squash that bug before they get further into their work, it would probably make their future work a lot easier. So I mean, it doesn't seem like it's a difficult thing to overcome if you're willing to spend a little bit of time just basically investigating it, whether it's like understanding how money works, or the process of like figuring out how to determine what is valuable to some other people so that you can then provide them with something that they'd be happy to have, and the things that they have that you need for your research, they're more than willing to help you out with. Once you have all that, then it's just basically a no-brainer to step forward. So unfortunately, the people that are so focused on the economy are usually not, they don't care about the science itself, so they're too busy ripping other people off, like the guy who was building the Slayer Exciter copies, and didn't seem to want to give any credit to the guy that G. Bluer, about the whole thing, I guess, because he was afraid it would somehow affect his financial value or something. But people weren't buying those kits with the little Tesla coil and whatnot because of his, them thinking that he invented or created it. They just wanted the tool. They were very interested in the actual tool itself. So, it could have been something where he could have even maybe worked out a mutually beneficial system between him and G. Bluer, and the two of them could have basically kind of like, got others that were more interested in just having a job to do the legwork, to put what they've got together, and then be able to basically push forward with their own works if that's what they were trying to do. Which I think, you know, Bloor is just more interested in electrical engineering and electronic engineering and, you know, designing and creating things. He wasn't really worried about making money, so that's why he wasn't the first person to try to sell something off of that Slayer Exciter design. So the manufacturing, though, I'll add to the economy thing. That is a big part of the reason why I put more of my time toward developing that kind of replicator level 3D printing upgrade, I guess, series of components for the technology to try to kind of cut the legs off of that problem completely, so that way it doesn't have to be focused on anymore. We can really get on to trying to, you know, test all these theories that people have thrown out there, or you know, new theories that people might have, or modifications to them where they see that maybe they could improve upon the design once they have done their, you know, their legwork of doing the testing to find something that actually has some sort of result they can measure. So of course it requires basically combining three pieces of technology. You've got to have the ability to refine or recycle to produce raw material, which you mentioned something about a spiral system that uses density for separation.
Yeah, spiral separators. They're used to mine monazite in China right now, and other things as well, I suppose.
Right. Well, and if you have like a, say, like a two laser system where one causes a chemical reaction, say to make like copper into copper oxide, but the other laser bounces off the copper, but it will ablate the copper oxide, you can now make sure that all of the copper oxide particles coming off are as small as, like, you know, you can physically produce because of the waveform of the two frequencies, so that they're very easy to work with. Then a little tiny bit of UV light and you can deoxidize that copper and cause the copper to collapse to form a solid copper mass, and just spread out layers of that powder back and forth while you know, laze over the surface, or run a, you know, a DLP system to reflect a high-powered laser where you change the shape of the beam itself with the little mirrors in the DLP system, and, you know, build up your solid copper component. So you know,
like this is a very long discussion and there's a lot of particulars, but one thing that's important to note about copper is there's only about 1 kilogram of copper per person on Earth. So for a realistic situation, you're probably going to have to rely on aluminum because it's so plentiful everywhere and the supply of it cannot be blocked. That's the idea.
Right, but you need to be aware too that aluminum is one of those things that, even though it's like the third most abundant element that's in the crust of the Earth, up until even Napoleon's era, because of the lack of knowledge on how to basically use energy to split and process the material to get at the raw aluminum, he had a whole group of dignitaries that showed up where only the wealthiest and most important got to eat with aluminum silverware. The rest had to just make do with solid gold. Yet now we can buy it for 35 cents a pound.
It's a little ironic though, because aluminum's not very good for your brain health long term. But anyway,
yeah, aluminum metal. There is something else to that though too. You know about zeolites, correct?
Yeah, but before you go on to zeolites, if you saw one of the things I mentioned, those aluminum chloride urea batteries can isolate aluminum room temperature. And aluminum chloride urea is not super toxic or anything relative to some of the other processes that would be used with like molten cryolite and high temperatures and crazy things. But yeah, aluminum chloride urea, inexpensive, not super toxic.
Seems like the chloride would have a pretty strong bond on the aluminum.
Very high thermodynamic efficiency. I think they were able to isolate aluminum. They were able to charge the battery with 99.7% Coulombic efficiency. So that is how you would basically take aluminum hydroxide and put it in hydrochloric acid and then mix it with urea and then electrolyze it at a couple of volts, and then you have your aluminum. That easy. Like these things are things we're working on in detail in various other groups, and we definitely need these solutions for the future of humanity. But yeah, it's not propulsion, I guess. So sorry for squeezing that into a propulsion conference.
Right.
But yeah, aluminum batteries, not only will they be a good replacement for lithium batteries, but then you have a simple, easy way of getting aluminum.
It might be easier to charge and discharge those too, since aluminum is amphoteric, so it can
Especially
act
under
as an
aluminum.
acid or a base. It doesn't matter.
Mhm.
What matters is what it's interacting with. So
Yep, nail on the head right there. Good stuff. Any other questions? I mean, people can email me too, but
you should maybe I don't know if there's any source already where they talk about your you were talking about urea to make graphitic carbon nitride through, I'm assuming you're talking about the thermal decomposition process.
correct.
Maybe some resources so people can basically avoid having to, you know, reinvent the wheel. If it's something that's already been accomplished, like Robert Murray Smith was doing with, was it silicon carbide powder to act as a microwave to thermal, basically using it to make a thermal emitter from a microwave emission. So you use a microwave oven to basically turn urea inside of a small vestibule into a, I guess he got like 30 or 40 grams worth of graphitic carbon nitride out of that. So
it's basically the only process you're going to want to use for photocatalytic water splitting, at least, is under ionic salts, specifically because the patent for that doesn't cover potassium chloride, lithium chloride salts, and then also just under a molten chloride salt, the crystalline structure is way better. The semiconductor, the band gap is way better and tunable. And then on top of that, ideally what you want to do for photocatalytic water splitting, and I don't understand why people haven't done this. You want to do photocatalytic water splitting at high temperature, high pressure, because then you get the lowest energy to split the water, and also you get the largest adsorption of.
I seem to see a common misconception of the photocatalytic cracking of water. It's not photocatalytic cracking of water. The water is cracking naturally on its own because of the catalytic reaction of the material. It's the photons that break the material free so that more water can get to the sites. Kind of like with the zeolites, where basically the site is so reactive, it'll tear other molecules apart in order to kind of fill its void, to make it's like a bunch of little cookie cutters that fill themselves up with these different components because of their electrostatic attraction and the size of the site. And then you got to figure out how to get those chemicals out without destroying them. So the photons make a very good way to basically push the material out. It was something that I wasn't, I was basically looking into the concept of using, because that's basically, you're using carbon to essentially cock block the nitrogen from making a permanent bond with either the hydrogen or the oxygen, but its energetic state through the neutral conductive state of the carbon allows it to transmit between the two so that it can still reach through it electrostatically to pull the water apart. And that way it only takes photons to just knock it loose from the carbon. If you add a base along with the acid to make a hybrid, you wouldn't need the photons, because the vibrational energy of the heat itself would cause the displacement constantly because of those two electrostatic states constantly charging. And this may be happening naturally in the Earth's crust, coming up out of the ground, and anything that's in the ocean would start cracking water to release oxygen into the air. Maybe providing the reason why there's oxygen and not the plants themselves, since after they die, they release all that carbon dioxide back into the air.
Not necessarily, but also, if that were happening, wouldn't we already be out of hydrogen? There would be a very different equilibrium of hydrogen on the surface of the Earth if there were that much water.
If it were a consistent process that the material isn't destroyed, so it has to be constantly being replaced by geological formations of like the tectonic plates moving across each other and whatnot, and the pressure and the heat necessary to create them in the ground. On the other hand, though, if you take table salt and add it to that solution system, it'll destroy your photocatalytic cracker, because the chlorine will create a stronger effect on the carbon and break it free of the nitrogen, and then you end up with exposed nitrogen. The sodium reacts with it, damaging it too. So you need a perfect interlocking system in an equilibrium of water that doesn't have any contaminants that could basically sabotage your components the same way zeolites have to be protected from sulfur whenever you're breaking down and reforming the compounds they get from distilling oil. So if there's a lot of sulfur, that's what they call sour oil, because it destroys their zeolites, and then they have to go out and spend more energy to make more of them, and they have to waste some of the material in order to get the patterning on the zeolites that they're making too. So it can be, you know, pretty wasteful because of that, just because of that sulfur, because they didn't get rid of it first. So in nature, I would say that's probably the reason why we don't have an overabundance that creates that destruction of what we have. If we didn't have all those extra elements, we would probably have a free fall into a pit. But that shows us, if that's possible, one of the ways that we can basically make sure that star travel can be maintained sustainably in space, if we know how to reprocess all our materials using these little tricks. We just have to basically figure out how the Earth has done it to make sure that we're using the most efficient means rather than what everybody thinks is going on.
Sure. And also, I would like to add the other thing is, if you have a salt solution, now your liquid is conductive and offers a path to short out any excitons that form.
Right.
So just another step in the process. But yeah, I mean, you're still going to have higher reaction rates, because a lot of these have a really good band gap, but they have poor adsorption properties, even though they have a good long exciton lifetime. So really, the only thing driving that absorption that you have remaining to try is temperature and heat, temperature and pressure. So, I mean, graphitic carbon nitride really doesn't have a problem with adsorption rates, though. But I think the lifetime of the exciton is just short. But then you can modify it with heterostructures, and I've seen cobalt tetroxide work really well, but cobalt is pretty rare.
I've heard of people using ferric chloride too. They'll rebake the graphitic carbon nitride with that to basically dope it either with the iron or the chlorine to basically improve its photocatalytic properties. So,
excuse me, I'd like to share something. It's a paper that just recently came out, and basically what it's called, factoring in gravitomagnetism could do away with dark matter. Observations of galactic rotation curves gives one of the strongest lines of evidence pointing towards the existence of dark matter, a non-baryonic form of matter that makes up an estimated 85% of the matter in the observable universe. Current assessments of galactic rotation curves are based upon a framework of Newtonian accounts of gravity. A new paper published in EBJC by Gerson Ludwig, National Institute for Space Research, Brazil, suggests that if this is substituted with a general relativity-based model, the need to recourse to dark matter is relieved, replaced by the effects of gravitomagnetism. The main role of dark matter, Ludwig points out in the paper, has historically been to resolve the disparity between astrophysical observations and current theories of gravity. Put simply, if baryonic matter, the form of matter we see all around us every day, which is made up of protons, neutrons, and electrons, is the only form of matter, then there shouldn't be enough gravitational force to prevent galaxies from flying apart. By just disregarding general relativistic corrections to Newtonian gravity arising from mass currents, and by neglecting these mass currents, Ludwig asserts these models also miss significant modifications to rotational curves, the orbital speeds of visible stars, and gas plotted against their radial distance from their galaxy center. This is because of an effect in general relativity not present in Newton's theory of gravity, frame dragging, or the Lenz-Thirring effect. This effect arises when a massive rotating object like a star or a black hole drags the very fabric of space-time along with it, in turn giving rise to a gravitomagnetic field. In this paper, Ludwig presents a new model for rotational curves of galaxies, which is agreement with previous efforts involving general relativity. The researcher demonstrates that even though the effects of gravitic fields are weak, factoring them into models alleviates the difference between theories of gravity and observed rotational curves, eliminating the need for dark matter. So I invite you guys to follow the link and read the paper. Thanks.
Thanks. Thank you. Yeah, we'll take a look.
I'm actually kind of wondering that you mentioned the spin of the galactic spin. If anyone has considered that the reason why we don't see hardly any antimatter is because of a Coriolis effect from the universe itself rotating, and that, you know, if you were to like achieve a point of reference from the opposite hemisphere, maybe you'd find the majority of the material would be antimatter rather than matter. So kind of how cyclones and hurricanes spin one direction or the other depending on which hemisphere they're on, as well as the rotation of the Earth, for the most part controlling which direction they flow. Whenever they form, they tend to always move from east to west, as well as moving from hemisphere toward the pole. So,
would you need antimatter if you had anti-gravity?
well, I'm not talking about a need for it. I'm just wondering if that might have some effect to it, because if the universe itself is rotating, it would definitely have to be taken into account for any kind of star travel. We'd need to know where its universe center is, as well as the direction of spin, and if it's drifting, what direction it's drifting to, in order to account for longer range travel, especially between galactic spires. So, and it could affect every experiment someone's doing if they're not accounting for that too, giving them a bunch of random noise they can't figure out why they're not getting an accurate measurement too. Sorry, I just had to get that last bit in.
So it would have an intrinsic spin to it. Is that what you're suggesting?
Well, I'm not saying it does or doesn't. I'm saying that it's something I haven't heard of anybody looking into. So it may be something we may need eventually to look into in order to kind of finalize and get rid of a lot of the need for fudge numbers in mathematics, where we do the testing and then we take the results and apply our answers to those numbers. We're not sure what the right answer would be or the right input would be, and adjust those numbers and constantly having to adjust those. For one thing, if we have a frequency that the entire universe is vibrating at, and that frequency is drifting, which accounts for our temporal movement, when you cross a barrier where there's something in your experiment where it's effectively matching that frequency, that would cause some random noise. You wouldn't have any idea what it was from, unless you have like an extra universal frame of reference, or you have enough information on how the universe is actually functioning and aren't completely ignorant of like things like, you know, universal rotation and whatnot, and how it could affect you. Once you have that, though, then it makes it a lot easier to go, oh, well, that's probably because of this, and that's probably because of that. And then you can start weeding through all the noise to get the true results you're looking for, so that they're not making it difficult to get your end result.
So, I can answer this. I can answer this question definitively if Tim would let me share my screen for a minute.
Well, may I mention something? The thing is, what do you mean by universal rotation? Because if you're thinking of like a reference frame of the vacuum, that's been shown by the Michelson and Morley effect not to exist. But well, yeah, I mean, Eric, go on.
Can I share my screen, Tim?
I don't know.
Is he there?
I don't think he's there.
All right. Well, let me just let me share my screen here.
Well, we're waiting.
Did somebody call for me, or did I misinterpret that? I was in the other room. I'm sorry.
No, nobody called for you, Jeremy.
I think Tim. Anyways,
Here we
I
go.
would like to add a little anecdote though. After the Michelson-Morley thing happened, and we assumed that, then people started assuming that the vacuum had no material properties since it didn't have a reference frame. But the variable speed of light models are, I mean, basically they consider a vacuum with material properties, but not necessarily a reference frame.
So do you think that the vacuum is has a constant density in all regions of the universe, or do you think there's regions of the universe where space-time is denser and regions where space-time is less dense?
It depends on what you mean, because all of the observations will be consistent with curved spacetime, because a variable refractive index model with matter also affected by the refractive index will just appear to us to be a constant speed of light, constant refractive index locally, because
So
we're just right down too.
So
but at a distance, that's where it counts.
Would you think that when you say space-time, would it, in your mind, would you think of it like the sphere on the membrane, or would you think it as space-time looking different? I kind of look at it, space-time as concentric shells. So the closer you get to the matter, the more time slows, for example, because you're closer.
Well, is my screen showing here?
Yeah, but it's really tiny print. Can hardly.
Is it really?
Yeah, it's too minuscule to read. There you go. That's a little better.
Is this better? I'm on a phone. It's the problem. Is this better? Can you read this?
Yeah, that's working for us. Don't go any bigger there, or we'll lose it.
Right. So Randall Mills has a theory of an oscillating universe that transitions from a minimum size where everything is matter, and then it transitions to a maximum size where all the matter converts to energy. And so the reason that the universe is neutral is because during the contraction phase, where we're in the expansion phase now. So the rate of expansion is proportional to the rate at which stars convert matter into energy. And so space-time expands for every 3 times 10 to the 22 kilograms of matter that converts to energy. And that's what actually drives the expansion of space-time and the acceleration of the expansion. So we're in the expansion phase. During the contraction phase, where that phase starts out where everything is energy, matter is formed by a neutron production pathway. So the reaction that occurs, so at the end of the expansion phase, when all matter has converted to energy, there are gamma rays and electron neutrinos left, and they form neutrons. And so that's the very first particle in the contracting universe. Then the neutrons beta decay to hydrogen, electron, antineutrino, and then the beta decay energy. And then you've got the electrons, binding with the hydrogen atoms to create hydrogen, and then you've got things coalescing, and basically it's a different. There's no Big Bang in this situation, and so the number of electrons exactly balances the number of protons. The universe is electrically neutral. The universe is oscillatory in matter, energy, and space-time, without the existence of antimatter due to conservation of spin of the electron neutrino, and the relationship of particle production to space-time contraction. So when what that means is that when matter converts to when energy converts to matter, when an electron positron pair is formed, space-time will contract relativistically. So the metric changes from Minkowski to Schwarzschild during particle production. And so the same type of special relativistic correction that you get when a particle, approaches the speed of c, when energy converts to matter and you get an electron-positron pair, contract, and in a resonator cavity is formed, and the photon that creates the electron-positron pair is trapped into the resonator cavity that becomes the particle. And the electric field of the photon induces the charge on the membrane of space that was contracted, and that's where the charge of the charged particle comes from. It's actually induced by the primordial photon that created the particle.
Eric,
and so all this happens in the particle production frame, which is the absolute frame. So it's the only frame that you can reference, that you have an absolute reference, because the speed of light is 0 in that frame. Light will the band stop filter will stop light, and it'll create the particle pair.
Eric, I got a simple question. Would you say that the universe has an inner and an outer event horizon?
Well, I think you were the one that was mentioning the spherical shape. So it's an R sphere. You know what an R sphere is? It's topology. So the universe is closed. So in this model, the universe is closed, but it has no boundary. So it's finite, but it has no boundary. So it expands into nothingness, but the amount of matter is finite. And when the universe,
if you go into the future, there's less neutrons, and as you go into the past, there's more neutrons.
Well, remember, it's a cycle. So the arrow of time is running forward now, and
but after it reaches the end of that, you say it turns around and goes the other way, right? It contracts.
That's right. When all of the matter in the universe converts to energy by natural processes, then the universe will then contract, and the arrow of time will reverse, and this neutron production pathway will take over, and matter will start to form according to that.
And so we're in the expanding time frame, and so that means there's another time frame where it's contracting that we can't see because time is reversed.
In fact, matter is created during the contraction phase when the arrow of time is pointed backwards, and spontaneous chemical reactions cannot occur. So life cannot arise in the contraction phase. And so astronomers find celestial objects that are older than the universe, and they don't understand how that can be. Well, the reason is that they were created during the contraction phase, before the arrow of time reversed. And so they were created prior to time equals 0. At time equals 0, the universe is at its minimum size, its gravitational radius. And at that point, at that point, the first, the first decay will happen, or the first, the first conversion of matter into energy will happen, and the expansion will start driving itself. And so here's like, for instance, a plot of the temperature of the universe during the expansion phase. And so you see the universe starts out extremely hot and gets very, very cold. But he's derived all the cosmological equations for the radius of the universe, the power of the universe, Hubble's constant. I mean, every single cosmological unsolved problem he has solved. For instance, the power of the universe. So it's a 1 trillion year cycle, right? So the cycle is 1 trillion years, almost 1 trillion. So, and it goes back.
So what's the name of the theory? What do you call the theory?
This is the grand unified theory of classical physics.
And now, is it like, is this the same as the oscillating universe or whatever they call it? So you got a big bang and then you got a big crunch, essentially.
No, there's no big bang. It's an eternal universe that's always been there.
So it's just cycling around. It doesn't have a beginning or an end, correct?
It doesn't have a beginning or end. It has the beginning of the expansion phase and the beginning of the contraction phase. And it's a harmonic oscillator. And so there's a restoring force, literally a spring restoring force that causes the universe to start contracting again.
So it's cyclical. It's cyclical, you would say, right?
Yes.
So what's the period of the cycle?
Universe.
Are we talking trillion years? Is that what you said?
It's 1 trillion. It's 999 billion point some years, almost a trillion years.
Okay, and
this is really the key equation. This is the quotient of the universe, and so this equation here tells you that for every 3.22 times 10 to the 34 kilograms per second of matter converting to energy. So 3 times 10 to the 34 kilograms of matter convert to energy every second. So stars are burning and converting matter to energy. And that conversion causes space-time to expand. Remember, when a particle is created, space-time contracts. When a particle annihilates, space-time expands. And so what's driving the expansion of the universe are all the stars in the universe burning and converting mass into energy. And this
is there black holes in this universe?
Yes, at the center of every galaxy is a black hole.
Okay. And it's an interesting theory. So one question I have, we're talking about neutrons a little bit.
Yeah.
My understanding of that, neutrons are unstable when they're free. They decay into a proton, an electron, and a couple neutrinos. So if you're when you're condensing, it's converting to neutrons. In that state, would those neutrons have to be stable?
No, a free neutron is not stable. It decays.
No, I'm not saying it's in our. So we're in an expanded. We're in the what you would call emergent cycle. We're in the emergent cycle, not in the contraction cycle, right?
Right. We're in the expansion.
Right. So, but I'm asking about in the contraction cycle. In order for this to work, wouldn't the neutrons have to become stable?
No.
You know what I'm saying? Because right now, as we're going expanding, free neutrons are unstable, right? So in our state, they have a lifetime.
That's correct. Yes.
Right. But I'm saying in the contracting stage, wouldn't that lifetime have to be longer or almost infinite?
Not at all, because that's what drives space. All of the energy in the universe is in the form of gamma rays and electron neutrinos. And the restoring force occurs, and this reaction here, the gamma ray plus the electron neutrino, in one step forms a neutron. And that can only occur in the contraction phase because of the thermodynamic requirements.
But it's saying it requires 0.7835 MeV too. You need to add some energy in.
Well, no, that's the beta decay. That's the beta decay. So the gamma and the electron neutrino have the sufficient energy to create the neutron. Then what happens is that the neutron then decays, and it decays into hydrogen, an electron, antineutrino, and an optional energy. This energy is sometimes given to the electron, the beta particle. And then this beta particle will then combine with this hydrogen proton and form a hydrogen atom. And then matter will start to coalesce.
So that hydrogen atom is ion. It doesn't have an electron.
No, it doesn't. It's a hydrogen at
ion.
It's a proton. It's a proton. And this beta particle is an electron. And so that's the neutron production pathway that is the reason why the universe is neutral, and not full of antimatter. I was going to show you real quick the I don't know why I can't. I've got to do this way, but there should be a way to very quickly. I don't know why I can't do this, but
just be patient.
Yeah, I know, but I all right. So here's Mills. Here's Mills' propulsion mechanism. So in his model, the free electron is a two-dimensional particle. It's a membrane of charge, and the charge circulates in rings. And the truly free electron is flat, and it has no gravitational mass. So it has inertial mass, but no gravitational mass. And when a free electron combines with a proton and forms hydrogen, that's when it gains curvature and it gains gravitational mass. But when it's a free electron, it has no gravitational mass. And what that allows is that the free electron can absorb a photon because remember the electron is a resonant cavity, and so it can absorb energy. And so when the electron absorbs the correct amount of energy, it turns into a sphere as if it were a bound electron in a hydrogen atom. But the current that's flowing around the surface of the electron, the supercurrent, is guided by the trapped photon that's inside the resonant cavity. And the photon is of such high energy that the electric field of the photon causes the current elements at the poles of the electron to circulate at almost the speed of light. And so if you plot if you plot the velocity of the current along the z-axis, it'll flare out at the poles. And so that creates a hyperbolic or a negative curvature. And so when the electron is in this state, it's called a pseudo-electron. And so it's a real electron, but it's got a negative space-time curvature. And so, he's gone and derived the geometry and all the energies that are the resonance energies that are allowed to create these types of electrons. And, everything's in force balance. And this is sort of what the normal vectors look like in terms of electric field on this negatively space-time curved electron. And so what happens is, and so the way you get propulsion out of this is these electrons are ejected away from massive bodies at a tremendous acceleration, because they're very, very, they have a very high amount of curvature. And the more energy you put into them, the higher the negative curvature they have. And so they may accelerate away from the Earth at like 1 trillion times the acceleration that any other object would. And so the way you get propulsion out of this is you convert the electron to a pseudo-electron so that its space-time curvature is negative. And then you accelerate the electron between capacitor plates such that the negative plate is in the direction that you want to move, and it's opposite the gravitational mass, like the Earth. And so the electron will be ejected away from the Earth gravitationally by virtue of the fact that it is negatively curved, whereas the Earth has positive curvature. And so that acceleration happens on a gravitational basis. And then when it happens in between capacitor plates that are mounted to the craft, the negative electron continues to be negative, but it's ejected toward the negative plate of the capacitor. And so it pushes the negative plate away while pulling the positive plate behind it, while the Earth is ejecting it at 1 trillion times the acceleration that it would normally have. And so essentially you get some incredible accelerations with this. And the gravitational power that is provided by just 200 amps of pseudo-electrons is around 9.4 gigawatts of gravitational energy or power, 9.4 gigajoules. And so this is running continuously. And so it doesn't take very much energy to get some really astounding accelerations. So here's the free electron that I was talking about. When it's free, it's two-dimensional, right? And so there it is on its side, and the density of current is highest in the center, and the radius shrinks the faster it moves. And so a free electron that's traveling very fast will be will have a very small radius, and vice versa. And there's many ways. So you can collide these with gamma rays, or you can collide them with certain geometric structures that will also cause the resonance to happen. So trihydrogen is one molecule that has the right shape. And so there's different ways you can create these pseudo-electrons. And his hypothesis is that the jets that are shot from black holes are probably pseudo-electron jets. And you'd have to go through the book and and understand why he hypothesizes that. But it's an amazing book. I would recommend it pretty much to anybody. And if you doubt it, I guess you can sort of look at what they just released. So they have a 250 kilowatt power source. That is pretty close to market. And this thing is only using water. It's using very, very small trace amounts of water. And it's a catalytic reaction. So water, so hydrogen is fuel, and nascent HOH is catalyst. And so this catalyst will bring the hydrogen down to a lower energy state below the ground state. And it's a stable state. And so the potential energy that's there stored in the atom is released when it's coaxed down to the lower energy state. And this is 250 kilowatts of power. Flash boiling and superheating water with probably a drop of water going into the reactor probably every 5 seconds, is what I'm guessing. And this reactor is about a month away from going to market. It's a thermal reactor, so I think a lot of people are not paying attention to this company and it's Brilliant Light Power. And I think a lot of people are going to get surprised when when some of these things start coming to market.
Hey, Eric, could you post a link on the chat for that company, please?
No, sure. So
Okay.
it's brilliantlightpower.com. And the book is I'll put the link for the book. But anyway, I think there's many more than one way to achieve propellantless propulsion, and this is just one of the ways.
Thanks.
Why is everybody being so quiet?
No, I'm done. I was going to give a much longer presentation on this some other day, but I'm exhausted. My voice is shot. So
I think we all
I hear
are.
you, bro.
Okay, well, it's been fun, folks. I think I'm going to sign off now and look forward to the next conference.
yes, it was great. I thank everybody.
It was fun.
I guess Tim is
Am
Probably
I
napping.
Thanks everyone. I am gonna end the stream right there on on YouTube. Thanks for everyone who joined and everyone who donated to the super chats. We'll catch you on the next one, and of course during the week.